the mayor.
Ladies and gentlemen, you've heard the reports that enemy planes are approaching. In less than 3 hours, an H-bomb might fall over Portland.
Like myself, I think you're going to be very interested in this story that we're going to tell you. And in this age of missiles and man-made moons, it takes on added significance. There are no actors in this story, but there are a lot of people. The people of the city of Portland, Oregon, and what happened to them, or could happen to them, on the day that we'll talk about. This is the land, between the mountains and the sea, between the snow-capped crater of Mount Hood and the Pacific. It's tall timber country. And this is the city, largest dry cargo port on the Pacific coast. And its people are friendly and rugged in the tradition of the Oregon Trail. Population, about 415,000, more or less about the size of the ocean. And this is what happened, or could happen, on a certain day called X. The sun came up at 6:31. Joe Kodak was there to observe and chronicle the event. The paper, Joe noted, was a little heavier than usual, but naturally he didn't stop to read it anyway. And Mrs. Frank Stukel, Portland housewife, mother of 5, was concerned at 8:02.
John, it's time to get up. You'll be late for school.
Children late and coffee boiling. With these problems duly appraised, she turned to the women's page of the Oregonian, thus managing to avoid the front page, which, after all, contained nothing but scare headlines. The time?
The time is 8:27. Wake up, Portland. It's a wonderful day today.
Stay tuned to KOIM for the best music and music. And now, we continue our wake-up show with more Grandpa Shoot.
At 8:36, the population of Portland increased by 1. Timothy James made his first comment at a local hospital and settled down to life in the 20th century. Like all communities, religion is important. The people, like its church architecture, are forward-thinking. At 9, a special service is being held. And at the busy port, at 9:18, Ray Matthews, the longshoreman, loaded scrap iron bound to Japan. At 9:37, at the Central Fire Station, the men were busy with their morning chores, scrubbing holes, cleaning ladders, and shining the pumper. By 10 that morning, at the Harvey Scott School, the kindergarten class of Elsie McGlendon was much involved with the morning's activities. And the twice-weekly meeting of the city council was much involved, too. The matter of sewer maintenance was one of the problems up for discussion. At police headquarters, the messages at 10:31 so far indicated 2 cars stolen, drunk and disorderly. An average day in an average American city.
Cat in a tree, 14 in agony.
Except this day is the one called X.
Attention all police. Emergency. This is an air raid warning.
aircraft over Canada and Alaska. Time to Portland, 3 hours, 15 minutes.
Thank you. I'll notify the mayor.
At 10:32, Jack Lowe, the city's civil defense director, received the words. Enemy planes have crossed the pole. Probably they carried H-bombs. Likely one, maybe two, are headed for Portland. The mayor delivered.
Clerk, gentlemen of the council, I've just received the information that enemy planes are approaching this area. Just authorized the sounding the evacuation. The council will be in recess and we will immediately reassemble at the emergency operations center.
Until this day called X, which began in such an ordinary way, is no ordinary day. At 10:35, the banshee wail of the siren echoes the warning, and the city prepares for survival. And there are those like Tom Cook who can't go. He's one of the power load dispatchers for all electric power in the Northwest. These men are expendable. Others can and do go.
Commonwealth radio alert. Normal broadcasting will be discontinued for an indefinite period. Civil defense information will be broadcast in most areas at 6:40 or 12:40 on your regular radio station. I repeat, this is a Commonwealth radio alert. Normal broadcasting will be discontinued for an indefinite period. Civil defense information will be broadcast in most areas at 6:40 or 12:40 on your regular radio station.
When the sirens sound, some cities go underground, take to shelter, particularly if there's little warning. But Portland evacuates according to a well-thought-out plan. The question is at 10:45 on the day called X. Will it work? Quietly, without panic, the city organizer becomes a mobile the best it can. Civil defense is not apart from normal city functioning. The same utilities involved in caring for a city in peace are those equipped to care for her in an emergency. And when the siren sounds, each man knows his responsibility. Public buildings follow a pattern well learned in practice. The idea, to move out of the city, to move fast, but with caution. Like other Portland mothers, Mrs. Cooper moved her family to a prearranged location outside the city beyond radiation range of necessary supplies. Things again, and his mother go for an unexpected ride in a moving van in the first day of life. Now, at 10:50, in the tower of the city, the seat of local government is moved a point some 6 miles out of town. Buried in the hill is a blast-proof, radiation-proof operations center where government can continue to function. Evacuation can be controlled, and if necessary, the city can be reorganized. The Portland plan revolves around the local government with Mayor Terry Trump as head. Government must survive if its people are to survive. Civil defense is government operating in an emergency.
Good morning, Mayor. The situation looks pretty bad right now. We just exactly what's happening. Planes over Alaska and Canada.
Ladies and gentlemen, you've heard the reports that enemy planes are approaching. In less than 3 hours, an H-bomb might fall over Portland. Mr. Jack Lowe, Civil Defense Director, will coordinate activities here. Jack, what's the system?
Mr. Mayor, according to our latest reports from CONAD, enemy planes are still headed this way at 450 knots. That will put them just about there on the Alaska-Canadian border. I'd say we still have about 2.5 hours if Portland is where they intend to make a drop.
What's the condition of the evacuation movement?
Well, we have very scanty reports now, so it's only been 15 minutes, but we can check with the police and with the traffic engineer and see if we get what information we have. I have no information yet as to how it's progressing.
By 10:55, the heads of utilities, Red Cross, military liaison, Civil Air Patrol, Weather Bureau, and all city departments are functioning as a civil defense team. While city commissioners and bureau heads remain behind working with their departments at the emergency seat of government, their families are among those evacuating. By 11, the operations officer is receiving reports on the evacuation of the city. And he is the reporter of the day. Traffic, time, weather. And in the operations center's broadcast studio, the time is...
The time is 11:10. This is an official civil defense broadcast. Enemy aircraft are over Canada and headed this way. Normal broadcasting has been discontinued until after this emergency has passed. You are now tuned to Conrad and will receive official information and instructions on this frequency. Keep your radio tuned to this frequency. Remember, there is a traffic plan for the evacuation of the city. All cars in the downtown area must follow the green light. They will lead you out of the danger area by the quickest route. Do not try to cross the flow of traffic. Follow the green light. Turn with traffic. Proceed with care.
John Carpenter, the sportscaster, becomes the warning voice. The people of Portland know his voice. Trust it. In 1955, Portland held a practice mass evacuation. The heart of the city was cleared in 34 minutes. It's safe to say that practice evacuation will be responsible for saving a great many lives this day. Should the bomb fall, many will be killed. The more that move out of the city, the greater the chances of survival. Pedestrians are helped out of the city. The great dangers are jam-ups and bottlenecks. Whirling over the city, a police helicopter reports traffic movement to the operations center.
Copter 1 to dispatcher. Copter 1 to dispatcher.
Copter 1, go ahead.
Marvin Slaven traffic moving very slowly, bumper to bumper. Suggest 1 or 2 lanes be diverted east on Hamilton. Over.
10-4, 11:31.
And at 11:32, at the operations center, Police Chief Hillbrunner receives the suggestion, and with traffic engineer Fred Fowler, he works out a way to divert traffic. Motorcycle policemen are sent to split the load onto a side road. There's no way of knowing if Portland actually is an enemy target. But with 3 hours of running, and the time fading fast, it's vital that all roads lead to safety, that all roads be kept open, allowing people to evacuate from the potential target area. Meantime, county and state police halt and divert incoming traffic away from the target area. Should a bomb fall, fire and utility equipment must be available to move back into the city to restore services. And so trucks of all sizes and of all varieties speed to points outside the city by a detailed plan. By 11:45, the men and equipment have arrived at the dispersal areas away from the target. Auxiliary police and auxiliary firemen are also in action.
This is serious business, man. We anticipate attack. Secure your vehicles as best you can. Turn off the ignition. Put on the tarps on the fire apparatus. Take the radiation instruments with you. Move immediately to dispersal area. Move as quickly as you can to dispersal cover. I say again, move to dispersal cover.
Around the dispersal area, in local public buildings, emergency kitchens are in operation. Rumors are everywhere. Facts are hard to find. But back underground, at the operations center, with time running out, only facts are considered.
According to information we have just received from Western Air Defense Command, the situation remains the same. Enemy aircraft are still approaching this direction. If they continue on this same course, we can expect an attack in this area anytime after 21:47 Greenwich time. That is 1:47 p.m. Pacific Standard Time. And now I would like a brief situation report from all departments on how we stand. First, John, what is the fallout situation?
Jack, according to our latest weather information, the winds will continue in a northeasterly direction at about 10 knots. Let's face facts, gentlemen. If we have a blast on target, downtown Portland, it'll be hours and probably days before we can get back in.
Engineering, Gordon Burt.
Have reports 80% of the city-owned public utility equipment has been successfully evacuated from the city. However, there is one group of electric company trucks caught on the west side. We're working now on a plan to get them out.
Fire Department, Chief Simpson.
Fire Department's initial dispersal plan is in effect. Several units have already moved out to their respective dispersal points. Engine 24 and Engine 30 are currently fighting a residential fire, and they will stay on the job until this fire has been controlled.
Police, Chief Hillbrunner.
After police activities, the city is about 65% evacuated. Traffic appears to be moving at about 15 miles an hour outbound. The state and county police have set up an effective roadblock diverting inbound traffic, thus enabling us to use all lanes for outbound traffic.
Emergency Medical, Dr. Metter.
City hospitals are continuing to evacuate. Emergency hospital units are functioning in Forest Grove, Mount Airy. Others should be heard from soon. You might be interested in knowing that en route, one boy and twins were born.
Russ Lang, Welfare.
As the reports continue, it is obvious that the Portland plan is working smoothly. Only 7 years earlier, Portland had no civil defense. It was then that the idea that civil defense was not to be separated from normal government evolved. And in 1952, a 1 mil tax levy to finance the plan was put on the ballot by unanimous decision of the City Council. After civil defense leaders went out and campaigned, the people voted to tax themselves, to protect themselves. And later, the city charter was amended to assure continuity of government, so that in an emergency like this, should the executive branch become casualties, they would automatically be replaced by a legally established line of succession of other experienced city officials. The people, as now and after the emergency, are assured of continuity of their government.
Schools report complete evacuation. There's no panic among the children. They've rehearsed this before. Reports from industries indicate approximately 90% evacuation. I think we're doing quite well.
And so, at 1:25, with some 22 minutes till 0 hour, Portland seems to be doing quite well. Should a bomb fall now, city officials and city services will be able to carry on. And meantime, vital messages are passed on to maintain contact with state and county headquarters.
Okay. W7SAA from W7BS.
Upstairs in this unique underground operations center, an emergency telephone system is functioning as the details of evacuation are reported and relayed. Part of the civil defense levy went to a comprehensive microfilming project supervised by Will Gibson, city auditor. More than 3 million documents and records that go back to the first handwritten city council minutes in 1851 have been microfilmed. Duplicates of laws and the engineering records without which the city cannot function out here. And so, in time of disaster, the records are preserved. And now, with a moment to breathe, some can take time for coffee in a built-in cafeteria. This time, talk with families which have been evacuated. It is time to be alone, to think of the future. And there's even time for those who need it now to rest. 300 can live here for a week, eat, sleep, and breathe. The operations center has its own water supply, its own electric power, even its own purified air. At 1:30, on this day called X, the air outside is strange and silent. Almost all its people have gone. And at 1:32, as directed by the mayor, the siren sounds once more. Take cover. The evacuation is stopped, and there is nothing to do but wait. Back in the operations center, the day called X reaches its climax.
Time now, 1:47. Enemy bombers are probably overhead.
What happened after that moment, we leave you to contemplate. But one thing is certain, Portland has a plan for the survival of its people and the continuity of its government. You know, actually, the survival of this entire nation depends upon the ability of federal, state, and local governments to carry out their responsibilities in the event of a massive nuclear attack. Each new scientific development in the weapons of war presents a new challenge. The people of Portland, through working together, they're ready. If there really were a day called X. How about like you.
This is a radiological defense operations room, a nerve center for survival, which we hope we will never have to use. But since war could come, this room is ready, and so are others throughout the country.
Greatest. Louisville, 742, I think. Fire Records Fund producer.
The USA, almost 3.5 million square miles. And at the other end of our scale of size, tiny dust-like particles. They too have a name. And the name is fallout, radioactive fallout. A large-scale nuclear attack on the United States could produce a patchwork pattern of fallout covering 2/3 of the nation. More than 2 million square miles in a single day. In this 2 million square miles, more than 100 million people living well beyond the destructive range of blast and heat could be subjected to dangerous or deadly amounts of radiation from fallout. Carried upward 15 miles or more by the mushroom cloud, spread laterally by shifting winds at all altitudes, fallout from a single thermonuclear blast could severely contaminate a 60-mile strip downwind from ground zero. 1,200 square miles within an hour of explosion. 4,000 square miles in 6 hours. All of us, even in small towns and on farms, live within fallout range of a likely target. Furthermore, since these targets are often only a few hundred miles apart, fallout patterns can overlap, intensifying the danger. How do we know all this? From practical experience.
A thermonuclear test in the Pacific in 1954 produced a highly contaminated area 20 miles upwind and 220 miles downwind, with a variable width up to 40 miles, large enough to reach from Washington, D.C. to New York City, along the densely populated eastern seaboard. In this 7,000 square mile area, there would be enough radioactivity to threaten seriously the lives of all who failed to take shelter before fallout arrived. Let's look at it in another way. Let's assume that industrial St. Louis were hit by a weapon with the explosive equivalent of millions of tons of TNT. Depending on winds, fallout could extend 40 miles into southwest Illinois in an hour, to Terre Haute, Indiana, 150 miles to the east in 7 hours, and to Wheeling, West Virginia, another 325 miles within 24 hours. Total drift, more than 500 miles. Civil defense tests have brought the problem into sharp focus. In one exercise, an imaginary force of 500 bombers severely damaged this country's key industries. Yet effects from fallout pose a more serious threat to the nation's survival than did the devastating but more localized effects of blast and heat. Let's examine some of the problems. Although most sources of water are located well outside of big cities, the wide drift of fallout could cause serious contamination of our surface water supplies. Fallout from a nuclear attack could gravely affect the nation's agriculture. Food supplies in fields or in open storage could become dangerously contaminated. Possibly they could be recovered for later use. But what about future harvests? They too could be dangerous if grown in seriously contaminated soil. Cattle, horses, and sheep might have to be kept out of pastures for a long time. In short, fallout from nuclear attack would threaten us with thirst and famine, as well as with sickness and death from direct radiation. That is why our survival as a nation can depend on how well we prepare to defend ourselves against radioactive fallout. And there is a defense against fallout. Before we examine our radiological defense programs, let's take a look at the basis of the problem. As every youngster learns today, there is nothing new or mysterious about radiation. A Roentgen, which we call an R, is a standard unit for measuring radiation. In an average lifetime, a human being is exposed to perhaps a dozen Roentgens. This exposure comes from natural radioactive elements in the Earth and cosmic rays from outer space. The human body withstands continued exposure to small radiation doses. It is when the rate of delivery is high, or the total dose in a short period is large, that recovery cannot keep pace with damage. Exposure of the whole body in a short time to 600 or more Roentgens of radiation will almost certainly be fatal. People receiving 200 Roentgens or more in a short period of time will get radiation sickness. Those receiving 600 or more in a short period of time will die. For your protection, shelter is the answer, since highly dangerous doses can be produced by fallout radiation. This is what happens.
3, 2, 1.
About 85% of a nuclear weapon's energy results in light, heat, and blast. 90% of the released energy is radiation. This is of two types. The first, initial radiation, is emitted from the fireball shortly after detonation. Since for large weapons it generally does not spread beyond the blast area, initial radiation is of minor concern in the overall problem of radiological defense. It is the second type, residual radiation, that creates the fallout problem. Its production can be described simply. When countless billions of atoms in a large megaton weapon are blasted apart, hundreds of pounds of highly radioactive material are produced. When such a bomb bursts at or near the ground, tens of thousands of tons of earth and debris are carried as high as 15 miles in the mushroom cloud. This tremendous cloud becomes a floating carrier, which drops tiny radioactive particles back to Earth. Where these particles land depends on a combination of three factors. One, their shape and size. Even the largest may be no bigger than a single grain of sand. Two, the height to which the radioactive cloud rises. And three, the direction and speed of winds at various altitudes. Fallout deposit resulting from the combined effects of these conditions is generally divided into three categories: close in, intermediate, and delayed. Close-in fallout usually settles within a few hundred miles of the burst and reaches the ground within 10 to 20 hours. It is made up of the heavier particles in the cloud. Intermediate fallout descends within a few weeks of a detonation. Since the particles are small, they remain in the air for weeks, covering many thousands of square miles. Sometimes they are driven to Earth by rain or snow. Delayed fallout is composed of very small particles that may drift completely around the Earth several times and may not descend for months or years. Radiological defense personnel, RADEF personnel for short, are primarily concerned with close-in fallout.
As you can see, close-in fallout is a real problem in radiological defense. And the problem becomes even more complicated because the speed, range, and direction of fallout depend upon ever-changing wind and weather conditions. Large particles fall fast and land relatively near ground zero. Smaller particles fall slowly, land further away. Winds, which vary at all altitudes and seasons, affect the pattern of these deposits. With winds variable at different altitudes, the spread of fallout will result in the effects of all winds acting upon it. For this reason, radiological defense officers cannot use surface wind direction alone as a basis for forecasting fallout. Radioactive materials decay with time. You might say they cool down. After all fallout is down and radiation has been measured, knowledge of decay rates permit estimates of how hot it will be days and weeks later. With this information, civil defense can estimate when it will be safe to evacuate or to leave shelter. Remember this rule of thumb. There is a 10-fold decrease in radiation rate for every 7-fold increase in time after detonation. For example, a level of 1,000 R per hour at 1 hour after the explosion would be reduced to 100 R per hour 7 hours following the explosion. At 7 times 7 hours, or in 2 days, the level would be down to 10 R per hour. At 7 times 49 hours, or at the end of 2 weeks, the level would be reduced to only 1 R per hour. But remember, until decay reduces radiation to tolerable levels, there are only 2 safeguards against it: distance, that is evacuation of safe areas, or mass, shelters. Underground shelters covered by at least 3 feet of earth, or basement shelters, the types recommended by Civil Defense, will give substantial protection. This is why we believe that most people who live beyond the areas destroyed by blast and heat can survive fallout if they will follow Civil Defense instructions.
As serious as fallout is, we can cope with it through action as individuals and through an effective radiological defense program. An active program carried on by federal, state, and local governments. At the federal level, representatives of many agencies meet regularly to perfect methods of collecting and analyzing fallout information and to find the best means of advising our states and communities about fallout conditions after a nuclear attack. An important part of the radiological defense program is a series of monitoring networks stretching across the country. A combined system of federal, state, and local stations, thousands in all, which will gather information on radiation levels as soon as fallout begins to spread downwind. On the basis of this information, transmitted by top priority communications of every type from coast to coast, early, effective action for our protection would begin at state and local level. In some cases, evacuation. In most cases, shelter. The federal monitoring network at Weather Bureau stations, Federal Aviation Agency sites, Department of Defense Air Weather Service units, and other government organizations operates on a round-the-clock basis. At every level of government, radiological defense units are being equipped and trained to act. Fallout forecasts, issued several times daily by Weather Bureau stations, will be useful in estimating local fallout areas if we are attacked. Certain stations gather weather information that is processed to give an estimate of the areas in the nation where fallout could be expected. Sent over a vast teletype network to civil defense and other offices throughout the nation, the coded information is charted on maps to show sections threatened by fallout. Lines on the map show where and when the fallout is likely to arrive. At all civil defense regional offices, radiological defense personnel help state RADF staff in their regions. Regional officers arrange for the distribution of training kits, supervise the contribution of federal funds to state RADF work, set up RADF training in their regions, and coordinate RADF activities of all federal agencies in the region. After an attack, the regional RADF staff will collect, analyze, and evaluate all fallout information received from the state, and will coordinate the flow of information to and from federal and state control points. The state RADF people will use both ground and aerial monitoring units to make broad, statewide surveys. Highway systems and key transportation routes, major industrial and supply sites, as well as urban and rural areas, will will be checked as rapidly as personnel safety permits. The state RADF unit also maintains working maps. It plots and correlates data, analyzes reports. By transmitting its summaries, it links regional and local offices. But it is at the local government level that radiological defense will be on an immediate, down-to-earth basis. Local RADF will perfect and test detailed plans for operations. Keep all equipment in readiness condition. Train and rehearse operating crews so they too will be ready. It will set up communications between its units and for liaison with state RADF organizations. When an attack warning sounds, local survival plans go into effect. Monitors will report to their stations. The public will be advised to take shelter or evacuate. After attack, first reports of radiation measurements will come from sheltered monitoring stations. As soon as radiation levels permit, police, firemen, highway maintenance men, conservation officers, everyone trained to use survey meters will begin the vital work of getting detailed data to control centers. From this information, current situation reports will be prepared. Using these reports, RADF officers can answer urgent questions raised by local authorities. Can short survival missions be undertaken? Is our water safe? What roads are safe? Are feed, livestock, and crops contaminated? When can emergency teams begin decontaminating and reclaiming property? When will radiation die down enough to make it safe for people to leave shelters for brief periods and for utilities to be put back into service? Survival of whole communities can depend on the accuracy of answers given to these questions. Local RADF plans also cover places where people work. Employers must shoulder their responsibilities by providing fallout shelters for workers. At work and at home, everyone must understand the hazards of fallout and the value of shelter. Every family must provide for its own survival for at least 2 weeks. Since radiation levels outside would often be deadly, fallout shelters will protect the most people. Both the underground and indoor basement shelters recommended by Civil Defense can be very effective. They must be stocked with a 2-week supply of food and water. First aid supplies, flashlights, and a battery radio with Commonwealth frequencies 640 and 1240 clearly marked on the dial should be included. Factories, offices, apartment houses, and schools all must provide shelter. Remember, too, that personal decontamination is important. Fallout particles can be brushed from clothing and washed from skin. All in all, a big program. Some of it in being, some under development. But it takes action to fulfill this program. Radiological defense training is being expanded. First priority, train more instructors. At 3 national centers, in classrooms, on calibration ranges, learning theory and practice, more than 2,000 adult students each year are taking basic or advanced courses. Courses that will qualify them to instruct classes back home. A total of 600,000 monitors must be trained to make radiological defense effective in every community. To support this program, radiation survey meters are being distributed widely. These instruments, which measure radiation levels in terms of Roentgens or milliroentgens per hour, are the backbone of radiological defense. In addition to survey meters, dosimeters, instruments which measure total doses of radiation, are being distributed to the state and federal agencies. Radiological defense instrument kits for use in science classes are being distributed to 15,000 high schools throughout the nation. With the aid of this equipment, our young people will acquire a better understanding of radiation and will be better prepared to contribute to the nation's radar effort. Improved radiation measuring instruments and multiple-purpose computers are being designed, built, and tested. An intensive public education program to tell the American people about radioactive fallout and shelter is underway. For it is an informed public that will mean the difference between success and failure in meeting this threat. Informed people in homes and factories and offices must know their personal responsibilities for shelter and protection. Informed officials at all levels of government, from Washington, D.C. to the smallest town council, must understand the RADEF program and help make it work if the people of a nation are to survive.
RADEF, Charleston, West Virginia, 2830 check.
Our efforts now to build a workable radiological defense will pay off richly by helping to deter aggression and by saving countless lives if nuclear attacks should come.
This film is concerned with the effects of high-altitude nuclear explosions on radars, optical sensors, and communications. To understand how nuclear explosions affect such systems, it is first necessary to understand the interaction of explosions with the atmosphere. We will discuss this interaction or phenomenology for explosions at very high altitudes in the ionosphere and in the upper atmosphere. We shall not consider the blast and other lethal effects that nuclear explosions produce. The air we breathe consists almost exclusively of gases and are electrically neutral in their ordinary condition. The number of electrons shown here is of course symbolic rather than literal. As we progress towards the top of the atmosphere, however, the gases are exposed to powerful X-ray, gamma ray, and ultraviolet radiation from the sun and from cosmic rays. Above about 90 kilometers, radiation increasingly breaks more of the molecular gases into their atomic or single atom state. This dissociation, primarily from the ultraviolet radiation,
affects as much as 50% of all molecules at altitudes of about 100 kilometers. The cosmic and particle radiation also causes ionization. Detachment of the single electron leaves the remainder of the atom or the molecule with a positive charge. This can happen to single atoms or to either one of the atoms of a molecular pair. Being electrically charged, free electrons are attracted to and tend to recombine with positive ions at the first opportunity, thus again creating electrically neutral units. If an electron does not recombine with a positive ion, it can be taken out of circulation by temporary attachment to a neutral atom or molecule, which then has a negative charge until the electron is snatched away by the stronger attraction of some positive ion. Because of the strong recombination tendency, ionized gases will not remain in that condition unless there is a constant supply of energy to cause new ionization as fast as the previous ions can recombine. The first significant quantities of naturally occurring free electrons begin to show up at an altitude of approximately 60 kilometers, which we therefore consider as the bottom of the ionosphere. From there on up to heights of several hundred kilometers, free electrons become more and more prevalent. Their rate of increase with altitude is non-uniform, and there are several clearly defined regions which exhibit distinctive electromagnetic characteristics. The first region is the D region, frequently called the D layer, between 60 and 90 kilometers above the Earth. Centered at roughly 120 kilometers is the E region. At 200 kilometers, the F1 region. And finally, at some 300 kilometers, the F2 region. In the relatively dense atmosphere of the D region, there are sufficient numbers of diatomic positive ions that no free electron can exist for long without either combining with one of these ions or becoming attached to a neutral particle. There is no solar radiation to produce a resupply of new ions in the Earth's shadowed or night regions. However, cosmic radiation provides a source of ionization both during the day and at night. Nevertheless, the absence of solar radiation at night allows recombination to proceed more rapidly than ionization, and the free electron density is reduced compared to that during the day. Up in the F region, however, the extremely rarefied atmosphere allows a large free electron density to exist throughout the night. Shortly after sunrise of the following day, the D region ionization, consisting mostly of electrons, is reestablished by solar radiation. We are concentrating attention on atmospheric ionization processes because the free electron density at the various altitudes determines the signal propagation behavior of many of our radar and long-range communication systems. Now, in what way do high-altitude nuclear explosions affect these free electron densities? To begin with, roughly 70% of the total energy produced in a nuclear explosion is emitted in less than a microsecond as a flash of X radiation. A few percent more of the bomb energy is emitted as prompt gamma and neutron radiation. Most of the remaining energy appears as directed motion or kinetic energy of the expanding explosion debris. Delayed gamma and beta radiation from this radioactive debris material emits some 5% of the total weapon energy over a longer period of time. We will examine the effects on the atmosphere of nuclear detonations at 50 kilometers, 100 kilometers, and 250 kilometers altitude. First, let us consider the events that follow the detonation of a sub-megaton weapon at a moderate altitude of 40 to 50 kilometers. Most of the X-ray energy is deposited near the burst point, heating air to incandescence. The prompt gamma and neutron radiations from the explosion can, on the average, travel large distances before colliding with air particles. Therefore, the ionization caused by such collisions is spread out laterally over a region several hundred kilometers in diameter. Radiation in an upward direction increases the D-layer ionization, which we symbolize with the blue shading. It is important to realize that the greatest range of these radiations will be upward and horizontal, because the exponential nature of our atmosphere causes its density and absorbing qualities to decrease very rapidly in upward directions. Specifically, each 15 kilometers change in altitude in either direction will make about a 10-to-1 change in air density. At 45 kilometers altitude, the density is approximately 1,000th of the air density at sea level. Coming back to our explosion, the X-rays heat the surrounding air to incandescence. Within a tenth of a second, tremendous radiant energy output and gas expansion processes have created a fireball of superheated air several kilometers in diameter. Inside the fireball, both the air and the smaller central mass of expanding weapon debris are fully dissociated from the molecular into the atomic state, and the atoms themselves are highly ionized. In another view, a high-velocity shock wave is seen to race outward from the radiation front, which is still at a temperature on the order of 10,000 degrees. The fireball expands at a slower rate to a diameter of 10 kilometers within about 5 seconds, during which time it also begins rising upward at a rate approaching 300 meters per second due to the buoyancy of its heated low-density gases. We watch the remainder of the explosion development through a camera located directly underneath the fireball. Sometime during the first minute, the rising cloud of fireball and debris material from explosions at this or lower altitudes interacts with the surrounding air, and the fireball transforms into a torus or donut shape. Both gammas and high-energy electrons or beta rays are continuously emitted from fission fragments in the debris. The cooling fireball and debris mixture, no longer luminous, continues to rise and expand, reaching a diameter of about 40 kilometers at 1 minute. It finally stabilizes some minutes later at an altitude of about 100 kilometers until dissipated by atmospheric winds. We will next consider a nuclear explosion of large yield at an altitude of 100 kilometers, where the atmosphere is less than 1,000, as dense as it was at 50 kilometers. The initial heavily ionized X-ray fireball will be an order of magnitude larger than from our low altitude shot, and much more tenuous and less brilliant in appearance, because so much of the X radiation escapes to large distances, over which it causes a significant ionization increase without luminosity. The atmosphere is so rarefied that the highly penetrating prompt gamma and neutron radiation from the explosion will produce only negligible concentrations of new ions in horizontal and upward directions. Ions are produced in the D layer and at lower altitudes. The hot and rapidly expanding fireball rises ballistically with something over 5 times the average velocity seen for the lower shot. Its diameter is some 300 kilometers after the first minute. Magnetic forces progressively distort the rising material, elongated along the geomagnetic field lines. Maximum altitude on the order of 1,000 kilometers is reached in 7 or 8 minutes. With the upward ballistic impulse exhausted, the material being heavier than the ambient atmosphere tends to fall back to denser regions on the order 150 to 200 kilometers. The fall is oriented primarily along the Earth's geomagnetic field lines. The diameter is several hundred kilometers with a thickness perhaps a tenth as great. The diffuse radioactive debris continues emitting both gamma and beta radiation with significant intensity for many hours after the explosion, thereby continuing to produce ionization. Most of the ionization from gamma radiation occurs at altitudes near 30 kilometers. However, ion lifetimes are very short down in such relatively dense air. Reattachment is so rapid that we actually find the greatest net population of gamma-produced free electrons up at the D-layer altitudes, where the reattachment rate is much lower. The other major radiation from the debris, the super high-velocity electrons from fission fragment decay, referred to as betas, are less penetrating than the gamma rays. Most of the downward-directed betas dissipate their energies in the D region at 60 to 80 kilometers, adding to total ionization in that region primarily by collision with neutral particles. The area of the ionization region created by beta radiation will correspond roughly in size to the area of the stabilized debris material itself. Actually, being electrically charged, the beta particles are constrained to follow the Earth's geomagnetic field lines. Thus, a region of ionization commonly called the beta patch is caused by these downward traveling electrons. The few beta particles that start out parallel to the field line will continue to follow them. If the particles encounter the field lines at an angle, however, they will spiral around them. Here we see beta particles streaming along the magnetic field through the fireball and debris of a burst. Those electrons ejected upward may be trapped along the Earth's magnetic field lines and are mirrored back and forth if the reversal or mirror point is substantially clear of the atmosphere. If the mirror points are too low, the electron will dip into the atmosphere at each end of its shuttle, soon will be lost by collision with air molecules. This collision excitation mechanism is generally accepted as one of the causes of auroral displays. Thus, a nuclear burst at sufficiently high altitudes can produce auroras at conjugate points in both hemispheres. Since the debris from a nuclear detonation begins radiating at the moment of the explosion, its conjugate point auroral effects can be expected to change location as the debris rises and intersects with successively higher magnetic field lines. Note that when the debris is located below about 200 kilometers, most of the electrons shuttling along the field lines will be lost in the atmosphere on their first pass, with very little mirroring back to the other conjugate point. We will next consider a nuclear explosion at altitudes above 250 kilometers. Mass asymmetries in the construction of the nuclear device and its carrier can be very important and are observable in this 400-kilometer explosion. At this very high altitude, a substantial change occurs in the mechanism of containment, the forces which slow and finally stop fireball and debris expansion. While ordinary hydrodynamic pressure resists the explosion expansion at low altitudes, geomagnetic back pressure becomes increasingly important at altitudes above 100 kilometers. The heavily ionized debris and gases in an expanding fireball are electrically conducting, so the Earth's magnetic field tends to be excluded from that region, creating a so-called magnetic bubble which presses back against the expanding gases. At great altitudes where air pressure is negligible, expansion might continue indefinitely if it were not for a collisionless process in the debris and surrounding air plasmas, which permits a degree of coupling between the weapon debris and the ambient atmosphere. The degree and nature of the coupling are believed to be very dependent on yield and burst altitude, but these processes remain major unknowns in the phenomenology of very high altitude nuclear explosions. Looking back again at another weapon effect on the atmosphere, most of the prompt gamma radiation is deposited between 25 and 30 kilometers altitude. The air molecules are ionized. The free electrons split off and start spiraling around the magnetic field lines. Each spiraling electron emits minute radio waves. All of the electrons exist nearly simultaneously, and the minute radio waves add together. This is the primary source of the high-altitude electromagnetic pulse, or EMP, which is a broadband pulse of radio frequency energy radiated from the deposition region. When this electromagnetic pulse is coupled into a system, very large voltages and currents may be induced. Other EMP generating mechanisms are operative in other burst regimes, but are outside the scope of this film and will not be described. In brief summary of the important effects on the ionosphere, we see that a nuclear burst in the 40 to 50 kilometer region produces first a heavily ionized fireball area, while the flash of prompt gamma and neutron radiation causes significant ionization lasting for several minutes and extending to large distances horizontally and upward, but with only minor range and duration in downward directions. Debris radiation continues to create intense ionization in the region of the fireball while it rises. At all explosion altitudes substantially above 50 kilometers, the immediate radiation produces almost completely ionized fireball regions of multi-kilometer dimension. Its strong but radially decreasing ionization extends to many hundred kilometers. The fireball and debris materials rise to maximum heights of from 100 to 1,000 kilometers as the first height is raised from 50 kilometers to the 100-kilometer region. Unlike debris from the lower explosions, material from the higher explosions falls back from its maximum altitude, ultimately settling around 200 kilometers. With rising burst altitude, greater quantities of beta particles and charged debris particles will shuttle north and south along the magnetic field lines to conjugate points in both hemispheres. Both beta ray and debris interaction with the atmosphere at those points will, for a number of hours, create significant ionization with vivid auroral effects and radio disturbances. Debris gamma and beta radiation will also enhance ionization in the D region at both conjugate points. Other phenomena associated with irregular structure in nuclear burst ionized regions are also important to communications, infrared, and radar systems. One is the eventual development of magnetic field-aligned filaments, or stria, in ionized regions. Irregular ionized structure also results from the upwelling or heave of explosion-heated air above 100 kilometers altitude. These phenomena are treated in greater detail in Part 2 of this film, which considers the effects of atmospheric ionization on military systems.
Davy, as President of the Royal Society, presented Mr. John Dalton with a royal mission in the development of the theory of definite importance, usually called the atomic theory of chemistry. This presentation set an official seal upon the emergence of the scientific theory of an idea of matter which had existed for over 2,000 years as a belief, unsupported by experimental proof. In Dalton's time, chemistry was becoming an exact science, thanks to accurate methods of weighing and analysis introduced in the 18th century. Dalton was able to work out fairly accurately the relative combining weights of many elements. In his new system of chemical philosophy, published in 1808, Dalton pointed out that these combining weights, which are constant for each particular compound, must be related to the weight of the ultimate particle or atom of the combining element. Thus, the atomic theory was reborn. According to Dalton, matter is composed of small particles which cannot be split up any smaller. These particles he called atoms. Our diagram illustrates his idea, but not, of course, the real case correct. He believes, secondly, that all atoms of one element are exactly alike, and differ from the atoms of other elements, and have a characteristic relative weight. Thirdly, he believes that atoms are indestructible, and cannot be created. Fourthly, that chemical combination occurs between small whole numbers of atoms. Such combinations of atoms are now called molecules. In any given compound, all molecules are alike. Dalton invented a system of symbols to represent the atoms of the different elements. He used these to show how the atoms combine to form molecules. Though some of his conclusions proved wrong, atomic theory was the foundation upon which the chemistry of the 19th century was built. Painstaking chemical analysis based on Dalton's theory and research arising out of Avogadro's hypothesis concerning molecules and gases enabled accurate atomic weights to be assigned to the elements. A connection was sought between atomic weight and chemical properties, and in 1869 this was supplied by Mendeleev's periodic table, which arranged all the elements then known in symbols according to their atomic weights and properties. Thus, the column headed by carbon contains a group of elements with dissimilar properties. The next column contains another group of similar elements, and so on. Now, from left to right, the elements are arranged in ascending order of atomic weight. The whole table fits together like a structure. The properties and place in the table of unknown elements were predicted, and the discoveries of later years proved the accuracy of these forecasts. The decomposition of solutions by an electric current was used as a means of chemical analysis in the early 19th century. By careful measurements, Michael Faraday was able to show that in such cases, a definite quantity of electricity was associated with definite amounts of the elements produced at the electrode, that is, with definite numbers of atoms. Hence, he suspected that electrons there were two kinds of electricity. Unlike charges attracted each other. Like charges repelled each other. By convention, these two kinds of electric charge became known as positive and negative. In a solution like common salt and water, the sodium chloride exists as ions or charged atoms of sodium and chlorine. When the solution is electrolyzed, the positive sodium ions travel towards the cathode and the negative chlorine ions to the anode. The work of many scientists on liquids and gases led to the theory that in all matter, molecules are in a state of perpetual motion. The botanist Robert Brown was the first to see in his microscope what is now called Brownian motion. This is the intricate motion imparted to fine particles in suspension in liquid by the impact of molecules. One can imagine a tiny particle being pushed about by these intricately active molecules. Each molecule is so small that 27 million are contained in one cc of gas at 0 degrees centigrade and normal pressure. The thinnest soap bubble that can be made by water in an instant is about 100,000 of an centimeter thick. In this space, about 1,000 molecules could lie side by side. Each of these molecules will be 3 or 4 times the size of a small atom. This much was known at the close of the 19th century, which Lord Lulliford sums up in these words.
At the close of the 19th century, the labours of the chemists had resolved the matter of our material world into 80 or more distinct elements, and the atoms of these elements appeared to be permanent and indestructible by the forces then paramount.
Physicists of the 19th century were not less active than the chemists. Faraday investigated the conduction of electricity by liquids. Later scientists investigated the passage of electric current through gases at low pressures with this kind of apparatus. Air is pumped from the tube until a luminous discharge passes from cathode to anode. As evacuation proceeds, brilliant rays are seen streaming from the cathode. The rays become invisible as pressure is reduced, but they still cause a faint green glow on the walls of the tube. This bell-shaped bezel shows the behavior of the cathode rays more clearly. At first, the current passes from the cathode to the edge of the fluorescent screen beneath it. Next, the glow of the cathode rays is clearly seen around the cathode itself. As the pressure continues to fall, the rays will disappear, but their presence is revealed by a powerful green glow when they strike the fluorescent screen. These cathode rays can be made to cast a shadow of an object in their path. This proves that they travel in straight lines from the cathode. The rays are capable of transmitting energy. The little veins in this tube are turned by angelic light motion of the tiny particles rushing up from the glowing cathode beneath. It can be proved that the rays are negatively charged. A wire connected to a plate on which the rays fall will discharge a positively charged electrode. In 1897, Sir J.J. Thomson devised an apparatus to measure the ratio of charge to mass of these particles, which had been named electrons. He was able to make an estimate of the actual mass of the electron. In this apparatus, a luminous spot showed where the electron beam from the cathode fell on a fluorescent coating on the end of the tube. This beam could be deflected in one direction by an electrostatic field between charged objects, and in the other direction by a magnetic field. These fields could be adjusted to balance each other, and from their strength, the velocity of the particles could be calculated. Then, from the strength of the magnetic field alone, and the deflection caused by it, the ratio of charge to mass could be found. From experiments such as these, the mass of the electron has been estimated as 1/1840th of the mass of the hydrogen atom. Sir J.J. Thomson's own description of this tiny object has been preserved for us.
Could anything at first sight seem more impractical than a body which could only exist in vessels from which all but a minute fraction of the air has been extracted, which is so small that its mass is an insignificant fraction of the mass of an atom of hydrogen, which itself is so small that a cloud of these atoms, equal in number to the population of the whole world, would be too small to have been detected by any means then known to science.
Thus the existence of a negatively charged subatomic particle, the electron, was established beyond all doubt. It was even found possible to photograph the track of the electron. This was done by an ingenious apparatus invented by Professor C.T.R. Wilson. During the war, most people saw the favorite trails left by high-flying aircraft. Wilson, while investigating the ionization of gases by charged particles, built a chamber in which such particles could be made to leave a vapor trail. It consisted of a glass-filled chamber filled with moist air. The bottom of the chamber is really a piston's head, supported by the air beneath. Connected by a valve to the main apparatus is a large vacuum chamber. When the valve is open, the air beneath the piston is sucked into the vacuum, and the piston drops sharply, creating an expansion of the moist air so that a cloud is formed. Now a charged particle from a source of radiation entering the chamber will ionize the gas along its path. Because of the sudden expansion, drops of moisture will condense on the charged atoms or ions along the path of the radiation and leave a visible trail. This is photographed by a synchronized electric flash. This apparatus, much improved since the original model, has proved invaluable in atomic research. Today, the electron is a commonplace. Any metal raised to red heat gives off electrons. The stream of electrons from this hot filament can discharge an electroscope. This is made use of in the radio valve, where the electrons from the hot filament can be used to send and detect signals broadcast over long distances. On this radar screen, electrons act as the eyes of a ship as it makes its way down the crowded river to the sea. And on the television screen, electrons paint pictures for our amusement.
The electron owes its practical utility to its small. Like the Faraday Shakespeare, say my use is great because I am so small.
The discovery of electrons raised big problems. Ordinary matter is neutral. For instance, it has no effect on the electron. Yet the method in this field produce the deflection of the beam horizontally. Similarly, an electrostatic field produced a vertical deflection. In both cases, the different velocities of individual particles produced a line instead of a spot. If both fields were applied simultaneously, the particles fell off the plate in a parabola. The position of this parabola in relation to that of the undeflected spot was determined only by the ratio of mass to charge. Thomson was able to calculate the mass. He found that each particular type of positive ray consisted of charged atoms of the gas present in the discharged tube. Under certain conditions, the different types of flow due to positive and cathode rays can both be seen. These phenomena could only be explained by supposing that the neutral atom contains both positive and negative charges in equilibrium. The stream of electrons from the cathode detaches other electrons from the atoms of the gas through which they pass. These atoms immediately become positively charged and rush towards the cathode. If the cathode is pierced, they emerge as positive rays. The sequence of events resembles electrolysis, and these charged atoms of gas are called ions. A gas in which such conditions arise is said to be ionized. In 1896, Weston found that the green glow excited by cathode rays striking the glass was itself giving off rays which caused the fluorescent screen to become luminous. The rays could penetrate like metal, but not penetrate like lead. The centerpiece metal here is lead. The outer ones are aluminum. Lead stops the rays completely, but the lighter ones are penetrated, cast a lighter shadow. These powerful rays became known as X-rays, and doctors soon found that they could use shadowgraphs made with X-rays to see inside the human body. Dentists were able to study the internal structure of teeth. And industrial X-ray machines such as this one have been developed to search for hidden defects. This
3 years after the discovery of radioactivity by Hitler, Russia inserted a radioactive gas ozone in a thin-walled glass tube which was surrounded by an outer tube from which all the air had been absorbed. The alpha rays coming from the gas penetrated the thin glass and collected in the outer tube. After a few hours it was found that the outer tube contained gas helium. Therefore, the alpha particles were acid helium. And this was the first direct evidence of one kind of gas actually changing into another.
A great change in our ideas resulted from the discovery of the electron and of the spontaneous radioactivity observed in the heavy elements, uranium and thorium. Bobby and I were able to show in 1903 that radioactivity was the sign and nature of the universal element, and that the atoms of uranium and thorium were undergoing a series of spontaneous transitions. I suggested in 1911 has proved very useful for this purpose.
Alpha particles radiated limited by a with various image sharply amongst the earth and the heat. The existence of the atomic nucleus has been proved. The next thing was to find out the magnitude of the charge on it. See how this was done? Shown here for X-ray. We have already seen how X-rays are caused or possible substance. X-ray tube. Target on which the tube curls. Causing X-ray signal communication.
To effect a veritable transformation of an atom, it was necessary to change the charge or mass of the nucleus or something else. Now, minute nuclei are held together by half and to effect their difference, it seems likely that a very concentration short particles of another nuclei in the individual atom. The bombardment of the nuclei by the energetic alpha particles of radium appears to be the most promising method for phototherapy.
In 1919, Rutherford found much of the nuclei could be formed by bombardment with alpha particles, and the protons were ejected at high speed as a result. In effect, he added together helium and nitrogen and changed them into oxygen and hydrogen. This was transmutation, the greening of the alpha, which the nuclear theory had at last discovered. Most significant of all, there could be no doubt that the proton, the hydrogen nucleus, was a fundamental particle in all atoms, a positive particle of the negative electron. Now the atom goes out to the space. Let us go back to our table of the elements. one and a massive one. But the atomic wasteland is still a problem. So the nucleus will have 4 more protons and it will create a big Now we have updated the balance of charge. 7 protons, 7 positive charges. 3 electrons, 3 negative charges. There is only one way to correct this. 4 electrons must be added. Now our charge is balanced. The negative charge, 3 electrons, is balanced by the outstanding positive charge, 3 on the nucleus. Such was it, yes. But even in 1920, Rutherford suggested that there might be a neutral particle of the same mass as a proton, which could account for the extra mass without affecting the charge. Ultimately, this proved to be another instance of his amazing principle. But in the years between, the drive to penetrate the secrets of the nucleus continued unabated. Inside the glass case is a single wire which serves as an electrode. Suppose that a radioactive source was emitting alpha particles. Then, each wire is the output. The ionization caused by the alpha particles is corrected, substituting a current to the central wire. If the alpha particle emitted ionizes the anionic spark on positive and negative ions. Actually about 100 pounds per part. These are fully charged with positive electrons, in the same way as the ions in solution being electrolyzed. The tiny charge collecting on the central wire as a result of continuous alpha particle emission can be measured. Development of radio valves enabled the pulsive current from each single alpha particle entering the chamber through a micro window to be amplified until it could operate a kind of counter. Then Geiger and Miller developed an ionization chamber which could multiply the original effect by a principle known as gas amplification. There is a modern Geiger counter capable of counting at the rate of thousands per minute. Linked to it is an electric counter capable of high-speed recording. As the tiny strip of radium fitted to this rod is brought near the tube, the dials will cause the gamma rays from the disintegration of single atomic nuclei. These gamma rays are actually penetrating the walls of the tube. The charged particles can be counted by using a suitable type of tube. The ionization effect can be amplified and passed through a loudspeaker, so that each effect represents the package of a single particle, or as in this case, the ionization caused by a single gamma ray. The same voltage will operate on a oscilloscope in which cathode rays trace on the speed, the effect of these nuclear explosions. allowed to pass through an electric stream, which deflected the particles at varying angles according to their velocity. All the particles of the same mass could be brought to a common focus on the surface of the sphere by means of a magnetic field of the right shape and intensity. In effect, estimates of wave atomic nuclei is very difficult. Work done with this apparatus shows that most of the elements detected as individual particles were actually mixtures of two or more substances of different atomic weights. The atomic weight of the elements have been very accurately determined by many chemists. Very few options have been expressed in simple numbers. Hansen showed that chlorine, with its atomic weight of 35.5, is in reality a mixture in a definite proportion of two forms of the same element. One with an atomic weight of 35, and one with an atomic weight of 37. Such different forms of the same element were called elements, and subsequent research has shown the number of elements of which isotopes exist is very large indeed. Little by little, hundreds of experiments all over the world built up the store of knowledge about atomic nuclei. As time went by, experimental evidence and theory both emphasized the increasing possibility that there did exist in the nucleus an uncharged particle of about the same mass as a proton. In 1930, Rother and Becker in Germany announced that they had noted what seemed to be an unusually penetrating gamma radiation produced by allowing alpha particles from polonium to bombard beryllium. The radioactive polonium gave off alpha particles which struck the beryllium. Radiation of some kind from the excited beryllium gave a high reading in the detector. Frederick and Marilyn Curie measured the penetrative power of radiation by inserting screens of varying substance. If these screens were of suitable density and thickness, most often reduced the amount of radiation reaching the detector. But when screens containing hydrogen in the form of paraffin wax were used, heavy increase of radiation was observed. In England, Professor Frederick confirmed the findings of Curie that this radiation was by an uncharged particle about the same mass as the proton. Imagine that this billiard ball is a proton. No stream of light particles by collection, no known type of wave, could have any more effect on such a body than these bright rays have on the billiard. But another particle of equal mass would share its energy on the billiard, just as this second ball imparts half its energy on the surface as it pushes it away. A particle of unit mass, but without electric charge, and so very difficult to detect. Frederick's reasoning recalled Lord Rutherford's suggestion of 1920, and the idea of a nucleus composed of protons and the uncharged particles, which were christened neutrons, was accepted. The field force around the nucleus acts as a barrier against the penetrative power of charged particles. Neutrons, however, being uncharged, can penetrate these barriers and strike the nucleus. The majority of nuclei are much heavier than the nucleus. If collision occurs, the neutron simply bounces off and continues with a slight loss of speed. Now, paraffin is made up of carbon and hydrogen. Protons, or hydrogen nuclei, are no heavier than a neutron. So, in collision, the neutron is able to transmit a large amount of energy to the proton. This is the explanation of the proton radiation observed by Professor Curie and Sir James Chadwick. The neutron at once explained the existence of isotopes. Chlorine, for instance,
an atomic number 17. That is, there are 17 electrons circling around the nucleus, of which there are 17 protons. But chlorine has two isotopes. The atomic weight of one is 35, and of the other 37. If we add 18 neutrons to 17 protons, we get an atomic weight of 35. And in the 37 isotope, we have to add 20 neutrons to get the correct atomic weight. An isotope of hydrogen, called heavy hydrogen, has a nucleus consisting of a single proton of ordinary hydrogen plus one neutron. This nucleus, called a neutron, has proved useful as a particle for bombarding atoms.
It became clear that to extend our knowledge, a more copious supply of bombarding particles of different sizes is necessary. Charged atoms of various sorts can be produced in vast numbers by the electrical charge suggested, and then accelerated by the use of high energy. In this way, we have been able to obtain our experimental transmission intensity of while the discovery of heavy hydrogen has given us a new possibility of remarkable transmuting energy.
Here, at the Cambridge Laboratory in Cambridge, the experts of this modern alchemy of transmutation go about their business. The purpose of these huge electrical machines is simply to use electrostatic forces to accelerate beams of charged particles to very high energy, and with these atomic bullets to bombard the atoms of various elements in order to see what changes occur in their structure. This laboratory grew out of the converted lecture room, where in 1932 Cockcroft and Walton operated one of the first successful machines to produce high-speed particles, and obtained significant results by bombarding liquids. The machine you see is a descendant of their original set. Ions are produced inside the large mushroom-shaped insulator and are accelerated down the rearmost tower. The bombarding tube continues down into the room beneath, where the stream of charged particles can be fed by a powerful magnetic field and directed towards the target. In the Science Museum at South Kensington is preserved the observation cabinet and acceleration tube of the original voltage quadrupler used by Cockcroft and Walton. Three cylindrical metal electrodes are arranged vertically inside a glass tube where a high vacuum exists. Protons emerge from a narrow positive ray canal at the top of the tube. As the protons descended, they passed through intense electrical fields by which they were accelerated and sharply focused. At the bottom of the tube, they struck the element set up as the target for bombardment. Any particle ejected from the target element passed through a mica window and caused scintillation on a fluorescent screen, which could be observed through a microscope. With lithium as the target, a startling result was obtained. Alpha particles of high energy were ejected. This result received wide publicity. Through the press, the public imagination was stirred by the vague implications of the phrase, "split in the air." But to understand the significance of this result, it is necessary to appreciate one of the most important aspects of Einstein's theory of relativity. Let us hear Professor Einstein himself.
It follows from the special theory of relativity more. So if we E is equal mc square, in which energy is just equal to mass multiplied with the square of the velocity of the wave, shows that very small amount may be converted into a very large amount of energy, and vice versa. The mass and energy were in fact equivalent, according to the formula mentioned above. This was demonstrated by Kocha and Walton in 1932 experiment.
In 5 non-committal terms, the scientists summed up their results thus. It seems not unlikely that the lithium isotope of mass 7 occasionally captures a proton, and the resulting nucleus of mass 8 breaks into 2 alpha particles, each of mass 4, and each with an energy of about 8 million electron volts. This reaction, which you see here, can be written down. We start with lithium of mass 7, placing 7 at the top left corner of the lithium symbol. Its nuclear charge is 3, so we add the figure 3 at the bottom left corner. The lithium is bombarded by protons, that is, hydrogen is added rather forcibly to the lithium, so we put down plus 8. Hydrogen has a mass of 1 and a charge of 1. As a result of the reaction, we get 2 alpha particles or helium atoms, each with a mass of 4 and a charge of 2. Note that the two sets of numbers add up to the same on each side of the reaction. 7 plus 1 equals 4 plus 4. 3 plus 1 equals 2 plus 2. The actual masses concerned in the reaction are known from mass spectra. On the left they total 8.0241 mass units. On the right, 8.0056 mass units. There is a difference of 0.0185 mass units. Measured in grams, this amounts to 3.07 times 10 to the minus 6. It is this amount of mass which has been converted into the energy released in the reaction. In other words, the relationship between mass and energy is a constant, and is expressed in Einstein's equation E equals mc squared, in which energy is put equal to mass multiplied by the square of the velocity of light. So, to find the energy released, we substitute for m the amount 3.07 times 10 to the minus 26. And for c squared, we substitute 3 times 10 to the 10th all squared, which is the square of the speed of light in centimeters per second. Thus, the energy released expressed in ergs is the product of these values, namely 27.6 times 10 to the minus 6. Now, the energy of each alpha particle released in the reaction can be directly calculated. It is 8.5 million electron volts. Or, more conveniently, 8.5 MeV. Thus, in our equation, we get E equals the sum of these energies, that is, 17 million electron volts. Measured in ergs, this becomes 27.2 times 10 to the minus 6. Thus, one calculation gives 27.2 times 10 to the minus 6, and the other 27.6 times 10 to the minus 6. Sufficiently close approximation to show that Cockcroft and Morton were correct, and that great energy can be released by splitting the atom. Man had set his foot firmly on the road towards the unlocking of great knowledge and power. All over the world, atomic physicists sought machines of higher and higher voltage with which to reach a goal that was still hidden. This machine is known as a supersonic. In it, electrons are whirled round at fantastic speeds by new methods method of using small high-frequency currents combined with powerful magnetic fields. High-speed electrons cause gamma radiation, which is betrayed by this sensitive detector. Even a thick screen is easily penetrated by this radiation. Energies as high as 8 million electron volts can be obtained on this machine, and in the United States, electrons of 100 million electron volts have already been produced. Giant systems are now being built to accelerate positive ions. Hidden behind a thick concrete barrier to absorb the dangerous gamma radiation is this latest type of linear electron accelerator, in which electrons pass through a series of alternating magnetic fields arranged in line along a corrugated tube known as a waveguide. Eventually, this machine will hurl electrons at its target with an energy of 5 million electron volts. Older in conception, but impressive in size and shape, is this electrostatic generator, designed to accelerate particle particles such as photons and neutrons. And this is one of the newest Van de Graaff machines to be built in England. These are so called after the American scientists who first designed them. Electric charge is sprayed onto a moving belt inside this tower and carried to the top of the accelerating tube, where the high potential thus generated is used to drive the particles down towards the target at great speed. When in operation, the machine is enclosed in a high-pressure casing which permits the potential of 2 million volts to be built up. Most impressive of all in their suggestion of a well-trained world are these 1 million and 2 million volt generators in the Cavendish laboratory at Cambridge. This is a cyclotron, one of the most technologies of accelerators. The inventor was Professor E.O. Lawrence at the University of California. The accelerating chamber, or tank, is fixed in the middle of the apparatus. Between the poles is a very powerful electromagnet. The principle is ingenious. The tank, which is completely evacuated, contains two hollow D-shaped electrodes, to which a high-frequency alternating current is fed. Minute quantities of the gas which is to provide the ions are admitted. The ions are produced in the center of the tank by electrons from the small arc or filament. Once produced, they are sucked into one or other of the beams by the powerful electric field. But this movement of the ions takes place between the poles of a big magnet. Consequently, the ions will travel with a circular motion in the magnetic field. The alternating voltage accelerates the particles each time they cross the gap from one D to the other, so that they are whirled round faster and faster until finally they are led off towards the target by means of a charged deflection plate. Here, an element is being set up and bolted into the target chamber, ready for bombardment. Nowadays it is known that almost all elements, if bombarded by neutrons, can be made radioactive for varying periods. Irene and Frederick Joliot-Curie first produced answers to radioactivity, and Professor Fermi made brilliant advances in this field. As the operator moves off towards the control panel, he passes through the water screen, 3.5 feet thick, which protects the scientist from the intense radiation produced by the accelerated particles. Now he begins to switch on the complicated high-frequency installation which feeds current to the beam. To build and operate such machines, atomic physicists have become engineers, overcoming step-by-step problems of high vacuum, screening from harmful radiation, construction of special magnets, and so on. For the production of neutrons, neutron beams are usually found most convenient. When the neutron strikes the target, it splits up, liberating a neutron, which easily penetrates to the nucleus. At last, the full power begins to flow. Through the observation window can be seen the arc in the center of the tank, and round it the pulsation of the accelerating particles. Some idea of the neutron's effect on the nucleus can be given by this simple experiment. nucleus of an atom. One might think that the neutron would go straight in and out on the other side, like this. Now let us fill the saucer with marbles to represent the particles in the nucleus. If we let the neutron marble roll down into the nucleus, it will just as the others will remain in the saucer. The nucleus has captured a neutron. It becomes unstable and gives off a stability as beta and gamma radiation. If the neutron marble enters the saucer with somewhat great affinity, one or more marbles will be knocked out. Thus, neutron capture can eject particles from the nucleus and cause disintegration. Outside the laboratory, the world was disturbed by the strident voices of evil men and the ever louder rumble of approaching war. But in 1939, atomic scientists made a fateful discovery. Professor Frisch, now at work in England, was closely concerned in this.
Early in 1939, Professor Hahn and Dr. Strassmann in Germany found that uranium, bombarded by neutrons, gave rise to what appeared to be an isotope of barium, only about half the atomic weight of uranium. Professor Luther Meissner, who had previously worked with Hahn and Strassmann, was by then deceased. He told me of their puzzling discovery, and together we considered the possibility that the uranium nucleus sometimes broke into two halves. We found that such a process, although quite unexpected, was indeed compatible with what we knew about atomic nuclei. If we were right, a great amount of energy was to be released in such a process, and I was able to show this experimentally.
Hahn and Strassmann's evidence that the disintegration of the unstable uranium gave rise to elements such as barium in the middle of the atomic case was purely chemical and required a physical confirmation before it could be accepted. The uranium nucleus is unstable and radioactive, as is known from its ability to emit an alpha particle. If a uranium nucleus could indeed capture a neutron, becoming more excited and splitting into two approximately equal fragments, it was to be expected that a large amount of energy would be released from such a process, sufficient fragments being hurled apart with great velocity. Professor Frisch obtained confirmation that this was so in an experiment essentially similar to the one shown here. Uranium was placed in the ionization chamber, which was placed over the end of a bombarding tube through which high-energy neutrons could be sent. The chamber was connected, as you see, from a cylinder. The trace you see here was made by alpha particles from the radioactive uranium. Now the high-tension set is switched on, and the uranium is bombarded by neutrons. On the screen of the oscilloscope, sufficient pulses reveal the large amounts of energy released when uranium atoms are split. If each fission had to be provoked by elaborate apparatus like this or accelerated particles, there was no hope of deriving useful energy from the process. But each fission was found to be accompanied by the release of a few neutrons. One neutron had been used to provoke the fission. The fission itself produces more than one neutron, and is thus itself capable of provoking more than one fission, and so on. There is thus the possibility of a self-sustaining chain reaction. The reaction can begin without any neutrons being supplied from outside, since a few fissions are always taking place spontaneously. These would supply a fused neutron. While these facts were being investigated, the political high tension in Europe sparked over into actual war. Years of aggression had at last forced the Western democracies to challenge the attempts of fascist domination of the world. There are two isotopes which make up the bulk of natural uranium. The atomic weight of one is 238, of the other 235. Over 99% of natural uranium is U-238. U-238 undergoes fission only with very fast neutrons. Many neutrons are scattered by uranium atoms and lose the speed necessary for fission. So, a divergent chain reaction will not take place in uranium which is predominantly U-238. U-235, on the other hand, undergoes fission with neutrons of any velocity. It seems possible that a controllable chain reaction might be achieved by using slow neutrons to cause fission in U-235. Using pure uranium containing both isotopes, a pile was built, in which uranium rods were embedded in a mass of pure carbon in the form of graphite. Neutrons produced in the uranium were slowed down by collisions with the light atoms of the carbon, the moderator as it is called, giving them a chance to cause fission in U-235. A slow controlled chain reaction was achieved on December the 2nd, 1942. If natural uranium and the moderator were replaced by a small amount of pure U-235, slow neutron reactions would give place to fast neutron reactions. Fission would occur, but so many neutrons would escape before hitting another nucleus that no chain reaction would build up. But if the amount of U-235 became larger than a certain critical size, a fast chain reaction would take place in less than a millionth of a second. This would produce a violent explosion. A simple mechanism from an atomic bomb thus suggests itself. Take two pieces of U-235, each smaller than the crystal size, but which, if placed together, exceed that size. They are driven together, and so U-235 became bomb material number one, and its separation from U-238 became a war priority. The behavior of U-238 in a pile is also of great importance. Slow neutrons are sometimes captured by U-238. No fission is caused, but this nucleus becomes U-239. This is unstable. A beta particle is emitted, causing a change to a new element with different chemical properties, neptunium-239. This new element is also unstable. Another beta particle is given off, forming another completely new element, plutonium-239. Now, plutonium-239 has fission properties similar to U-235, and will be built up by this process of neutron capture and subsequent beta disintegration throughout the uranium in the pile. Being a different element, it can be separated by chemical means from the uranium, and used also for a bomb. So, plutonium is bomb material number 2. Huge plants for the production of pure U-235 and of plutonium arose in the United States. By 1943, it had become plain that Great Britain was fully extended in war production. In consequence, her nuclear physicists crossed the Atlantic to continue with American and Canadian colleagues the brilliant work already done. The main practical effort and most of its prodigious costs now fell on the United States, where very active research has been going on since 1939. The processes were laborious, and at all times elaborate precautions had to be taken by workers on the atomic pile and in the chemical laboratory because of the ever-present danger from gamma and neutron radiation. Danger signs and warning signals, lead and concrete shields, remote control, detectors, protective clothing. These were the everyday equipment of the men who worked to make the material for the bomb. At last, in the desert of New Mexico, the first atomic bomb was set off under conditions of great secrecy. Thousands of calculations, years of work, reached their climax in this moment of dreadful splendor. Within a few weeks, the bomb burst upon Japan, now seen this supreme destroyer in action 5 times in all. We are aware now of the compelling urgency of the situation created by the bomb. We know that war must be banished, or else our civilization may die, as Hiroshima died on that summer morning in 1945. The tale has been told in full by those who lived through it. Utterly destroyed in an instant. 60,000 people dead, many from flash burn, thousands more by blood, many from strange sicknesses caused by gas radiation. For a short while, the world was sentenced to accept the fact that atomic energy, by destruction, had brought peace. Then came the question, can this power be controlled to serve mankind? Professor Einstein has recorded his opinion.
To give any estimate of when atomic energy can be applied to constructive purposes is impossible. What now is known is only how to use a fairly large quantity of uranium. The use of quantities sufficiently small to operate, say, in a car or airplane is as yet impossible. Presumably, all materials which may be used for such purposes will be among the heavier elements of high atomic weight. Those elements are relatively scarce because of their lesser stability. So, though the release of atomic energy can be, and no doubt will be, a great boon to mankind, that may not be for some time.
Other possible sources of atomic energy are suggested by what is known as the generation of solar and stellar energy. Under conditions of tremendous heat and pressure, complicated nuclear reactions are provoked, resulting in the building up of helium nuclei from hydrogen. In this process, large amounts of energy are released. Perhaps man may one day obtain energy by building up heavy atoms of the light. Meanwhile, the representatives of the United Nations in conference strive for some formula to banish the atomic bomb and to permit the blessings of atomic energy to be used for peaceful ends. Great Britain's research establishment at Powell is under the direction of Dr. Cockcroft.
You have seen the story of a remarkable scientific achievement based on the work of scientists of many nations, but owing most of all to the work of Rutherford
and the school of nuclear physics which he developed. Final achievement of the release of nuclear energy for war was due largely to the scientists and engineers of the United States, stimulated and helped by British physics. We have now the task of using the immense power of nuclear energy for peaceful purposes, for the production of radioactive materials, for medical and biological research, and for the generation of heat and power. With our present knowledge, it's possible to design nuclear power stations which will produce power at a moderate cost. Until we acquire operating experience of these plants, we do not know how economical they will be, nor are we sure we will be coming all the technical difficulties which will occur with large-scale nuclear power. Nevertheless, there is a real promise that over the next few decades, world power sources can be greatly increased, and as a very great benefits will be obtained, will be much to increase standards of living. It is the hope of every scientist that nuclear energy will lead to the establishment of a world organization for the effective control of all weapons of mass destruction. Through this, for the abolition of war.
From Dalton's theory to atomic power. It is a long road, but the landmarks are clear. With the atomic theory as a basis, a pretty complete picture of the elements of our material world was fitted together during the 19th century. The discovery of electrons, the realization of the nature of positive rays, the strange powers of X-rays revolutionized conception of the nature of matter and of the atom itself. The study of radioactivity, first investigated by Becquerel, and then by Curie, led Lord Rutherford to make the greatest single advance in atomic theory. He pictured a small, heavy nucleus in the atom, round which the electrons revolve. In 1919, Rutherford discovered how to change one element to another by bombardment with alpha particles. He suggested that the nucleus of the atom might contain protons and uncharged particles of about the same mass. In 1932, scientists could say with certainty that the atom contains electrons carrying unit negative charges and a nucleus built up of protons carrying unit positive charges and of neutrons, uncharged particles equal in mass to protons, whose existence was proved by Sir James Chesney. In 1932 also, Cockcroft and Walton split the lithium atom by bombardment with protons and found that mass could actually be translated into energy in perfect accord with Einstein's theory. Atomic disintegrations provoked by great machines became a commonplace of well-equipped physics laboratories. In 1939, uranium fission was first noted. The possibility of a self-sustaining chain reaction suggested the wholesale release of energy. Controlled chain reactions were achieved in the atomic fire. The imagination of the world has been stirred by the prospect of adapting such piles to use as sources of heat energy and as sources of radioactive materials for use in medicine. In research laboratories, the scientists are even now writing fresh pages in this unfinished story. But overall, the smoke of the atomic bomb hangs like a pall. If we are to reach the future that promises so bravely, the peoples of the world must see that this new power is wisely used.
Should there be a nuclear attack, many billions of them will fall through the sky instead of the earth, releasing radiation that could cause sickness or death in the area where they fall.
a raging nuclear furnace. It shoots out showers of particles too tiny to be massive as we can see them, along with invisible forces that we call radiation. This radiation and these particles travel through space at fantastic speeds until they strike some other matter which may make new flares of radioactivity. They strike wandering asteroids, moons, and planets such as our own. Everything in space, Earth included, we don't worry about the small amounts of natural background radiation. Amounts increase, so do the danger. The amount of energy generated by a nuclear explosion is enormous. Near the crater area, there is almost total destruction from blast and heat. And now, large amounts of pulverized debris and molten earth are poured out into the mushroom cloud. This is where radioactive fallout is formed. The radioactive atoms produced in the explosion join with the particles of earth and debris. Mushroom-shaped cloud forms, fine cloud. It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, throwing it off in one or more directions. Gravity clubs the cloud. The larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt or fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms, and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be. And this gives us an invaluable ally. Time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. 2 days, although still dangerous, it's only 1/100. In 2 weeks, it's only 1/1,000. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally. Distance. The greater our distance from the fallout particle, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top of ground floors, because will be more distance and partition between you and the source of the radiation. The fallout particles which would cover the roof and the ground around the building. Only an insignificant amount would get inside. And finally, along with decay rate and distance, you have still another and very important ally. Mass. When highly radioactive fallout covers our immediate area, we can shield ourselves through the most dangerous period by using the sheer weight of any material. But the protecting material must be heavy. To shield out some 99% of the radiation, you would need about 5.5 feet of wood, or 2 feet of earth, or 1 1/3 feet of concrete, or a half foot of steel. Even though the thickness of these materials varies, they all weigh the same. Taking a house as an example, it offers a small amount of mass and distance from radiation, but not enough protection in an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation. Whether it's a home for a single family, or a large community house in an apartment building, they offer the kind of protection from radiation you would probably need in case of a nuclear accident. The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we use a rate. And instead of miles per hour, we measure the rate in lengths per hour. We need not enough to affect it. This same healthy person would need medical care if he received more than 200 rentings within a few days. 300 rentings in the same period would cause severe radiation sickness or possibly death. And as we go beyond 300 rentings, the danger of death increases rapidly. So now we see why shelter is vital. The difference between accumulating a large dose because of little or no shielding and a small dose because of adequate shielding is the difference between death and life. No clothing, of course, could possibly provide enough shielding. However, if you were to be in the open during fallout conditions, clothing would keep the particles from touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you could reach the safety of the shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed. Its radiation damages only living things. And you can easily decontaminate it using almost the same methods you use in everyday food preparation. Actually, even if you accidentally swallow some fallout particles, it wouldn't kill you. The effects, if any, probably wouldn't show up for years. Still, since there is a possibility of long-term effects, such as shortened lifespan, cancer, or hereditary damage, it's wise to remove the radioactive particles by simply washing, wiping, or peeling. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time can reduce their potency. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. Chances are you wouldn't naturally go on. The water helps to wash itself through the natural processes of sedimentation and filtration. And quickly moving rivers like this can carry fitting on a ventilating pipe would keep fallout particles from entering the pipe and getting inside. Of course, surviving a nuclear attack means more than just waiting in shelter for radioactivity to decay to save life. Survival, reconstruction, and recovery would involve decontamination in many areas. A very difficult job.
Unit 8 at Elm Mark. Growth rate 15 lengths per hour.
Fallout would have to be removed from important areas by street sweeping. And the remaining particles could be flushed out of the way. The reason we would be able to grow and eat food planted in this land is the capacity of radioactivity in soil and plants is extremely low. Survival can only come through knowledge. The basic facts we must all know are relatively simple. First, there is nothing new about radiation. It has always been witnessed. What is new is the vast amount we would be exposed to as a result of nuclear explosions. Much of this danger would come to us in the form of fallout. But we are not without personal weapons for defense. One of these is time. Radiation decays, and so we would not have to take maximum precautions indefinitely. Another defense is distance. Radiating particles 50 feet away, for instance, would not affect us as much as particles a few feet away. And our third defense is mass. Any material with enough weight will keep the penetrating rays from hurting us. The greater the weight of the material between us and the particles, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed to safer levels. That's why food remains important in that fallout accidentally swallowed with water or food will do you no immediate harm, but for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin, but you would still need to find shelter quickly. If we remember these facts, if we act on them intelligently, we can increase our chances of survival nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man, woman, and child.
worry about the small amounts of natural background radiation. Amounts increase, so do the danger. The amount of energy generated by a nuclear explosion is enormous. Near the crater area, there is almost total destruction from blast and heat. Now, large amounts of pulverized debris and molten earth are pulled up into the mushroom cloud. This is where radioactive fallout is born. The radioactive atoms produced in the explosion join with the particles of earth and debris. Mushroom-shaped cloud forms and climbs high. It now contains billions of highly radioactive particles of matter that we call fallout. The strong winds of the upper altitudes go to work on the cloud, blowing it off in one or more directions. Gravity tugs on the particles. Larger and heavier ones sink toward the ground, while the lighter particles continue to drift with the wind. Some of the lightest particles remain suspended in the upper atmosphere. As time passes, their radioactivity grows weaker, so that the longer they remain aloft, the less dangerous they are. But the heavier particles, spread by high-altitude winds, fall to the ground within 24 hours. Several miles from the explosion, they are about the size of table salt and fine sand. These are the most dangerous, because they carry the greatest number of radioactive atoms, and so emit the largest amount of nuclear radiation. Which brings us to an all-important fact. Deadly as radiation can be. And this gives us an invaluable ally. Time. Suppose a nuclear explosion takes place at 12 noon. By 1 o'clock, the total force of the residual radiation is at a high level. By 7 o'clock, it's down to 1/10. In 2 days, although still dangerous, it's only 1/100th. But in 2 weeks, it's only 1/1,000. With this decay rate in mind, consider radioactive fallout conditions which might confront us after a massive attack. Within an hour, fallout will be a serious problem in the vicinity of explosions which occur on or near the ground. By 7 hours after the attack, the fallout area covers more and more of the country, as the prevailing winds expand the fallout in a downwind pattern. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people can even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than time. Fortunately, we have another ally. Distance. The greater our distance from the fallout particles, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top of a ground floor, because there would be more distance and distance between you and the source of the radiation. The fallout particles which would cover the roof and the ground around the building. Only an insignificant amount would get inside. And finally, along with decay rate and distance, we have still another and very important ally. Mass. When highly radioactive fallout covers our immediate area, we can shield ourselves through the most dangerous period by using the sheer weight of any material.
Taking a house as an example, it offers a small amount of mass and distance from radiation, but not enough protection in an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation, whether in a home for a single family or a large community site in an apartment building. They offer the kind of protection from radiation you would probably need in case of a nuclear attack. The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we have a rate meter. And instead of miles per hour, we measure the rate in kilometers per hour. We need it, not enough to affect it. This same healthy person would need medical care if he receives more than 200 wrenches within a few days. 300 wrenches in the same period would cause severe radiation sickness or hospital death. And as we go beyond 300 wrenches, the danger of death increases rapidly. So now we see why shelter is vital. The difference between accumulating a large dose because of little or no shielding and a small dose because of adequate shielding is the difference between death and life. No clothing, of course, could possibly provide enough shielding. However, if you were to be in the open during fallout conditions, clothing would keep the particles from touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you could reach the safety of a shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed, since radiation damages only living tissue. And you can easily decontaminate it using almost the same methods you use in everyday food preparation. Actually, even if you accidentally swallowed some fallout particles, it wouldn't kill you. The effects, if any, probably wouldn't show up for years. Still, since there is a possibility of long-term effects, shortened lifespan, cancer, or hereditary damage, it's wise to remove the radioactive particles by simply washing, wiping, or healing. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time can reduce their potency. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. The chances are you wouldn't have to for long. The water helps to wash itself through the natural processes of sedimentation and filtration. And swiftly moving rivers like this will carry most fallout particles downstream. In still waters, most particles will send up quickly to the bottom. Others might remain suspended in the water for some time, while a small percent of the radioactivity will dissolve. The normal processing of a water treatment plant would make it safe to drink. And water coming from a bottled well would be safe from radioactive contamination. There is no problem with breathing, for air is not contaminated once the fallout is on the ground. Fallout is not poison gas. If ventilation is needed in a shelter, a simple inverted tube fitting on a ventilation pipe will keep fallout particles from entering the pipe and getting inside. Of course, surviving a nuclear
be a problem. After a nuclear attack, we will first use existing food supplies to shelter farmers and surface food stores. When fallout has decayed to safe levels, people could begin to work in the fields for limited periods of time. In a few areas, the land would not be suitable for food, but such crops as pasta could be grown. Crops for human consumption can be grown in areas that have received the least support. The reason we would be able to grow and eat food planted in this land is the transfer of radioactivity from soil to plants is extremely low. And so, if nuclear attacks should ever come, despite its every effort to avoid it, we must be able to survive and rebuild for the future. But survival can only come through knowledge. The basic facts we would all know are relatively simple. First, there is nothing new about radiation. It has always been with us. What is new is the vast amount we would be exposed to as a result of nuclear explosions. Much of this danger would come to us in the form of fallout. But we are not without personal weapons or defense. One of these is time. Radiation decays, so we will not have to take maximum precautions to do that. Another defense is distance. Radiating particles 50 feet away from us will not affect us as much as particles a few feet away. And our third defense is mass. Any material with enough weight will keep the penetrating rays from hurting us. The greater the weight of the material between us and the particles, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed and safe around. That's why food remains good no matter how much radiation has passed through. Fallout accidentally swallowed with water or food will do you no immediate harm, but for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin, but you would still need to find shelter quickly. If we remember these facts, we act on them intelligently, we can increase our chances of surviving nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man
release of energy becomes manifest in three forms: heat, radiation, and blast, if that will be by far the most important. The effect of the atomic bomb on the selected target depends on three factors. First, the nature of the target. Second, the power of the bomb. And third, the height at which the bomb is detonated. For the purpose of this film, we shall assume that the target will be a large British city, and that the power of the bomb will be equivalent to the explosive force of 20,000 tons of TNT. This size is known as a nominal bomb. The assumed height of detonation will be 1,000 feet above the sea. This is about the height at which maximum destruction would be caused to a British city. To explode the bomb below this height will reduce the area of destruction. While to explode it at a greater height will reduce its power to destroy large, steel frames. If the bomb were to be more powerful than nominal, then the height of detonation would be greater. Now we'll examine the three kinds of heat. First, there is that of heat. The heat originates at the moment of detonation and continues to come. The gaseous product of the explosion glow and form what is called the ball of fire. It expands rapidly, and as it cools, it shoots up into the atmosphere at an initial speed of 200 miles an hour. The gases then form into the familiar mushroom-shaped clouds at a height of some 40,000 feet. Although the heat ranges a very short duration, it can cause considerable damage. The heat from it will scorch and may set on fire any exposed inflammable material up to a distance of 2 miles from the earth. Atmospheric conditions range for the fire. On a misty or foggy day, the range of the heat blast will be greatly reduced. Effect number 2 is that of nuclear radiation. The effect of radiation becomes manifest in two forms. First, immediate radiation, and second, residual radiation. There is immediate radiation of gamma rays and neutrons at the time of the explosion. They are centered in the rising ball of fire, which carries them out of range within less than 1 minute after the explosion. The gamma rays travel at the speed of light in all directions of the explosion. They have a lethal range of about 3/4 of a mile to any person directly exposed to them or into the field. Beyond this point, the power of the rays still lost rapidly. They do not make the ultraviolet radioactive. The neutrons are atomic particles produced from the explosion, which have the power to make some material that strikes radioactive. Their effect is largely outweighed by that of the gamma rays. The second form of radiation is that known as residual radiation. This consists chiefly of gamma rays which arise from deposited radioactive material, and to a lesser extent from material made radioactive by neutrons. Since only a small fraction of radioactive material ever reaches the ground, the danger from residual radiation is much less than from immediate radiation. These gamma and other rays are less concentrated, and they only become dangerous to human life if a person is exposed to them for a long time. In the case of a bomb detonated at 1,000 feet, there would be relatively little danger from residual radiation. Last, but by no means least, we come to the third effect, that of blast. This effect is caused by a shock wave resulting from the sudden and terrific heat produced by the release of atomic energy. With the normal type of explosive used in the last war, detonation of the bomb usually occurs on or after impact with the ground. If the atomic bomb is detonated on impact or below ground level, like this, the effect is somewhat different. A very deep crater would be formed, and it would be surrounded by a great ring of crater debris. The blast effect would be considerably less, although there would be a large area around the crater where buildings would be collapsed by earthquake effect. The danger from heat flash and immediate radiation would be less, since the insulating properties of the earth would absorb the greater heat. The danger from residual radiation would be greatly increased in the vicinity of the crater. Same applies to an underwater. Considering once more our nominal volume estimated at 1,000 feet, let us get some idea of the area that would be affected. The area may be divided into three circles, the first of which will be a quarter-mile radius. First, this point is known as ground zero. Within this quarter-mile circle, the target will be completely ground. The second circle, drawn at a radius of 3/4 of a mile from ground zero, will contain a large number of buildings totally or partially destroyed. The third circle, at a distance of a mile and a half from ground zero, marks the limit of houses suffering severe structural damage. Outside this area, the damage will be progressively less severe, tailing off at about 2 miles. If such a bomb were detonated over London, the relative area affected would be approximately this size. Over Birmingham, the relative area would be this size. Over Glasgow, this size. And over Liverpool, this size. Now we will take an imaginary city, call it Sheffield, a typical British city of 500,000 people, and see more clearly what the effects of the atomic bomb have been. The air raid warning has sounded, and people are in the shelter. The atomic bomb has burst over the camp. Within a radius stretching out to a mile and a half from ground zero, a large number of buildings are destroyed and many are burned. Let's take a closer look and see what it looks like before and then after the bomb has exploded. There is no need to study the whole area, and it may be presumed that the effects are similar at comparable distances from ground zero in any direction. So we'll take a slightly more section of the planet like this. Now here is a portion of Sheffield, about a quarter of a mile from ground zero before the explosion. First there was the flash, and then the blast. This entire area is now devastated. That is to say that it is more than 80% totally destroyed. As a result, the fires here will be of little consequence, but the spread of rubble may make the locating of air raid shelters and the ultimate rescue of their occupants extremely difficult. Now let us examine the second circle, a distance of 3/4 of a mile from ground zero. Here it is before the explosion. Again, flash and blast. Notice that the damage is severe. Many streets are blocked with rubble, and this fact, combined with the large number of fires caused by heat flash, will produce many problems for those responsible for rescue. And so we come to the third, one of the hardest. Here it is before, and now after. Windows are broken, roofing damaged, doors blown off and injured. Structural damage is unlikely. distance from ground zero, damage will be confined to broken windows, fallen tiles and chimney pots, and similar minor damage. Only in exceptional circumstances would there be major structural damage. That then would be the effect of a nominal atomic bomb detonated at 1,000 feet over a British city. You may have noticed that no mention has yet been made of the aircraft carrying the atomic bomb was mistaken to be the atomic bomb, and the population did not take cover. That mistake cost many lives. In a British city with wartime evacuation, with an efficient air raid warning system, and with the cooperation of an intelligent public using suitable shelters, such a terrible death row could be very greatly reduced. The number of casualties, however, will depend on the state of preparedness of the population to meet such an event. In particular, it will depend on the number of trained civil defense workers, who, together with the police and firefighting services, will be available and ready for action if and when the time is come. Surrounding an object is affected by the intense non-free heat of the flame, with the exception of that part directly in the shadow of an object, like this furnace. This effect occurs so rapidly that the outline of the leaf is barely left before the leaf itself is destroyed by the heat. In this case, the shadow of a man was left before the leaf comes down. Here, the flash came through the window and left the imprint of a man's pipe. Should the population have failed to take cover prior to the atomic bomb explosion, severe skin burns will be very heavy up to a distance of 2 miles from ground zero in clear weather. It's important to realize that the weather conditions at the time of the explosion have a marked effect on the range of the heat gas. In heavy mist, rain, or fog, the effective range of the flash is more than half. Types of clothing worn by unsheltered people will also affect the number of injuries from burns. Thick woolen garments offer the best protection, and at the extreme range of the flash, lighter colored cloth is more easily taken. Covering of all normally exposed parts of the body with any material will invariably lessen the severity of the burn. However, if we assume that the population has taken cover, there is no danger directly from the heat. The indirect danger, that is fire started by the flash, may produce a number of problems and must be considered as a common effect of the explosion. Any easily inflammable material exposed within a 2-mile radius of ground zero is liable to be ignited by the heat. In this country, there is little use made directly exposed to the flash would be so effective. Therefore, it is likely that a large number of primary fires started will be situated on the upper floors of buildings. These fires may be quite small, started by ignited curtaining or furnishing, and easily dealt with by cannon-operated equipment. It's very important that the small fires occurring in a otherwise undamaged area be dealt with quickly. Otherwise, the spread of the fire will seriously impede the firefighting of rescue squads endeavoring to reach the wall of the damaged area. The risk of fire from heat flash can be very greatly reduced by the simple expedient of electrifying the window pane. It is to be remembered that although glass in itself offers little protection against heat flash, any more than it stops the heat from the sun, the glass will not be shattered until after the flash has done its task. This is because the shock wave of glass travels much slower. Any white or lime electrical glass will withhold the heat and reduce its penetrating fire considerably. Or the climax of the building. At night time, a wooden blackout screen fitted to the window will also serve to reach the surface and expose the heat flash. The wood may be charred on the outside, but it should prevent fire being started in the room. All such screens should, of course, be whitewashed on the outside. If the curtaining material is very heavy, it will also serve to stop the heat flash from entering, though at the risk of the curtain itself at night. There are, however, several ways of making materials fast. This can be done at home. Householders will be advised on how it is best done. The more serious fire situations may be expected at the 3/4 mile range from ground zero. These will include a number of secondary fires started by collapsing buildings. It will be important to warn the public that all domestic cooking and heating appliances must be turned off at the main before taking cover. It will be even more necessary than before to obtain cooperation from the public in clearing their attics and lofts, and in providing their own firefighting equipment to deal with small outbreaks. Remember, with the explosion of an atomic bomb, fire will be a very great danger to human life and property. For the purpose of this film, we will assume that the atomic bomb used is a monster bomb, and that it is detonated at a height of 1 ton. We know that one of the three effects of an atomic bomb burst is that of nuclear radiation, and that this effect is itself divided into two stages: immediate radiation and residual radiation. It must be emphasized that nuclear radiation will not be a source of danger for the civil defense worker, provided that he is protected from the immediate radiation and does not exceed the specified safe dose of residual radiation. The rays emitted by the bomb at the moment of the bomb's detonation come of the first immediate category. The most important of these are gamma rays and neutrons. The lethal range of the neutrons is smaller than that of the gamma rays, so the latter must be our main consideration. The effects due to the activity induced by neutrons in various materials will be examined with the other effects due to deposited fission products when we deal with residual radiation. All forms of radiation can be measured in terms of wavelength. Gamma rays have a very short wavelength. Related to other and more easily identified forms of radiation, gamma rays have a wavelength even shorter than X-rays, which, as you know, have the power to penetrate a human body and affect a photographic plate exposed on the far side. At the longer wavelength are the ultraviolet rays produced by the sun. Longer again is that of visible light. Then infrared rays, and considerably longer, the radar and radio wavelengths. It will be seen then that the gamma ray wavelengths are among the shortest wavelengths known to man. Short wavelengths When an atomic bomb is detonated, gamma rays are emitted in all directions at a very high speed. They travel up to a mile and a half from the Earth. Except in the case of very massive doses, there is no immediate physical reaction to these rays entering the body. It may be some days before radiation sickness will experience. With a lethal dose of gamma rays, death will usually occur at any time up to 6 or 8 weeks later. The gamma ray dose received by a human being when an atomic bomb is detonated is governed by two factors. First, the distance from the explosion, and secondly, the amount of protection available. As the rays stream out from the source, they are spread over an ever-widening sphere, so that their density falls off very rapidly. At a range of 3/4 of a mile, the density is so far reduced that the dose received is not released, although it may cause explosion. At distances greater than 3/4 of a mile from the explosion, the energy and penetrating power of the rays fall off rapidly, and by the time they reach the minus one circle, they are virtually lost. The second factor, that of protection, is of great importance. For protection from gamma rays of the density of materials, the less the thickness required. At 1/4 of a mile from ground zero, protection from a lethal dose may be obtained from 7 inches of steel. The same degree of protection can be obtained with 2 feet of concrete or 3 feet of well-packed earth. Air raid shelters of the last war type will afford definite protection depending on their distance from the explosion, and with a additional covering of earth or concrete can be efficient to a substantial degree. Now we will examine the kind of radiation known as residual. As its name implies, it concerns the radioactive particles left on the ground after the explosion. Into an area some 1/4 mile radius from ground zero may fall a quantity of radioactive particles called fission products. These are the products resulting from an atomic explosion. They are radioactive and emit gamma rays. The rising cloud from the explosion is also filled with these particles. They may be carried by the wind and will be widely dispersed. Some may fall to earth anywhere down the river. This is called a fall. The radioactivity at the fallout is likely to be relatively weak, therefore not considered. The neutrons which were emitted from the bomb at the same time as the gamma rays also have the power to cause residual radiation. With this type of airburst bomb, a number of these neutrons will reach the ground in the vicinity of the explosion. In doing this, they may make other objects on the ground radioactive. That is, they cause those objects to radiate gamma and other rays. Except with air bursts of about 500 feet or below, the potentially dangerous gamma rays of residual radiation, whether caused by fission products at ground zero, or by neutrons, or in the fallout, are not likely to be present in sufficient quantities to be a serious hazard, unless exposure to them is prolonged. In the case you see here, there is believed to be some radiation due to a streak fallout, and a reconnaissance party is sent to investigate. Radioactive rays are measured in dose rate, units received per hour. These units are called Roentgens. It's known that a single dose of 500 Roentgens has a 50-50 chance of being useful to human beings, and that a dose of 25 Roentgens has no observable effect. Although it's unlikely that civil defense personnel will absorb even this amount in the normal course of their duties, nevertheless, in special circumstances, they may be called upon to receive considerably greater doses. It is known that a dosage of 50 Roentgens can be absorbed without undue risk. In these cases, civil defense workers may, where circumstances, be withdrawn from radioactive hazard. Although it might at first sight appear advisable for civil defense personnel to wear respirators so as to avoid inhaling radioactive particles, the real danger is from the residual gamma radiation. And provided this is restricted to 25 Roentgens, it has been found that there is no danger from inhaled particles.
It is possible for the radioactive dust of fission products to contaminate exposed food and water and thereby lead to radioactive waste. However, food and water stored in undamaged airtight containers would be immune to the risk of contamination. It is important to realize that radioactivity in any of the sources cannot be destroyed. This makes decontamination a difficult problem. It does, however, decay rapidly with the passing of time. In the case of fission product contamination, at the end of the first 24 hours, the gamma ray activity is only 1/50 of what it was after 7 hours. Provided the civil defense worker is adequately protected from gamma rays at the time of the explosion, and that an accurate record is kept of the dosage he has received, radiation is the least dangerous of the atomic bomb being placed.
You will no doubt have seen, even if you will not study, Civil Defense Handbook and Attack, entitled Advising the Householder on Protection Against Nuclear Attack. In order to illustrate the contents of this handbook more graphically, the Civil Defense authorities have produced 7 short films based on the 7 sections that form the contents of the handbook. If the government decides that the time has come for this advice to be acted upon, these films will be shown to the public on all television networks. Their present purpose, however, is for your information. So we shall now show the 7 films as one. Here we go. The government has decided that in the present state of international tension, you should be told how best to protect yourselves from the dangerous effects of nuclear tension. If this tension should lead to war, it is essential that you should have taken every possible precaution to safeguard your family, yourself, and your home. This film will show what are the dangers you expect, best means. First, the basic facts. When a nuclear weapon explodes, it produces 3 main hazards. The first of these comes from the heat generated by the fireball. This may last as long as 20 seconds. The heat is so great that for some miles around the explosion, it could kill people who are caught in the open, and it could burn exposed skin over a much wider area. The heat also threatens your home. By striking through unprotected windows, it would start fires across the whole area. The second danger is from blast. For some miles, buildings will be destroyed or severely damaged. Further out, buildings will suffer less severe damage as the blast effect diminishes. And for many miles beyond that, there will be light damage, such as broken windows. The third danger is from fallout. If the bomb explodes on or near the ground, dust is sucked up by the explosion and is made radioactive in the rising fireball. It rises high in the air and is then carried downwind, falling slowly to earth over an area which may be hundreds of miles long and tens of miles wide. Within this area, everything in the open will become covered with a film of radioactive dust. This fallout dust gives off radiation, rather like X-ray. Radiation cannot be seen, felt, heard, or smelled, but exposure to radiation can cause sickness and death. The radiation is at its greatest intensity during the first 2 days, but the danger decreases rapidly as time passes. After 2 days, it is 100 times less harmful than at first.
but even then it is still dangerous. These then are the dangers that may face all of us: heat, blast, and fallout. In the other section of this film, you will be shown what precautions will help to protect you from them. To obtain protection against fallout, and as far as possible against heat and dust, you should now select and fortify a room in which to shelter, both during the attack and during the period of intense radiation and follow. The penetration of harmful radiation is cut down by heavy and dense materials such as brick, concrete, and earth. The more, therefore, of these materials you can put between yourself and the fallout, the greater the protection you will obtain. The fallout will not get inside a house that has its windows and doors shut and has not been damaged by the blast, but it will settle on the roof and around the house. It is the radiation from this external fallout that endangers anyone inside. Now the choice of a fallout room. A basement or a cellar will give you the best protection and is the most suitable as a fallout room. Many houses will not have a basement or a cellar, but you can still find a room in your house which will give you protection from fallout. Remember that the more material there is between yourself and the fallout, and the further you are from the outside walls and the roof, the better the protection you will obtain. You can see why this ground floor room gives the best protection against fallout. It has only one outside wall, with the other walls either connecting inside the house or with the house next door. The room is also shielded by the houses across the street, which give it extra protection. The radiation from fallout can come from an appreciable distance, so this makes the front room more suitable than the back room, which overlooks a wide area and is far more exposed. If you live in a modern concrete block of flats of 5 or more floors, unless there is a basement, the best protection is given by the middle floor. If your home is in the upper or lower parts of the building, it will be best if you made arrangements to join the family living in the middle floor. In no circumstances should the top stories be used. In a block of flats with 4 stories or less, or one which has wooden floor joists, the best protection will be on the ground floor. A room should be selected in the same way as for a house, with not more than one outside wall, and with the most protection from neighboring buildings. Prefabricated houses or bungalows give little protection from radiation. If you live in one, you should try and join friends or neighbors whose houses give better protection from fallout. If this should not be possible, there are other steps you can take which will be described later. Wherever you live, when you have chosen your fallout room, it should then be modified to improve the protection it can give you. The windows will be the weak point and will have to be blocked in with some heavy material. Using sacks or sandbags, which should be about 2/3 full, you can block the windows from the outside. Here, they are piled on strong cables until the whole window is blocked. Alternatively, you can fill boxes or other containers with tightly packed earth. If you can't block up the windows from the outside, pieces of heavy furniture should be positioned in front of the window, and then packed with earth or board. A second method to use is to remove the window altogether. Fill the gap both on the inside and the outside with planks or boards. These rest on the windowsill and should be bolted or wired together. As you build them up, you should fill the space between the boards with tightly packed earth. Thirdly, after removing the window pane, you should fill the space with brick, a double layer. Both these methods are as effective as sandbagging and may be the most suitable for your house. You can make the fallout room more effective by blocking the outside door and any windows in the passage leading to your room, by treating adjoining rooms in the same way, and finally, by thickening the outside wall. By constructing a core, or heavily protected shelter, you can greatly improve your protection for the first few hours when radiation is at its greatest intensity. This is especially important for those of you living in a bungalow with no alternative shelter. There are several simple kinds of shelter for you. Here, 2 doors are leaned against the wall, leaving a space in which the householder and his family can sit, and then bags of earth are placed over the top. Here, the floorboards are taken up and a trench is dug under the floor. Ensure that it is in the corner furthest from the outside wall. You could also use a cupboard under the stairs, with sandbags outside the door and on the stairs.
For some of you, it will not be practical to build a shelter indoors, but a trench dug outside your home would give good protection. It should be deep enough to stand in, and the sides should be short. The trench should be covered with planks or other available material strong enough to support at least 2 feet of earth. Don't forget to leave an entrance to the movable cover.
In one or other of the ways we have just seen, you should now take steps to protect yourselves against the hazards of nuclear attack. After an attack, it may be necessary for you, your family, and any others who have taken refuge with you to live in your fallout room for at least a week. It may not be safe for you to go outside to obtain any more food and water, so you will have to be prepared to live on the supplies you collected before the attack. You will now be shown what general provisions you should make. First of all, your furniture. Your shelter is going to be your living room, your bedroom, washroom, your kitchen, and your storeroom. It must have the basic furniture to fulfill all these requirements, but at the same time, floor space should be saved wherever possible. Use shelf space to its best advantage.
Your room will need heating, bedding, a portable radio and spare batteries so that you can receive advice and further instructions, amusements and pastimes for you and the children, simple cooking equipment and fuel, and a large store cupboard for food supplies.
You will need to have by you a reserve of tinned and other non-perishable food. This should be enough to feed the whole household and possibly some extra mouths for at least a fortnight. Wrap up all your food, except for tin stuffs, and keep it in closed cabinets or cupboards. Food is not harmed by fallout radiation, but anything that has had fallout dust on it will be contaminated and made dangerous to eat. If there are babies or young children, remember their special food, and don't forget the pets. It may not be possible to keep all your food in the fallout room, but you should keep as much food there as possible. Any remaining food should be kept in your larder or in a cupboard close to your fallout room. Once there has been a warning of fallout, it may be dangerous to leave your fallout room except for very short periods to collect more food and water. After a nuclear attack, the main water supply may fail or become contaminated by fallout. Store as much water as you can. For drinking, you will need a minimum of 2 pints per person per day. 3 days' ration of drinking water should be kept in sealed flasks, bottles, or jars inside the fallout room itself. Do not waste the water. It may have to last you a fortnight. Fill the bath, the hot and the cold tank, and every available container. Keep reserves away from the light and cover. Water stays fresher in the dark, and if fallout dust gets into the water, it will be contaminated. Find the whereabouts of your main stopcock, and be ready, if there is a warning of attack, to turn off the supply. After an attack, you may not be able to use your lavatory because of insufficient water for flushing. Therefore, you must make alternative arrangements for sanitation. either in your fallout room or just outside the door. You will also need to provide a dustbin, as there will be no way of disposing of your refuse. Finally, first aid. A simple but well-stocked first aid box. You must be able to help people who are injured or taken ill. It is essential that your fallout room is properly equipped for sleeping, eating, drinking, storage, cooking, refuse, sanitation, and emergency first aid. Remember, you may have to live in the room for at least a week. Your survival may well depend on the care and foresight with which you have supplied your room. When you have completed the preparation and equipping of your fallout, you should next take precautions to safeguard the rest of your house. You should be prepared to deal with the worst effects of heat and blast, in particular, the menace of fire. Fire is the most immediate danger after a nuclear attack. Though the heat will not set light to the bricks or plaster of your house, it will strike through unprotected windows and set any inflammable material on fire. Whitewash the windows, especially those at the top of the building. This will greatly reduce the fire risk by reflecting away much of the heat, and the heat should have passed by the time the slower-moving blast wave arrives. There are other things you can do to reduce the fire risk. You should remove all inflammable materials from upper floors, which are the most exposed to the heat wave. Clear away all newspapers, magazines, and wooden furniture, so as to leave as little as possible that could start fire. You should also remove any boxes and inflammable material near the outside of the house. If you have a garden syringe or a spirit pump, this should be kept close to your fallout room. Fires can be put out quite easily if tackled at once, while they're still small, but they spread rapidly and can soon get out of control. Keep buckets of water on each floor of your house. Remember, fires can be extinguished just as well with dirty water as with your valuable drinking water. To minimize the danger from flying glass, you should draw your curtains and lower your blinds. After an attack, it may be necessary to move you and your family to a safer area. To provide for this emergency, you should have a suitcase ready packed. You should include a change of clothes, personal valuables, eating and drinking utensils, and a blanket. Take an overcoat or mackintosh in case of rain. You must remember you will only be able to take what you and your family can carry. Finally, a point for all car owners. Always keep your car topped up with petrol so that if you're instructed to move to a safer area, you will be ready to leave at any time. But until you are told, you will not know where it is safe to go. These are all necessary precautions, as there will be no time for preparation once an attack starts. By taking these steps, you can increase the safety of your home and of your family. I'm going to explain the system of warning used in this country against nuclear attack, and on which you should be prepared to act. An exact knowledge of the signals and what to do when you hear them could save your life. There are 4 warnings: the red, the grey, the black, and the all clear. First, the red one. siren is sounding the red warning. It means that there is imminent danger of an attack. This is the gray warning. It means that fallout is expected in an hour's time. Where sirens have not yet been provided, the gray warning may also be given by church bells, or in Scotland, where church bells are not in common use, by word of mouth or by whistle. These are maroons. They indicate the black warning. It means there is imminent danger of fallout in your area. Where maroons have not yet been provided, this warning might be given by a gong or whistle sounding one long and two short notes, which is the Morse note, D. Finally, this is the all clear. It means that there is no further threat of air attack or fallout and that you can leave your place of shelter. The all clear may also be given by civil defense workers or the police. Now, what to do when you hear the signal? First and most important, you should take cover immediately if you hear this red warning. If you are outdoors and cannot get home in 4 or 5 minutes, take cover in the nearest building. If you are caught in the open, take any available shelter. But if there is no obvious cover, you should lie in a ditch or a depression in the ground, covering the exposed skin of your face and hands to protect them from the heat flash.
An air attack is approaching this country now. Go to shelter or take cover at once.
If you are driving a car, park immediately. But do not leave your car in any place where it might obstruct the many vehicles that will be engaged on urgent rescue work. Park it off the road if possible. Find the nearest cover, and if there are no buildings, lie flat in a ditch or depression. You should always give shelter to anyone who is caught in the open near your house when the warning sounds. They may have no other protection from the attack.
An air attack is approaching this country now.
If you are visiting, take cover wherever you are, unless you can get home in 4 or 5 minutes. If you are at home, you should turn off the gas and oil supplies and disconnect your electric heater. Damp down any fires with earth or sand and close all your windows. Then take cover in your fallout room or shelter. Now a grey warning, with fallout expected in an hour's time. If you had only taken temporary cover, you should go home, if you can get there quickly. If, however, you are still in the open, look for safer and more comfortable shelter as quickly as possible. If you are visiting and have taken shelter, go home if you can get there quickly. But if you can't, stay where you are. If you are at home, finish any last-minute preparations and then go to your fallout room. Finally, a black warning, which means fallout is imminent. If you are still outside, find the best available cover. If you are visiting, take shelter where you are. At home, go at once to the fallout room when the black warning is heard. Remain there. Keep the door of the room shut, as there will be plenty of ventilation from around the door.
Everyone must realize there is the possibility of an attack taking place before any warning can be given. If this happens, the first indication would be the flash of heat and light produced by the explosion and lasting up to 20 seconds. This would be followed by the blast wave. Whatever happens, you must not look in the direction of the flash. It could blind you.
If you are caught in the open by the attack, fling yourself on the ground instantly, wherever you are. move until the blast wave has passed. If you are at home or visiting, move instantly away from open windows or doors and take cover behind the nearest solid protection. When the heat flash passes, go to your fallout room if you can reach it in a matter of seconds before the blast arrives. If you can't, you should stay where you are until the blast wave has passed.
It is unlikely that an attack will come without any warning, and the warning system is aimed to give notice of the threat of attack and of fallout so that you have time to take cover. Instant recognition of the warning signals is vitally important. So let's recap.
The red warning. Imminent danger of attack. The grey warning. Fallout expected in an hour. The black warning. Danger of fallout imminent. The all clear. No further danger of attack or fallout. Warnings will only be cancelled by the all clear, or by word of mouth from the police or civil defense warden.
Once a warning has been given, there is danger, and you must not expose yourself needlessly. From now on, you must listen for and take immediate notice of warning signals. For your own safety, you must follow exactly and promptly any instructions given by civil defense workers or the police. The warning system can save your life. You must not only know what to do in the event of a nuclear attack, you must also know what action to take immediately after. Your safety may depend on prompt action taken during the short time that may elapse before fallout arrives.
As soon as the heat and blast waves have passed, one of you should leave your fallout room and find out the extent to which the house has been damaged. Fire will be the most immediate danger. You should go round the house and put out any fires that the heat may have started before they have a chance to become established. Call your family to help you if necessary. Fires can be extinguished by using mains water if still available. You must turn off the stopcock as soon as possible so as to prevent the possibility of contaminated water entering the system. You must at the same time turn off any water heaters and shut down your boiler. To prevent valuable clean water from being used for flushing, you should tie up the ball cock in your WC cistern. From now on, conserve your water supply. Having dealt with the inside of your house, you should now put on gumboots or stout shoes, a coat done up to the neck, a hat or headscarf, and some gloves before going to see what needs to be done outside. This must be done, regardless of the unknown risk of fallout. Make sure your house is safe from any fires that may have started nearby, or fires that may spread from other houses. When you have dealt with your own home, be ready to give assistance to your neighbors if they need help. But whatever you are doing, listen for the warning signals of approaching fallout. If you have been in the open after an attack, when you get indoors, take off your outer clothing and leave it outside the fallout room. Have a wash if possible. By these precautions, you will get rid of any fallout that may have settled on you. Once this has been done, go to your fallout room and stay there.
It is vital that you should know what to do immediately after. On your actions, may depend the safety of your home, your family, your neighbor, and yourself. Any delay on your part may endanger the lives of everyone living around. Once the black warning is sounded, it means your home is in a fallout area and you must remain in your fallout room. Remember, you may have to remain under cover for at least a week, and our general guide for the days you'll have to spend in your fallout room.
Stay in your rescue room.
During this period, listen for announcements and instructions on your radio. It will be all right for you to leave the fallout room to collect more food or water, or to go to the lavatory. But time spent outside your fallout room should be kept to the absolute minimum. Except for these reasons, you should never go outside the fallout room. Fallout dust cannot usually be seen. Only the wardens and the police, with their special instruments, will know the level of fallout radiation. The amount of fallout will vary from place to place. It will be heaviest in the middle of the fallout area and grow less and less towards the edge of the plume. Where fallout is particularly heavy, people may have to be moved to a safer area. If this does become necessary, you will be told by radio or by the warden or the police. Keep your suitcase to hand and be ready to move, but on no account leave home before you are told. If you have to be moved, put on some warm clothes and take with you enough food to last for 24 hours. This food should be packed in airtight containers. Private car owners will be asked and expected to fill every available seat. As few people as possible will be moved, and for most of you, it will be stay in your fallout room. Use your food and water carefully, and always remember the danger of radiation. For your own safety, you should wear plastic or rubber gloves. Keep all your food covered. If the cover is unbroken, then the food will be safe. Before you open the food, wipe the packing carefully. This will prevent any fallout dust that has settled on the package from getting into the food. When you've unwrapped the food, you should immediately dispose of the wrapping in the dustbin. Your water must also be kept covered. Do not use any mains water for cooking or drinking until you have been told that it is safe. In the meantime, use your water sparingly and reuse the water for different purposes. Always remember, boiling contaminated water will not make it safe for drinking. Everywhere, the dangers from fallout will decrease as time passes. When the danger from fallout is lessened sufficiently, the civil defense or the police will tell you when you can go outside. Do not go out until you are told it is safe. And even then, you may only be able to go out for a very short time. Essential work will be restarted as soon as possible. Emergency arrangements may be made for the distribution of water. You will be told when it is safe to stay out for longer periods, but there will still be danger from fallout, and nobody should remain outside for longer than necessary. You must still be careful not to bring fallout into the house from outside. Wear some stout boots or shoes to go out, and change before returning indoors. Wash the boots thoroughly when you get back. Wipe down all the working surfaces in your kitchen, your larder, and also anything that may come into contact with food. You should wear plastic or rubber gloves, and when you have finished, you should wash the dust. Burn all your rubbish. Although the fire will not get rid of radioactivity, it will reduce the bulk of your rubbish and help to prevent the spread of ordinary disease. If the present world situation does lead to a nuclear attack on this country, It is vital that you shall have taken the necessary measures to safeguard your home as much as possible. It is vital that you should know what action to take in the event of a nuclear attack. If you fail in this, your negligence could endanger the lives of your friends and neighbors as well as your own family. Remember that the civil defense wardens and the police are here to aid and advise you. But wherever you live, you must know how to help yourself and be prepared to help others if their lives are in danger.
Nuclear explosions are caused by weapons such as H-bombs or atom bombs. They are like ordinary explosions, only many times more powerful. They cause great heat and blast. They also make a cloud of deadly dust which falls slowly to the ground. This is what is called fallout. So these are the two dangers. First, heat and blast, which is followed by fallout. The heat and blast is so severe that it can kill and can destroy buildings for up to 5 miles from the explosion. Fallout is dust that is sucked up from the ground by the explosion. It can be deadly dangerous. It rises high in the air and can be carried by winds for hundreds of miles before falling to the ground. You can protect yourself and your family, and later on we will show you what steps to take. These are the warning sounds you must recognize. First, the attack warning. If an attack is expected, the sounds will sound a rising and falling note like this. Next, the fallout. When fallout is expected, you will hear 3 bangs in short succession. They will be sounded by means of maroons like this. Or you may hear 3 gongs like this. Or 3 whistles like this. These all mean that fallout is expected. Warnings of the attack and of fallout will also be broadcast. When the immediate danger of air attack or fallout is passed, the siren will sound a steady note like this. Here are the warning sounds again. Attack. Fallout.
Here is a reminder of what the air attack warning sounds like. This is the sound. When you hear the attack warning, you and your family must take cover at once. Do not stay out of doors. If you are caught in the open, lie down. And now here is a reminder about fallout warning. When fallout is expected, you will hear 3 bangs in short succession, like this. In some areas, the warning may be given by means of 3 gongs, like this. Or you may hear 3 whistles, like this. All these 3 types of sounds indicate that fallout is expected. When you hear them, you must stay in the safest position in the house. Keep the door shut. Do not go outside the house until you are told it is safe. Here is the all clear warning. When you hear this sound, you can leave your cover. But keep listening for further warnings. You must now choose a room in your home which will give the best protection from fallout. If you live in a house, the safest place is the ground floor or basement. Choose a room with the smallest amount of outside wall. The farther you are from outside walls and the roof, the better the protection. If you live in a block of flats, which is more than 5 floors high, it is important not to use the top 2 floors. The safest places are inside houses away from outside walls and windows. If the block is 4 floors or less, the best place for a fallout room is the basement or ground floor. If you live too high up to be safe, you must make arrangements now with your neighbors in the lower floors, or make some suitable arrangements to shelter with someone close by. If you live in a 1-story house, like a bungalow or prefab, the building itself will not give you much protection. So the best thing is to make arrangements now to shelter with someone close by. If this is not possible, look for a space in your home which is farthest from the roof and the outside walls. Later, we shall be telling you how to strengthen and improve your fallout room. have told you how to choose a fallout room in your home. The best place is farthest away from the roof and outside wood. Your fallout room will protect you, but you will make it even safer by strengthening a small part. This part will be your inner refuge during the worst of the attack. Making a refuge is not difficult. The main things you will need are shovels, boxes, cartons or large plastic bags, earth or sand. Start collecting them now. These things may also come in handy. Hammer, saw, screwdriver, nails, screws, string or thin rope, scissors or pencil. One idea is to make a lean-to of wood, resting against an inside wall. Strong boards or doors taken from their hinges like wood. Stop them slipping down the wall by fixing them to the floor with a strip of wood, like this. Then cover the wood with bags or boxes filled with some heavy material, like sap, earth, books, or rolled up clothes. Don't forget to fix the bags and boxes so that they don't slip off. Across the two open ends of your refuge, you should make thick walls of bags and boxes of earth or sand, or heavy furniture packed tightly with heavy material. Don't forget to leave an easy way into and out of your refuge. Next, a cupboard under the stairs. That is another good place for a refuge. Put boxes of earth or sand on the stairs and along the walls of the cupboard, like this. If the stairs are on an outside wall, make the wall thicker with bags of earth or sand. Stack the bags up to a height of about 6 feet. Here is another idea. Use tables, if they are strong and large enough for you and your family to shelter beneath. Make solid sides around the tables out of heavy furniture, boxes filled with sand, earth, or books. If you can, lay strong boards or doors across the top and cover them with bags of heavy material. This will make a good roof over your refuge. If you live in a caravan or other building of lightweight construction, which provides you with very little protection against fallout, your local authority will be able to advise you on what to do. Whatever type of refuge you have, the main thing to remember is that the more heavy material you have around you, like earth or sand, the more chance there is of safety. Start looking now for materials for your fallout room and inner refuge. Here is a list of things and some ideas for you. Bricks, concrete blocks, bags or boxes filled with earth or sand. If you cannot get hold of sandbags or boxes, try travel bags, haversacks, suitcases, pillowcases, or anything which will hold sand or earth. Strong pieces of wood, heavy furniture, doors taken off their hinges. All these things can give you good protection. Think about it and make plans now. Decide what you already have in your home that will be suitable for making a refuge. Decide what you may need to bring into the house: earth, bricks, sand, etc., to strengthen it. Decide where you will store all these materials, so that you will know exactly where they are when you need them. You can use these materials like this for thickening the floor above your fallout room, for building your inner refuge, for blocking windows, doors, halls, or passages, for thickening outside walls. All these materials can save your life. If you have taken the advice we've been giving you recently, you will by now have chosen your fallout room and gathered your materials for an inner refuge. The time has now come to make everything ready for you and your family in case an air attack happens. This does not mean that war is bound to come, but there is a risk, and we must all be prepared. So don't waste time. Start now. To help you, we will remind you once again about choosing a fallout room and an inner refuge. First, choosing a fallout room. That should be a room in your house which will give you the best possible protection from fallout. A room that is farthest from the outside walls in the room, or one with the smallest amount of outside wall is safest. Whatever room you choose, remember that the further you can get away from radioactive dust in or around your home, the safer you will be. So in a house, the safest place is the ground floor or basement. In a block of flats, do not shelter in the top few floors if the block is 5 floors high or more. Go to the lower floors, ground floor or basement. The central corridors will give good protection. If you live in a bungalow or similar one-story home, it will not give you much protection. If you cannot make alternative arrangements, choose the safest place, which is the space farthest from the roof and outside wall. And now a reminder about your inner refuge. We have told you that your fallout room should be the safest place in your home. Even this is sometimes not safe enough, however, particularly for the first 2 days and nights after an attack, when the danger from radiation could be critical. So you need, inside your fallout room, an inner refuge, a fortified area to give you greater protection during the worst of the attack. The inner refuge should be thickly lined with dense materials to resist radiation, away from outside walls if possible. Now for its construction. Make a lean-to with wood, resting against an inside wall. Use boards or doors taken from their hinges. Stop them slipping down the wall by nailing a strip of wood to the floor like this. Cover them with dense material and fix some rope around it so that it won't slip. Partly close the open ends, leaving an easy way in and out of your refuge like this. Another good place for a refuge is a cupboard under the stairs. Reinforce the stairs and the side like this. If the stairs are on an outside wall, stack up containers of earth or sand to make the wall thicker to resist radiation. If you've got tables large enough to give you and your family sufficient shelter, use them. Make the sides solid with heavy furniture or boxes of books or sand. Reinforce the top with strong boards or doors and cover them with dense materials. More details are given in the booklet, Protect and Survive. If you haven't got one yet, get one from the post office now. And start right away making your home and your family as safe as possible from nuclear attack. Start now on your fallout room and inner refuge. Thicken the floor above your fallout room. Start blocking windows, doors, halls, passages. Thicken the outside wall of your fallout room. Fallout dust gives off dangerous radiation. It cannot be seen or felt. It has no smell. Anybody staying within reach of fallout for too long can fall ill or die. So you must keep away from fallout until it is safe. And this may mean staying in your fallout room for up to 14 days. Prepare yourself for this now by storing all the things you need. Put them in your fallout room or stacked up within easy reach close by. Here is a list of the most important things you will need. Drinking water. Food, mostly in tins. Portable radio and spare batteries. Tin opener, bottle opener, some cutlery and cloth. Warm clothing. And now here is a list of some things which will make living in your fallout room much more comfortable. Bedding, sleeping bags, portable stove and fuel, saucepans for boiling water and cooking, torches with spare bulbs and batteries, candles, matches, table and chairs, toilet articles, soap, toilet rolls, change of clothing, first aid kit, household medicines and prescribed medicines, box of dry sand, cloths or tissues for wiping plates and utensils, notebook and pencil for messages, brushes, shovel and cleaning materials, rubber or plastic gloves, toys for children, books and magazines to pass the time, cloth and towels. Finally, don't forget your book, Protect and Survive. It tells you how to make your home and family as safe as possible. All the items we've just told you about are listed in it. A warning may come quite unexpected. We will now tell you what to do if a warning sounds when you are at home. And then we will explain what to do if you are out of doors. First, if you are at home. If attack is imminent, you will hear the attack sound like this. So take cover at once. Send your young children to the fallout room, then go quickly and turn off the gas and the electricity at the mains. Close down stove. Damp down fire. Shut windows. And draw curtains. Then go to your fallout room and stay there. If the fallout warning sounds are heard, they will be like these. You should now move yourself and your family to the safest area in your fallout room. That is, you should get inside your inner refuge and stay there. After 2 days, the danger from fallout will get less, but don't take any risks by contact. The longer you stay in your refuge, the better it will be for you. Listen to your radio. Stay where you are and keep listening to your radio. Now, this is what you should do if you are out of doors when the warning sounds. Take cover at once when you hear the attack sound. If you cannot reach home in 10 minutes, take cover in the nearest building. If there is no building nearby, try to find some solid cover. If there is no solid cover, lie flat in a ditch or a hole and cover your head, face and hands as fast as you can with some of your clothes. If you hear the fallout warning, seek the nearest and best cover as quickly as you can. But before entering the building or cover, brush or shake off any fallout dust you may have picked up and get rid of it. Change your outer clothing if you can. Stay under cover. When the all clear sounds, like this, it means that you are safe from attack or fallout for the time being, and that you can go out. But keep listening for further warnings, or to your radio for further advice. After an attack, you may have to stay in your home for about 14 days. So make sure to store plenty of water and food for your family. Water is more essential to life than food. You can live for a long time with a little food if you have enough water or liquids to drink. How much is enough? Well, each person should drink about 2 pints a day. So, for 14 days, 3.5 gallons is enough for one person. But you should double this amount if you can. Then there will be some to spare for washing your face and hands. Keep drinking water in your fallout room. Store it in plastic containers with a screw top, or in bottles or jars covered to keep out dirt. Store the rest in kettles and saucepans and in basins in the bathtub. Try to keep some tins of fruit juice as well. Now, food. Stock enough for everybody for 14 days. You may not be able to cook anything hot, so buy food you can eat cold and that will not go bad. Buy food well wrapped or in tins. By the way, don't forget your tin opener and bottle opener. You will do best to buy lots of different kinds of foods if you can, so that you won't get bored with too much of the same thing. Stock up with meats, vegetables, fruit, tinned or powdered milk, and special foods for babies or invalids. You will also need some sweet things, like sugar or jam, and biscuits. Keep the food in a cool, dry place until you have to take it to your fallout room. Foods that will go bad quickly should be the first to be eaten. Try to ration everything so that it will last up. nuclear explosion produces intense heat. This can get through unprotected windows and set fire in your home. But there are steps you can take now to cut down the risk. First, whiten your windows with white paint to reflect some of the heat away. This will cut down the risk of these fires. Then get rid of junk lying about in your attics and upper floors, especially old papers and magazines, which can catch fire easily. The heat from the bomb strikes at attics and upper floors most easily, and fires there are usually the hardest to put out, so pay particular attention to these places. In other parts of the building, clear away papers and magazines. Then net curtains and windows. And any old rubbish inside or outside your home which is likely to catch fire easily. Small fires can be put out easily if they are tackled at once. If they are left, they spread fast and soon get out of control. The fire brigade may not be able to reach you, and you will have to protect yourself without any help. So prepare now. If you have a fire extinguisher, keep it handy. Or a garden hose would be very useful. Keep buckets of sand and water ready on each floor. When you take cover in your inner refuge, you must not go outside until it is absolutely safe. And if the fallout is heavy, you may be in your refuge for quite a long time. Although the danger from fallout will get less and less as time goes by, you will never be able to judge for yourself how bad it is. Advice will be given to you on the radio, so keep listening. This advice over the radio and other instructions and news will be very important to you while you're cut off from the people living around. So make sure your radio is in good working order. And if you have a spare radio, keep it in your fallout room. Radios must be battery operated because your electricity may be cut off. So be sure to get some spare batteries. After a fallout warning, you have been advised to take cover in your inner refuge. The first 2 days will be the most dangerous period because fallout will be at its worst. So it is in your best interest to stay in your inner refuge the whole of that time, however cramped or uncomfortable it may be. But if you must leave the refuge to go to the lavatory, or to get more water or food, don't stay out a second longer than is necessary. In any case, don't go outside the fallout room at all. After 2 days, the danger from fallout will be less, but it may still kill you. So the longer you stay in your inner refuge, the better your chances are. Although it may be fairly safe for you to move about inside your fallout room, it certainly will not be safe for you to go outside the house until the radio tells you. So keep listening to your radio for advice. At first, you'll be told when you can go outside the house for a short time to get rid of lavatory waste and rubbish. Then, as the danger from fallout begins to pass away, you will be able to stay out for longer spells. There may still be a lot of fallout dust lying about, so be careful not to bring it back with you into the house. Keep a separate pair of boots or strong shoes for going up. Before coming in, take them off and wash or wipe, soles as well. It is also a good idea to wear rubber gloves while you are outside. Try to keep the younger people indoors as much as possible. In fact, it will be far wiser for only people over 30 to work outside until things get better. And now a reminder of some of the things we have told you in earlier films. Fallout can kill, though you cannot see it, feel it, or smell it. There is danger outside, so don't go outside. Stay in your fallout room until you are told it is safe to come out. After an attack, fires will start in many places. The fire brigade may not be able to help everyone, so it might be up to us to tackle the fires in our own homes. Here is some advice on how to do it. Make sure that you have turned off gas and electricity at the mains. Don't smoke. Then start checking for fires. Start at the top of the house. Check roof space and every room, putting out fires before they get out of control. Small fires can be put out quite easily if they're tackled at once. If they are left, they spread quickly and take hold. Use water from the tap to reserve. Earth and sand are also useful. Put all the members of your family to work putting out fires in the house. When you are satisfied that the inside is safe, check the outside of the house and make sure that you are safe from any fires which have started nearby. When you have seen to your own household, help any neighbor in need. If you have used any of your precious drinking water to fight fires, make good your reserves. Fill up all your containers again and put covers on. Turn off your water supply at the mains. It may become contaminated. If your house is damaged, you may have a little time before a fallout warning to carry out minor jobs to keep the weather out. Curtains or sheets may be used to cover broken windows or holes. Then listen for the fallout warning. If it comes, take cover in your inner refuge and stay there. Earlier we told you what to do to prepare emergency backup arrangements in or near your fallout. It will not be easy to easily clean in shelter conditions, mainly because it is unlikely that there will be any water to spare for washing or for flushing the large. But cleanliness is essential to prevent sickness, and here are a few simple rules to help you. All toilet containers should be covered when they're not in use. Pour in some disinfectant. It will cut down the smells and keep off flies. When you have used the bucket lavatory, wipe your hands with toilet paper soaked in a little mild disinfectant. Throw the paper into the container and put the lid on. Keep an eye on small children. and see that they do the same as you to keep cool. Don't let the bucket get too full. If you have lined it with a plastic bag, tie the neck tight before lifting it up. And put it in a separate dustbin well away from the fall. Put a fresh plastic bag into the bucket with a few drops of disinfectant. Cover the bucket with a lid. When it is safe to do so, take the dustbin and its contents outside the house. Remove the waste and bring the empty bin back. Food scraps, empty tins and other rubbish should be wrapped up tightly in newspapers and put in a separate dustbin. Keep the lid on. If you have got only one dustbin, use that for toilet waste only. Put all other rubbish separate in plastic bags or paper until you can take it outside the house. Keep your hands as clean as possible. Wear rubber gloves for dirty work. Try to avoid touching food with your hands as much as possible. Keep your knives and forks, plates and cups, etc. clean. Dry, clean sand is quite good for this. After an air attack, your water taps may run dry, or the water in them may be too dangerous to drink because it has been poisoned by chlorine. So your life may depend entirely on what you have stored. Keep it clean by covering the container. Its main use is for drinking, but use it sparingly. For each person, you should have stored at least 2 pints for each day. Don't waste water on washing or anything else. If you must use water for cooking, use as little as possible. If you heat cans of food in a saucepan of water, don't throw the water away. It can be used over and over again. By the way, make sure you pierce the top of the can before heating. Dip your dirty knives and forks into the pan while the water is still hot. Water is life. Safe. You should by now have built up an emergency reserve of tinned food or other foods that don't go on quickly and that can be eaten cold. Keep your food reserves in your fallout room. And remember to keep them well covered to protect them from fallout dust. There might be fallout dust on the packaging. Take care this does not get into the food. So wipe the tins, packets and bottles. You may not be able to replace your stocks of food for a long time, so make them last. Most of the time, you'll be resting your fallout work, and you won't need to consume much food. Eat the smallest amount you can get by, and plan meals carefully so that there is no waste. And remember, keep your food covered from falling. Wrap open tins and loose tins. Prepare small amounts at a time. You may not be able to replace your stocks for a long time, so ration food carefully. After an attack is over and the all clear has been sounded, arrangements will be made as soon as possible to treat any people who are ill or injured. Listen to your radio. Details will be given about what to do, when to do it, and how. If anyone dies while you are kept in your quarters room, move the body to another room in the house. Label the body with name and address, and cover it as tightly as possible in polythene, paper, sheets, or blanket. Tie a second card to the cover. The radio will advise you what to do about taking the body away for burial. If, however, you have had a body in the house for more than 5 days, and if it is safe to go outside, then you should bury the body for the time being in a trench or cover it with earth and mark the spot for burial.
Wandering asteroid. Moon and planet such as our own. Everything in space, Earth included, received. We don't worry about the small amounts of natural background radiation. But to safely handle larger amounts, highly radioactive particles 1/100. But in 2 weeks, it's only 1/1000. With this decay rate in mind, consider radioactive fallout might be cut like that for a maximum. Within an hour, fallout would be a serious problem in the vicinity of explosions which occur on or near the ground. 5-7 hours after the attack, the fallout area covers more and more of the country, and the prevailing wind expands the fallout to ground level. 24 hours. 48 hours. Without shelter, millions would face death. A few days later, those who have taken shelter will survive. In many areas, people didn't even leave shelter for brief periods of time to carry out important tasks. Within 2 weeks, most people can leave their shelters for longer periods as the radioactivity decays to lower levels. The lesson is obvious. We must shield ourselves from radiation through the dangerous period. To do this, we need more than knives. Fortunately, we have another ally. Distance. The greater our distance from the fallout particle, the less radiation we receive. You would receive less radiation in the middle of a tall building than you would receive on the top or bottom floor, because there would be more distance transportation between you and the source of the radiation. The fallout particles which would cover the roof and ground around the building. Only an insignificant amount would get inside. And finally, along with decay rate and distance, we have still another very important ally. Man. When highly radioactive fallout covers our immediate area, we can shield ourselves through the most dangerous period by using the sheer weight of any material. But the protecting material must be heavy. To shield out some 99% of the radiation, you would need about 5.5 feet of wood, or 2 feet of earth, or 1 1/3 feet of concrete, or a half foot of steel. Even though the thickness of these materials vary, they all weigh the same. Taking a house as an example, it offers a small amount of mass and distance from radiation, but not enough to protect an area of heavy fallout. The solution is plain. Fallout shelters are the best defense against nuclear radiation, whether in a home for a single family, or a large community like in an apartment building. They offer the kind of protection from radiation you would probably need in the case of a nuclear attack. But the best shelter would be worth it unless it was used. Most people find it hard to understand how the island is visible rays which cannot even be felt. Again, let's see what happens when radiation penetrates the body of the cancer cell. What is a cell? And what happens to it? It's a simple organism which reproduces itself by dividing. Our bodies are... The key then is the amount, the total dose of radiation received. We measure radiation the same way speed is measured by a speedometer. Only instead of a speedometer, we have a rate meter. And instead of miles per hour, we measure the rate in revolutions per hour. We need another device, called a dosimeter, to record how much radiation a person has accumulated over a period of time. In the same way we record accumulated distance in miles, the
The dosimeter records accumulated dose in range. With this in mind, let's return to background radiation. In an average lifetime, a person might expect to accumulate about 10 Roentgens from his natural environment. Not enough to affect his health. This made healthy person who needs medical care and may receive more than 300 Roentgens within a few days. 300 Roentgens in the same period would cause severe radiation sickness or possible death. And as we go beyond 300 Roentgens, the danger of death increases rapidly. So now we've seen why shelter is vital. The difference between accumulating a large dose because of little or no fuel and a small dose because of adequate fuel is the difference between death and life. No clothing, of course, could possibly provide enough fuel. However, if you were to be in the open during fallout conditions, clothing would keep the particles touching your skin. There is no such thing as a fallout suit, but ordinary clothing would help until you reach the safety of the shelter. Then the fallout particles can be brushed off and outer clothing removed. If fallout settles on your food, the food itself is not harmed, since radiation damages only living tissue. And you can easily decontaminate it using almost the same methods you use in everyday food preparation. Actually, even if you accidentally swallowed some fallout particles, it wouldn't kill you. The effects, if any, probably wouldn't show up for you. Still, there is a possibility of long-term events, such as shortened lifespan, cancer, or hereditary damage. It's wise to remove the radioactive particles by frequent washing, wiping, or peeling. But it's vital to remember this. Neither water nor chemicals can destroy radioactivity. The fallout particles can only be moved or washed away. Only time will move their motion. And what of water? Well, here again, the same rules apply. If necessary, you could drink water containing fallout particles without worry or immediate harm. The chances are you wouldn't have to for long. But water helps to wash itself through the natural processes of sedimentation and filtration. And swiftly moving rivers like this would carry most fallout particles downstream. In still waters, most particles would settle quickly to the bottom. Others might remain suspended in the water for a long time, while a small percentage of radioactivity would dissolve. The normal processing of a water treatment plant would make it safe for drinking water. And water coming from a covered well would be safe from radioactive contamination. There is no problem with breathing, for air is not contaminated once the fallout is on the ground. Fallout is not a poison gas. Separation is needed in the shelter, as simple as burning fuel quickly on a ventilated pipe to keep fallout particles from entering the pipe and getting inside. Of course, surviving a nuclear attack means more than just waiting in a shelter for radioactivity to decay and take life. Survival, reconstruction, and recovery
bomb. After a nuclear attack, we would first use existing food supplies to shelter, market, and surface food chains. When fallout had decayed to safe levels, people could begin to work in fields for a limited period of time. In a few areas, the land would not be suitable for food, but such crops as cotton could be grown. Crops for human consumption would be grown in areas that had received the least fallout. The reason we would be able to grow and eat food like in the Midwest is because where radioactivity in soil and plants is extremely low. And so, if nuclear attacks should ever come, in spite of every effort to avoid it, we must be able to survive and rebuild for the future. But survival can only come through knowledge. The basic facts we must all know are relatively simple. First, there is nothing new about radiation. It has always been with us. What is new is the vast amount we would be exposed to as a result of nuclear explosion. Much of this danger would come to us in the form of fallout. But we are not without personal weapons or defense. One of these is time. Radiation decays, so we will not have to make maximum precautions to inject it. Another defense is distance. Radiating particles 50 feet away from us would not affect us as much as particles a few feet away. And our third defense is measure. Any material with enough weight to keep the penetrating rays from hurting us. The greater the weight of the material between us and the particle, the safer we will be. The best way we can use all three weapons of defense is with an adequate shelter, thick enough to shield off a good part of the radiation until it has decayed to safer levels. When radiation attacks, the cells of our body are damaged. Most of them can repair themselves if the total dose over a period of time is not too high. Even though the rays penetrate our bodies, causing damage, they will not infect us and make us, or anything else, radioactive. That's why food remains good no matter how much radiation has passed through. Fallout accidentally swallowed with water or food will do you no immediate harm, but for long-term safety, it's best to wash, wipe, or peel the food and filter the water. Even if you were caught outside under fallout conditions, ordinary clothing would keep the radioactive particles from touching your skin, but you would still need to find shelter quickly. If we remember these facts, if we act on them intelligently, we can increase our chances of surviving nuclear attack. And the key to survival is adequate shelter. That is why the federal government has a nationwide fallout shelter program. The goal is adequate fallout shelter space for every man, woman, and child. And this goal can be reached. For with knowledge of radiation, we can face the facts about fallout, take action to protect ourselves, and learn how to live in the nuclear age.
construction worker with the day off, standing up on his floor alone. Or a senior citizen catching up on his feet. Suddenly, something happened. Something that halts the normal routine for the day. War machine has become the target for nuclear attack. With the whole team on being attacked, we must stop them. Be prepared to take something, most likely an atomic bomb. What will we do there? How will we react? How will you adjust to the new and different way of life in the encounter? Whether you will In our projected situation, a nuclear detonation has taken place several hundred miles from this base. Dangerous radioactive fallout is being carried downwind from Waterloo. This is one of several public alarms. Commonwealth Barnes is said to be sheltered management force putting down instructors who have received federal sponsored training. Barnes knows the importance of having attention within the shelter. In this shelter, each person is given a registration form which will indicate important data about them. The form provides a ready means for retrieving the skills of each person, which may be used in the various joint functions. Not all shelters will be organized or operated in the same manner. Procedures will depend on the size of the shelter, its floor plan, facility supplies, and the availability of trained technicians. Where the number of occupants is large enough, a supervisor for each shelter function may be needed. Members of the community who have prepared themselves with training in civil defense adult education courses, or in such areas as disaster aid or medical shelter, can provide valuable guidance in the shelter security. Outside the main base is a circular registration form that sees it as an Red Cross home nursing center. In the absence of professional medical personnel, Manager Barnes assigns her the job of nurse. A section has been set aside at the first aid. Different places will set the medical supplies and arrange facilities for care of the sick and injured. Is Hal Benton, construction worker and former military policeman, going to appointment of security before? Necessary function in many situations where many people are confined in a limited area for a length of time. Seeking solace in this time of trial, office worker Bert James finds in himself a native ability to comfort others, to bring them spiritual guidance and help. The alert shelter manager is always on the watch for the emergent needs to help reduce the burden of shelter provision.
as well off taking our chances on the outside. We're lucky we have people here who know how to handle it.
Remember that life in the shelter are not connected to their normal conditions. Suppose in our building there had been no shelter, no plan, no organization, no trained personnel. Suppose no one was there who understood the nature of the cover the shelter occupants took. Suppose no one had known when or if ever there would be hope of returning to a life previously known. In the perilous world of this nuclear age, shelter is critical. Community shelter planning will result in the best use of our shelter facilities. Should the siren sound, would your community be ready with the kind of shelter preparation just needs?
Man also progresses, but along the way, times result in dangerous changes in our environment. Unchecked, these changes may threaten our very survival. Man must stop mishandling of nature, work toward a future with clean air to breathe, clean water to drink, uncontaminated soil in which to grow the food we need. Oxygen sources like these, vital to our environment, must be protected. This is our deep commitment to the future. How do we meet it? The science of the peaceful uses of atomic energy is one of the ways man is responsible to fight, preserve, and restore his environment. The atomic energy system, from its inception, has had a vigorous program in environmental research. The application of atomic energy to meet environmental objectives moves in two directions. First, supplementing the conventional power plants that pollute the atmosphere with clean atomic power stations. Secondly, use the atom as a research tool to study our environment, especially the burdens placed on the environment by modern industry. This challenging work offers many exciting career possibilities for scientists and technicians. Power production is one example. Electric power requirements in this country are doubling about every 10 years. Sometimes the heavy demand exceeds the supply, causing power blackouts and brownouts. The basic principle of power production is simple. A heat source there is another heat source, the atom, the nuclear fissioning of uranium. The discharge of noxious chemicals into the atmosphere is one thing coal and oil burning power plants have in common. Atomic power plants, on the other hand, don't release smoke containing such contaminants that pollute the atmosphere. Both conventional and atomic power plants discharge some excess heat into adjacent waterways. These thermal effects must be controlled and minimized. Methods are being developed at the giant cooling towers and man-made lakes. Whatever the heat source, water is converted into steam, which turns the turbines, which drive the generators. When the steam leaves the turbines, it must be cooled and condensed back to water and returned to the boiler. The cooling water does not make contact with the radioactive core. Cool water is usually taken from rivers, lakes, or the ocean. At atomic power plants, the water is pumped through the condensers and returned to its source as warmer water. Although so far, no significant detrimental effects of warm water on fish and other aquatic life have been found in the vicinity of nuclear power plants, thorough investigation will continue in order to assure that environmental impact will not be excessive when weighed against man's growing need for electricity. But of course, slightly warmer water may be used beneficially for agriculture and even recreational purposes. Future, more efficient nuclear generating stations, such as the breeders, will release less heat per kilowatt. However, nuclear power plants do release very minute quantities of radioactivity into cooling waters and into the atmosphere. But federal standards carefully and conservatively regulate such releases to protect the public. In actual practice, the amount of radioactivity released is held to only a very tiny percentage of the amount permitted by the standards. The natural background radiation you would receive from taking a plane ride across the country or from spending a summer in the mountains would be about the same you would receive if you lived next door to an atomic power plant for an entire year. One of the reasons for the success of our agriculture was the use of insecticides, resulting in more abundant crops due to the elimination of pests. But unfortunately, insecticides can be harmful to livestock and wildlife. However, insect control is a necessity. So, by using atomic energy as a research tool, experiments are underway at a number of universities to develop insecticides which will do their job without causing side effects, as far as the food chain, from plants to animals to man. At the University of California at Riverside, the Department of Entomology is doing decisive research work in this area under the guidance of scientists such as Dr. Roy Bakuto. The purpose of these scientists is to aid in the development of insecticides which are selectively active. To put it simply, the goal is the creation of insecticides that control pests but do not harm humans or livestock. Well, how does nuclear energy come into the picture? Radioactive power is the research tool that traces the effectiveness of the insecticide being tested. 2 samples of insecticides are being tested. Sample A, used as a control, is a compound currently on the market. It is poisonous to warm-blooded animals. The new compound B is selectively toxic to insects. It therefore may be used without harmful effect to our environment. Both samples were previously tagged with radioactive carbon. The presence of radioactivity is detected with the radiation counter. The bottle caps have to be removed to obtain a measurable radiation count. Here we see some highlights of the experiment. This mount fed with compound A, currently used toxic insecticide, is placed inside a metabolism chamber. The second mouse is given a sample of compound B, the new insecticide. Into another metabolism chamber. The test animals spend predetermined time periods in the metabolism chamber. At certain intervals, urine specimens of the two test animals are taken to determine the relative metabolizing action of samples A and B by the test animals. Specimens are placed into this radiation counter to measure the radioactivity. Now a tiny amount of both samples is placed on this chromatography plate. The compounds will move to different places on this plate. Their position will indicate the nature of the compound. Slight radioactivity of the compound makes it possible to trace them on a photographic film for easy visibility. Thus, atomic energy, through the position of the spots, helps the chemist reach the conclusion that compound B, the new insecticide, is indeed less dangerous to warm-blooded animals than the sample taken from the currently used insecticide. Although it is illegal to dump oil into coastal waters, some ships still flush out their fuel tanks, discharging oil into coastal regions, usually at night. As a result, oil slicks may be washed up on beaches, destroy marine life, and even cause fire. Since our bodies of water are already burdened with more waste material than they can manage, the Coast Guard has added another duty to its routine patrol: protection of the marine environment. When an oil slick is located by the helicopter, a Coast Guard cutter is dispatched to take samples. Scientists using atomic techniques will be able to relate the sample to the polluting ship. Samples for comparison can be taken from ships suspected of dumping the oil in that area. The link between the oil slick and the suspected ship can be established by a novel use of atomic energy called neutron activation analysis, which produces atomic fingerprints of the samples under investigation. A small nuclear reactor is used for the next step. The oil samples shoot in the ocean, as well as the samples collected from the suspect ship are made radioactive. Then, radiation chemicals used to produce a profile of each radioactive sample. The information is also recorded on a printout. The atomic fingerprints are compared. In the event that an oil sample from the suspected ship matches one of the oil samples retrieved from the ocean, the authorities can be reasonably sure who caused the pollution, and existing laws can be enforced. Wave energy and strong ocean currents often cause beaches and sandbars to appear and disappear. Beach erosion is a constant threat to recreation areas and homes near the sea, and sand eventually clogs channels. In some cases, constant, expensive dredging is required to clear harbors and channels for shipping. In order to learn more about the mysterious movements of the sand and perhaps help prevent our valuable beaches from eroding, the Atomic Energy Commission, working near a research center at Oak Ridge National Laboratory, is studying how the pounding of the waves and currents above affects the movements of the sand below. These boxes contain sand packed with tiny quantities of radioactive gold, gold-tagged sand at certain predetermined locations. Plastic bags will disintegrate in salt water. Tagged sand is placed along the beach according to a predetermined pattern. These experiments are conducted at Point Mugu in California. Deposits are made also below the waterline. Frogmen place stationary radiation markers to help measure the radioactively tagged grains of sand that are spreading along the ocean floor. This roller-shaped apparatus, called the ball, is a highly sensitive mobile radiation counter. It is used to survey the gold-tagged sand. The study of one series of placements may continue for a week. It will decay and elucidate to make radiation undetectable. The ball is pulled along the beach through the water. The distance is up to 1,500 feet from the shoreline. The signals picked up by this atomic radiation detector accurately reproduce data indicated by this map, showing for the first time the movement of the sand under the sea. Rivers, by their very nature, have their own cleaning mechanism. But ever-increasing amounts of waste dumped into rivers often exceed the flowing water's capability of self-purification. With the use of AEC-produced radioisotopes, the Georgia Institute of Technology is studying the problem. These men are preparing atomic tracers for use in this research work. Bottles containing the atomic tracers, red dye, are emptied into the flowing water. The red dye is used so that the movement of the radioactivity can be easily followed. Samples collected at various points downstream will be taken to the Institute for assessment. The tests will indicate the decrease of radioactivity of the effect. These data relate to the amount of oxygen absorbed from the air and will give a much more precise picture of a flowing stream's ability to purify itself. That is, to absorb oxygen on which the very life of the river runs. The findings will aid in the proper placement of sewage plants and industrial facilities along rivers and help determine permissible waste output. Industrial wastes are killing fish in the Great Lakes. In order to fight the drought, scientists are determining which pollutants are mainly responsible. They collect fish throughout the Great Lakes. The case history of every fish is fed into a computer. Then the vital organs of the fish are removed for analysis. AEC's Argonne National Laboratory, in cooperation with the U.S. Bureau of Fisheries, is trying to isolate the fish killers. Neutron activation analysis is used to identify poison elements, such as mercury, copper, zinc, and phosphorus, shown here in their specific profiles, their telltale atomic fingerprints. This information helps to provide a picture of the dispersion and type of the pollution in the Great Lakes. Belching batteries of smokestacks used to be the hallmark of industrial success. Today, they are signposts of deep concern to ecologists and the medical profession. AEC's Brookhaven National Laboratory, in conjunction with the National Air Pollution Control Office, took off on an airborne program of diagnostic studies to determine the extent and composition of typical plumes and their effects on the surrounding area. Industrial plumes contain polluting sulfur dioxide. In this compound are naturally varying amounts of two types of sulfur. The ratios of the two types of sulfur can be measured by means of stable atomic isotopes. This information helps determine the intensity and dispersion of corrosive smoke particles and predict pollution patterns over our cities. The planes fly through the plumes at predetermined wide knowledge of pollutants and industrial smoke. Such information is important in pollution control and will help decrease the damage to man and vegetation in the environment. This geodesic dome, the climatron, houses a tropical forest in the center of the United States, the Missouri Botanical Garden in St. Louis. Experiments in the fight against pollution are conducted under the guidance of Dr. David Gates, using radioactive tracers to study the way plants convert carbon dioxide into oxygen, and to what extent plants can absorb substances such as sulfur dioxide, one of the most dangerous pollutants of coal-burning furnaces and automobiles. Photosynthesis is a key link in the chain of life. The functioning of the green leaf and other green plants is responsible for the survival of the human race. Changes in the environment due to pollution would jeopardize the process of photosynthesis. So it is essential to investigate the effect of pollution on the plant life of the world. The studies conducted here with the help of the atom yield valuable answers. Other answers will come from experiments in this forest at AEC's Oak Ridge National Laboratory under actual outdoor conditions. The tagging capability of radioactive cesium is used to learn more about the growing process of plants and trees, to help determine the flow of elements through the forest and its grasses, shrubs, and trees. And now, take a look at the possible future of the atom's fight to help our environment. Perhaps underground atomic explosions could provide safe storage space for waste materials. New types of power plants employing nuclear fusion, producing temperatures hotter than the sun, hopefully someday to supply almost limitless pollution-free energy for the world of tomorrow. And perhaps the same energy in the form of the fusion torch would reduce the vast amounts of industrial and household wastes to their original elements, making the continued recycling of our resources possible. Yes, the fight for the preservation of the Earth's environment goes on. One very valuable weapon in the arsenal of the ecologist is magic of the atom.
This, our country and all its people, could be in danger of nuclear attack. In minutes by enemy missiles. In hours by enemy aircraft. Our cities, our farms, our factories. Prime targets would be our air bases. With all our aircraft on the ground, our weapons of interception or retaliation not instantly available, we might face another and infinitely more costly Pearl Harbor. To avoid surprise disaster, some of our aircraft must always be in the sky or on the alert, carrying nuclear weapons. These weapons are always unarmed. They will be armed only following a decision by the President of the United States. Only these ready aircraft with nuclear weapons can form our first-line deterrent force in peacetime. Our sure striking force in case of attack.
we American people understand and accept this necessity for our survival. But we want to know the facts about one question. Do we live in danger of nuclear explosion and radioactive fallout if one of these airplanes should crash or one of these nuclear weapons accidentally drop? To give you the facts, the United States Air Force presents This bomber carries a nuclear weapon. It is a well-designed, carefully maintained, skillfully flown airplane. But airplanes, just like it, have crashed and burned. There was no nuclear explosion, no radioactive fallout. These are the facts. The bombardier watches over controls as safe as human ingenuity can make them to prevent accidental bomb release. But nuclear weapons have been dropped inadvertently. There was no nuclear explosion, no radioactive fallout. These are the facts. And specially instrumented aircraft verify these facts in a continuing nuclear safety program that tests our nuclear weapons under controlled conditions that simulate every conceivable hazard. Vital to this nuclear safety program is Air Force Special Weapons Center at Albuquerque, New Mexico. Here, in ultra-modern laboratory buildings, work scientists in and out of uniform. They work with the incredibly complex equations of nuclear physics, which derive from Einstein's famous relationship of mass to energy. These cryptic figures, programmed into lightning-fast computers, are the theoretical base upon which these scientists, together with those of the Atomic Energy Commission, can build nuclear weapon safety. By research, design development, and laboratory test, they ensure weapons not yet built against accidental nuclear explosion. They have been doing this successfully since 1945 in safety conferences with other Defense Department agencies and the Atomic Energy Commission. In 13 years, there have been a few accidents, but not one has resulted in nuclear explosion or radioactive fallout. These are the facts. What keeps our nuclear weapons safe? To understand why there has never been an accidental nuclear explosion, you must first know how these explosions can be produced, the general principles of nuclear explosion. Any explosion is the result of a very rapid release of a great amount of energy. Conventional explosions result from the rearrangement of whole atoms in some explosive material. For example, in TNT, the rearrangement of whole atoms of hydrogen, carbon, nitrogen, and others produces explosions. On the other hand, nuclear explosions result from rearrangement within each atom. This may be a joining together or fusion, as in Wasteland, or the splitting apart or fission, as in an A-bomb. At present, an H-bomb explosion starts with fission. So the splitting of the nucleus of the atom is the basic principle of nuclear weapons. All matter is composed of one or more of the 100-odd elements. Of these, the atoms of the metals uranium and plutonium can be most readily fissioned to cause nuclear explosion. These elements are mildly radioactive. They emit short-range, low-penetration alpha particles while in their unfission state. These alpha particles do not have the harmful effects of the longer range and stronger gamma rays, which are given off by certain elements such as radium or by the products of nuclear fission. The atoms of uranium and plutonium are among the heaviest. Heavy because the nucleus of each atom contains large numbers of the fundamental particles called protons and neutrons. When a free neutron hits this nucleus, it splits into two parts, releasing more neutrons which may go on to split other nuclei. The resulting fission products become highly radioactive, emitting the long-range and dangerous gamma rays. The split nucleus weighs less than the whole, and this difference in weight is released in the form of energy, nuclear energy. After fission, harmful gamma radiation. Before fission, innocuous alpha radiation. To build up a nuclear energy release, the fissionable material must be of a certain size, shape, or density. Then one of the neutrons escaping from a split atomic nucleus will, in turn, split another, and a chain reaction is set up. The mass is now releasing nuclear energy, but not quickly enough to cause a nuclear explosion. This condition is called critical. If the mass is now suddenly increased, so that more neutrons are trapped each time an atomic nucleus is split, a multiplying chain reaction is maintained. Now the mass is supercritical, causing a nuclear explosion. Density of the fissionable material can be as important as mass in building up a nuclear explosion. The same sphere can be compressed so that the atoms are closer together and neutrons split more atomic nuclei, making the smaller mass critical. If compressed still more, a multiplying chain reaction sets in, causing the mass to become supercritical in a nuclear explosion. Nuclear weapons make use of both of these principles. A gun-type device can increase the mass of fissionable material to a supercritical state instantaneously. One subcritical mass is propelled forcibly into another by an ordinary counter charge. The increased mass becomes supercritical. A multiplying chain reaction builds up until the nuclear explosion. Obviously, if any mechanical device keeps these two subcritical masses apart, the weapon is nuclear safe. Applications of this fact prevent accidental nuclear explosions in gun-type weapons. Another kind of nuclear weapon is the implosion type. It compresses the fissionable material to greater density to make it supercritical. To do this, the sphere is enclosed by a shell of ordinary explosive designed to direct its explosive force inward. This effect is called implosion. The detonators attached to the explosive are connected to a complex firing device, which can fire every detonator simultaneously. When all the explosive is detonated simultaneously, the nuclear material is compressed into a supercritical mass, which results in a nuclear explosion. Implosion-type weapons are nuclear safe because only the specially designed firing device can produce the simultaneous detonation of all the ordinary explosive, a deliberate effect possible only by the precise firing mechanism. Should a single detonator be fired accidentally, whether by malfunction, crash impact, or fire, the explosive would not provide the all-around compression necessary for implosion. Instead, it might push the nuclear material out of the shell, break it into small pieces, or even burn it. This unfissioned material emits only alpha particles because no nuclear explosion has taken place. These alpha particles do not penetrate the skin. The simplest precautions can prevent their intake into the body, and the simplest cleanup measures can remove them.
So you see, each type of nuclear weapon has its own safeguards against accidental nuclear explosion. These are the facts.
And they are based upon practice as well as theory. Specially instrumented aircraft fly the tests that verify what happens inside a weapon, what accident hazards the nuclear components may have to withstand. Nuclear safety is everybody's business. Although Air Force flies the test missions, scientists and technicians from the Atomic Energy Commission and other services man the test range and evaluate the findings of the elaborate instrumentation. Drop tests measure impact characteristics of various weapon types. They are made without nuclear components, so that this precious material is not wasted. They supplement the detonation tests that have been made with the complete nuclear weapon. Impact or shock does not cause nuclear explosion or radioactive fallout. What has exploded is the ordinary explosive, which is an essential part of nuclear weapons. The ordinary explosive in a nuclear weapon can be a hazard, exactly as in a conventional bomb. Depending upon the amount and location of the explosive, and the speed and height of the drop, we may experience a variety of ordinary explosions. Large ones, small ones, or none at all from impact of the bomb. Beside the hazard of impact, frequent tests are run on the hazard of fire. To learn what temperatures and pressures would be created inside a weapon by an aircraft fire, various types of bombs are subjected to a flame bath of burning fuel. Because fire would also destroy the precious nuclear material, it is replaced by instruments. Their readings are compared with known characteristics of the fissionable material to assure that temperatures higher than any aircraft fire will not set off a nuclear explosion. The characteristic white flame indicates that the ordinary explosive is burning in the weapon. Sometimes the explosive detonates because of close confinement and intense heat. The effects of such explosions are measured and compared with those in an actual nuclear weapon. Fire and ordinary explosives do not create the conditions necessary for nuclear explosion. These are the facts. And on the vast desert ranges of the Atomic Energy Commission, the facts are verified by safety testing live prototypes of all new weapons before they go into production for our stockpile. The tests are costly in money and manpower, even more costly in the fissionable materials on which our nuclear strength depends. But they do provide insurance against nuclear accidents, which make them a bargain at any price. Some take place deep in the earth. Fantastically complex instruments replace the five senses. They record what happens when some of the explosive that surrounds the nuclear material of a new weapon is deliberately detonated. They record only an ordinary explosive blast. A random detonation has not created the implosion which would compress the nuclear material to a supercritical mass. There was no nuclear explosion, no radioactive fallout. Each new design must be proved nuclear safe, able to withstand accident, fire, or random explosive. Other tests with nuclear weapons are made above ground. These are also designed to test the nuclear safety of new weapon types by intentionally detonating the explosive which surrounds the fissionable material.
Sometimes these tests also provide data on the side effects to be expected if the fissionable material is broken up by the explosion. Air samplers and test pads are used to gauge the area, intensity, and duration of these side effects. In this way, they learn not only what does not happen when a charge is deliberately fired, but what does. The explosive does break up the nuclear material and scatter parts of it over a small area. This fissionable material is mildly radioactive. If the explosion or fire should suspend any of this material in dust or smoke, it should not be inhaled or otherwise taken into the body in quantity. That is why the trained monitoring and cleanup crews may wear respirators until air samplers or alpha counters have determined that no injurious concentration exists. The alpha particles emitted do not penetrate skin or clothing, so this material is harmless when on the ground. Only simple cleanup measures are necessary, plus an effort to find and save the valuable material. The findings from all tests set up to measure possible radiological hazard are no external radioactive hazard from material on the ground, slight radioactive hazard from prolonged inhalation of material suspended in a small area near the accident, but none from the short exposures necessary for firefighting, rescue, or cleanup of the small area involved. These are the facts. Facts that have dispelled the fearsome myths about accidents involving nuclear weapons. For anyone near an accident, whether or not the crashed airplane carries a nuclear weapon, here are the safe and simple rules. Stay away from the crash unless you are needed for rescue. Bystanders endanger themselves and hamper others. To be safe, keep at least a quarter of a mile away from any burning airplane. At this distance, you are safe from the flames, which may explode the jet fuel, from detonating explosives, and from flying debris. These are the real dangers in rescue or firefighting, as they have always been. The trained men who bear these responsibilities know how to do their job and get quickly away from all these hazards. After the emergency is over, the area is monitored for radioactive material, and, if necessary, cleaned up by specially trained teams. Other specialists care for burned or undetonated pieces of ordinary explosive. Until this is done, access to any crash area is controlled to prevent accidents and speed up the work. The tests you have seen have proved the safety of our nuclear weapons program over and over again. But the grim reality is the payoff. How safe is a nuclear bomber coming in for a crash landing? Detonation of the ordinary explosive in the weapon cause nuclear explosion or radioactive fallout. The safety that was designed in during research, built in during development, proved in the laboratory and on the range, has withstood the ultimate tragic test. These are the facts.
They prove that you, the American people, can stay both safe and strong. Safe because the weapons your Air Force must carry have been tested nuclear safe. The possibility of an accidental nuclear explosion is so small as to be practically non-existent. Strong because an Air Force, nuclear-armed and combat-ready, stands guard against surprise attack. Under this shelter, you and your family may live in peace, free from the fear of nuclear accidents. The threat of disaster is never pleasant. For a long time, schools have been improving ways of protecting children from the kinds of disasters and accidents we have come to expect. These safety measures are essential. Today, however, we are threatened with a new form and magnitude of disaster. For this is the age of the atom. So long as we are confronted with this unprecedented threat, protection of our children must be a basic goal of every educational program. We can achieve this goal only by undertaking a comprehensive civil defense program in all of our schools. Protection from nuclear attack is possible. Local conditions will dictate the courses of action. There is a general concept for every school system to follow in developing a civil defense program. First of all, the general objectives and main features of the plan must be carefully worked out by the superintendent for presentation to the school board.
We presented this program to you a week ago at your meeting, and I need hardly tell you that this proposal to expand our school protection program was worked out with the close cooperation of Mr. Miller, our city civil defense director. The program consists of two main parts: protection to take care of our immediate survival needs, and a curriculum program to include civil defense in our courses of study. Before I describe in detail...
In this meeting, the school superintendent is seeking the board's approval of the general proposal. Before he can proceed with a more detailed plan, the board must endorse the proposal and authorize funds for development and implementation of the plan.
Thank you, Mr. Douglas. The board has already studied the outline of this proposal that you gave us last week.
explain the new directive and to make specific assignments for detailed planning. The curriculum coordinator heads the curriculum committee. The safety supervisor is appointed chairman of the protection committee. The school architect engineer is made chairman of the fallout shelter committee. Many others, such as the chief school nurse and the head building custodian, are assigned responsible positions. Everyone on the staff has an important role. The Civil Defense Director is present to explain how the schools fit into the total community survival plan. Principals are charged with full responsibility for developing and executing both the protection and curriculum programs in their own schools, programs which will conform with those established for the entire system. Before calling a meeting of the entire staff, principals in turn discuss the program with some of their key people. The school's safety supervisor is appointed as the civil defense coordinator. And teachers serving on the curriculum committee are told to prepare for special meetings to find ways of building civil defense into the courses of study. One of the first steps in developing the protection program is to decide on the best and most economical ways of providing shelter from radioactive fallout. With the aid of the local civil defense director, the school superintendent and his architect engineer make detailed plans for including dual-purpose fallout shelters in all new school construction. Plans are approved, funds obligated, and the real work gets underway. When this shelter is completed, it will also serve as the school cafeteria. Existing school buildings throughout the system are surveyed to determine what areas within them are best adapted for shelter use or for ready conversion to shelter. This area, for instance, was formerly used for coal storage, but now it serves as both fallout shelter and workroom for school theatrical production. This school needed more classroom space, but to add it above ground would have taken away valuable playground area. The problem was solved by building dual-purpose sheltered classrooms underground according to specifications furnished by the Office of Civil and Defense Mobilization. Alternate plans for evacuating the schools in target areas are also developed. If there is enough advance warning of an attack, civil defense plans in many target cities call for sending children home from school. Some target cities, such as this one, if there is adequate warning time, plan a general evacuation to safer areas. With the help of the local civil defense director, the school superintendent makes certain that arrangements for evacuating schools in his system are coordinated with those already established for the community at large. Cooperative arrangements must also be made between school and local government officials at reception areas. Development of an adequate internal warning system for the schools also is carefully worked out to supplement existing civil defense warning facilities. This community has a good outdoor warning system with sirens covering the entire area. Everyone here knows that the alert signal, a steady blast of from 3 to 5 minute duration, means to take action as directed by the local government. And that the take cover signal, a wailing tone or a series of short blasts of 3 minute duration, cover at once in the best available shelter. To supplement these outdoor signals, an indoor warning system is needed. Although there are other approved systems for instantaneous relay of warning, bell and lights are used here to alert the schools. Public address systems are installed so that emergency instructions can be given to the students and staff in the shortest possible time. Here's how the whole system works. When a warning is received by the local government through the attack warning system, sirens and bell and lights throughout the community are activated simultaneously. Every school in the system receives this signal. On receipt of the warning, the switchboard operator immediately informs the principal. Using the public address system, he gives appropriate directions to his staff and to the students. It cannot be stressed too strongly that any civil defense warning signal used in schools must be clearly distinguishable from other types of alarms. Survival plan for schools can be effective without the full cooperation of an informed staff. The importance of the role of teachers in conducting shelter drills, for instance, cannot be overemphasized. Efficiency of their teachers, youngsters gain confidence in arrangements made for their security. While individual schools may have different requirements, all must hold periodic drills to assure immediate response to warning signals. An adequate school fallout shelter should contain enough provisions to sustain students and staff for at least 2 weeks. In this combination shelter cafeteria, the cafeteria manager is in charge of emergency feeding facilities. It must be stocked with blankets for everyone assigned to the shelter. If the school is dependent on a vulnerable community water system, a special well may have to be provided for emergency water supply. Battery-powered radios with Commonwealth frequencies 640 and 1240 clearly marked on the dials must be available to receive emergency information. A telephone tied in with the city's Civil Defense Control Center. First aid and medical supplies. Sanitation facilities and means for safe disposal of rubbish and waste. Radiological monitoring equipment. An emergency electric power generator. And adequate ventilation are among the special items which must be provided. Because children would need some form of recreation, an area within the shelter should be available for physical activities and play. Of course, if time would permit, they would be in their own shelters at home. While the protection program is taking shape, civil defense is introduced into the curriculum at all levels. This third-grade class, for example, visits emergency facilities in the community, like the local fire station. Here they learn that the people people who protect them every day are a vital part of civil defense. In this 5th grade class, children make posters on home preparedness. Gradually, an awareness develops that civil defense is as natural, as meaningful, and necessary as everyday safety rules. The conditions of survival are learned. Preparedness becomes a personal responsibility. Discussion of the effects of natural disasters leads to a realistic grasp of the consequences of a nuclear war. The objective of curriculum planning is to give each student a background in the needs and methods of civil defense so that he will be prepared for living in the nuclear age. Under the supervision of the school nurse, first aid courses are taught as a regular part of the physical education program. These young homemakers in the 10th grade are getting some first-hand tips from their cafeteria manager on ways of preparing food for large groups of people. They learn that there is a real relationship between good food and good morale. Civil defense concepts should evolve naturally from existing subject matter, as in this 12th grade class in American government.
And if we were ever attacked, we would need more than ever the help and leadership of our government. Most states and many localities have already adopted this program to help us recover and to preserve our constitutional government. The first point in this continuity of government program is to establish automatic lines of succession to important positions. In a serious disaster, many officials may be
This is a sound peculiar to our time. A sound that is meaningful to this 12th grade physics class studying the effects of radioactive fallout. These radiological defense instrument kits for use in science classes have been distributed to high schools throughout the nation by the Office of Civil and Defense Mobilization. From experiences like this, young people grow in their understanding of the problems they must face, of the responsibilities they must accept as citizens of the nuclear age. If it is to be a successful program in our schools, civil defense must also be understood and practiced in our homes.
Vitally important area. We have been talking about some of the precautions schools are taking to protect their children and to help them meet the challenge of our time. But I want to stress that it's just as important we carry this knowledge, this preparation, into the home.
your community plan for emergency action. Protection from radioactive fallout through shelter. First aid and home emergency preparedness. Use the Conrad 640 or 1240 on your AM radio for official directions. These are some of the things that we must do. Prepare a family fallout shelter and equip it with 2 weeks' supply of food and water, a first aid kit, and a battery-operated radio. Since we are in a target area, prepare an evacuation kit for your automobile. Include a supply of food and water, a first aid kit, a battery radio, and blankets. First, let's talk about the family fallout shelter. This is a model of one of the types of family shelters recommended by the Office of Civil and Defense Mobilization.
The protection of our families at home and in schools is basic to the success of any community or national survival program. For the sake of clarity, let's review some of the steps in preparing a school civil defense program. After outlining a general plan with the help of the local civil defense authority, the superintendent makes his proposal to the school board. With the board's approval, he calls a meeting of his staff and principals to explain the new policy. Starting with the emergency plan, a shelter program is developed under the supervision of the architect-engineer who works with the civil defense director. If evacuation is called for in the community survival plan, school procedures are designed to conform with it. The entire school system is provided with a reliable warning system. Individual schools carry out their directives and refine their programs through regular drills and exercises. Following committee recommendations, the curriculum is modified to incorporate civil defense and survival techniques into the existing courses of study. And home preparedness is stressed as a necessary extension of the school survival program. Approaches to the development of school civil defense programs will necessarily vary according to local conditions. But if these guidelines are followed, while working closely with local civil defense officials, schools will be better prepared to meet any disaster. A nuclear war may never come, especially if we are prepared. But we cannot ignore the threat. The stakes are too high.
Over 19,000 disasters strike somewhere in our country every year. That's more than 50 disasters every day. Some are major, like Hurricane Camille. I witnessed this often destruction. Hurricane Camille, and even the greatest natural disaster we could imagine, would be dwarfed by the loss of lives and property in nuclear attack. I'm saying this because I have good reason to be concerned. My name is John Davis, and I am the National Director of Civil Defense in Washington, D.C. Our purpose in civil defense is to protect you, and to help you protect yourself in time of emergency. That's the reason we have prepared this special film, to tell you what actions you should take to help protect yourself and your family in case of a nuclear attack. The protective actions you take today would not be wasted if a nuclear attack did not occur. Experience tells us that these actions save many lives in natural disasters and other emergencies. But surest way to invite disaster is to do nothing to avoid it. Please give this film your closest attention.
Most likely, the most important fact in the world today is this. We've been living in the atomic age since 1945. It's a long time now. And none of the catastrophes so freely predicted, so honestly feared, have come to pass. True, there have been dangerous moments like the Berlin Cuban crisis. But so far, Canada has prevailed. Hopefully it always will. And yet there's no point in looking away from reality. We live in a troubled and uncertain world. And it's got to go on being troubled for a long time to come. The nuclear gene is out of the bottle. And until the world finds a way to clap it back in, and then put a lock on the stopper, there'll always remain the outside chance that what our nation and a great many others have been working so hard to avoid could conceivably happen to all. And of course, so long as even the slightest possibility exists, it's something we must reckon with, guard against, prepare for it, just as a common sense precaution. So let's talk a little about these things, about what's being done to protect you, and about what you can do to protect yourself in time of emergency. Of course, our first and strongest line of defense lies in what the strategists call the power of deterrence. In our intercontinental missiles, our nuclear submarine fleet, strategic air command, in the ability of all our military forces to retaliate even after a surprise attack, and do it with such enormous force that the aggressor would be defeated, most likely destroyed. And in that fact, that knowledge alone lies the strongest incentive any enemy could have to avoid launching a nuclear war. But behind the sword, there's also a shield. Very quietly, but steadily over the years, we've been building a nationwide system of civil defense, designed to save lives, to protect as many of our people as possible. It consists of many things. The National Warning System, tied in with NORAD, the North American Air Defense Command, able to alert the whole nation in a matter of minutes. A monitoring network with more than 65,000 locations to measure and report fallout radiation. And most important, a very large and growing public shelter system to protect us from that radiation. Local governments have been making detailed plans to deal with all kinds of disasters. An emergency broadcast system organized to keep you informed. And thousands of special emergency control centers to direct life-saving and recovery operations. In short, if attack ever threatened, there'd be help available from many sources. You would not be alone. But a lot, inevitably, would depend on you. There's no point in denying or trying to minimize the grim fact that a nuclear attack would take a heavy toll of lives. But in all the Defense Department studies, and there have been many of them, two things come clear. Even under heavy attack, our nation could, in fact, would survive. And our losses would be much less, your own chances of survival much greater, if each of us would take time to do just three things. First, understand the dangers you face. Second, make some fairly simple preparations to meet them. And third, learn exactly what to do if emergency comes. Then do it. 1, 2, 3. Now, about those dangers. There are some you can't think much about, but others you can. And knowing the distinction between the two could very well mean the difference between staying alive or dying an utterly useless death. When a thermonuclear weapon explodes, four things happen. First, a brilliant white flash of light. Then, a searing wave of heat shooting out from the nuclear fireball. The blast wave hurling debris before it. But even under heavy enemy attack, only 4 or 5% of our land, 1/20th of the country, would be affected at all by blast and heat. All the rest and all the tens of millions of people in it would escape untouched, except by radioactive fallout. It could spread on the wind to cover not just 5%, but 80 or 90% of our country. But that's one danger you can do something about, if you know a few facts about fallout. When a nuclear weapon explodes anywhere near the ground, tons of dirt and debris are pulverized into millions of tiny particles, swept up into the fireball, turned dangerously radioactive. They drift downwind in the mushroom cloud, then start slowly crawling back to Earth. The heaviest and most dangerous particles first, after 15 to 30 minutes in the area nearest the explosion. The lighter ones later, perhaps hours or days later, and hundreds of miles away, wherever the winds may take them. But wherever they fall, in fields and streams, on rooftops, or in the streets, they spell danger. Each one of these fallout particles, no larger than grains of salt or fine sand, is like a tiny X-ray machine, shooting out deadly, invisible gamma rays that can damage or destroy the cells of your body. Too large a dose in too short a time means sickness or death. But it's a useless way to die. Useless because it's unnecessary if you use the 3 defenses you have against it. One is time. The most dangerous period would be the first 24 hours after fallout arrives. But fortunately, radiation decays very rapidly. It's like an elevator going down fast. For example, if all the fallout were down on the ground 1 hour after the burst, then by 7 hours, the radiation would have dropped to just 10% of that 1 hour level. By the end of 2 days, it would be down to 1%. And in 2 weeks, it would be just 1/10 of 1%. In short, with shelter, you can wait it out. But while you're waiting, you'll need protection. And that comes from 2 things: mass and distance. Mass, meaning thick, heavy, dense materials. Concrete. Steel. Even ordinary earth, to absorb or deflect those deadly gamma rays, reduce the amount of radiation reaching them. And distance, because the farther you are from the source of the radiation, fallout particles settled on the roof or on the ground outside, the safer you'll be. Put those 2 together, mass and distance, and you've got a fallout shelter. You'll find it wherever you see this sign, the black and yellow sign that marks our community fallout shelters. And they could mean the difference between life and death in time of emergency. Of course, if you're convinced of the utility of it all, and you want to just stand out there and bear your breast to radiation, that happens to be your privilege. But as we all found out in the Cuban crisis, that kind of talk becomes just talk. As the real danger mounted, so did our will for survival. We all discovered a reason for living. Ourselves, our families, our children. And we were all looking for shelter. Well, it's there now, ready for use. A nationwide system of more than 100,000 large public fallout shelters located in office buildings, apartments, schools, factories, stores, and it's a good idea to look around, to know at all times where the nearest ones are, just in case they ever prove needed. Of course, there's still not enough, and they're not everywhere. Usually, there's plenty of fallout shelter downtown where most people work, but less in the suburbs where a lot of us live, and not nearly enough out in the country where there aren't enough buildings with heavy construction. If that's the problem, if you're just too far away from the nearest community shelter to reach it in time, then you'd better do something about it. One answer may lie in your own house. If the house has a basement, earth and concrete may give you some shielding already built in. And to help fill in the gaps, the Office of Civil Defense has been conducting home surveys in many of our states, asking each homeowner to fill out a questionnaire, then telling him by means of computer exactly how much fallout protection is already there. If you've already taken part in one of these surveys, you already know if your house has enough. And if it hasn't, well, usually all it takes to improve it, to build a home shelter in your basement, is some do-it-yourself effort, plus a couple of $100 at most for concrete blocks and other materials. And in extreme emergency, if crisis seems imminent and no shelters available, it's still possible to improvise some last-minute protection against fallout. Not as good as you'd find in a regular shelter, but any protection's better than none, and it could be enough to save your life. Remember, use mass and distance to reduce radiation. Choose the corner of your basement that's most below ground level. Set up a sturdy table or workbench there. Wall it in with the heaviest materials you can find. Bookcases, chests of drawers, appliances, trunks. Then, fill the drawers with earth or sand to give added protection. Cover the top with as much heavy shielding as it will hold. House doors, bricks, flagstones, firewood. Then, once your family's all inside, block up the entrance, leaving an opening at the top just large enough to let air in, of course. If you live in the country and your home lacks a basement, a storm cellar outside can serve just as well. If the existing roof is made of light wood, put in extra posts and braces to support the added weight. Then cover the roof with a foot or more of earth to give you solid protection. After everyone's inside, use bricks, sandbags, or heavy concrete blocks to wall up the entrance, leaving just a few inches open at the top, again for ventilation. Or you can improvise a shelter in your yard. Dig an L-shaped trench, 4 feet deep and 3 feet wide. Make the longer side of the L big enough to accommodate your family. The other leg will serve as an entranceway and help reduce the amount of radiation getting into the shelter. Shore up the sides of the trench for safety. Then cover it with house doors and heavy timber. Then pile on a foot of earth for protection. As a last resort, even if there's no basement or storm cellar available, you could get some limited fallout protection by improvising a shelter on the ground floor of your home. Use a hallway, an inner room, or large clothes closet, away from outside walls and windows. With doors, chests, trunks, and boxes filled with earth or sand, you can create an enclosure large enough to live in for the short time of that first peak period of danger. If the inner space you've chosen is too small to allow room inside for all these shielding materials, place them against the other side of the walls, in the surrounding rooms. All these are last-minute measures, of course, for use only in extreme emergency if you just can't reach a regular fallout shelter. But it's better not to wait that long to make the preparation, particularly when it comes to supplies. Most community shelters, though not all of them yet, have been stocked with the basic requirements: emergency food rations, water containment, sanitation equipment, medical kits, radiation detection equipment. But even so, in a time of crisis, shelter living would be sparse. None of the comforts of home. And there are things you'd better plan to take along to help ease that shelter stay. A battery-powered radio, flashlight and extra batteries, a blanket for each member of the family, any dietetic foods or special medicines your family may need for reasons of health, like insulin, heart tablets, antihistamines. If you have a baby, don't forget bottles, disposable diapers, cans of formula, and special baby food. And of course, if your neighborhood shelter is not stocked with the basic supplies, you'll need to take as much water and ready-to-eat food as you can carry. That's true of a family home shelter, too, for here you'd be on your own. So keep a 2-week reserve of supplies around the house for use in emergency. For shelter use, canned goods are best. Soup, canned meat, all the pre-cooked food. And packaged goods like crackers and wafers that don't need refrigeration. And water. That's even more important, for you can't live without it. As a minimum, 3 or 4 gallons for each member of your family, and store it in tightly capped bottles or plastic containers. If the supply runs low, don't overlook all the alternate sources right inside your house. The canned fruit and vegetable juices on the kitchen shelf. Soft drinks, milk, and ice cubes from the refrigerator. The 20 to 60 gallons in your hot water tank. And of course, all the water trapped in the pipes of your house plumbing system. In case of attack, simply turn off the main water valve in your basement to avoid having it all drain away if there's a break in the outside main. Then, turn on the faucet located at the highest point in your house, probably the upstairs bathroom, to let air into the system. Then, draw the water as you need it from the faucet located at the lowest point. It'll be pure, drinkable, and free from fallout. If some fallout particles are on food that you brought in from the outside, don't worry. They can't make it radioactive. Simply remove the particles, and you remove the danger. Just wash or peel the fruits and vegetables. Wipe off the packages or cans. For safety, it's better to make sure that babies or small children aren't allowed food or liquids that might be contaminated. However, in extreme emergencies, thirsty people should not be denied water, even if it contains fallout. There's little danger that any adult could swallow enough to hurt him. It'll be like trying to swallow sand. Of course, we've only skimmed the surface here of things you need to know and do. But you'll find everything covered in fullest detail in this Citizen's Handbook prepared by the Office of Civil Defense. It's titled, In Time of Emergency. It deals with natural disasters as well as the dangers of enemy nuclear attack. And you can get a copy from the Civil Defense Office of your own local government. Read it. Study it. And above all, keep this quick checklist of emergency actions in mind. First, know your local emergency actions plan. Hundreds of cities and counties have prepared and printed specific community shelter plans, complete with maps and detailed instructions, telling every resident where to go for the best available protection against fallout. Make sure your family knows the plan, where the nearest shelters are, and how to get there in time. Second, keep a stock of emergency supplies on hand. Food that require no cooking, enough drinking water and other liquids, special medicine, radio, flashlights, blankets. And if you're planning to use a home shelter, don't overlook the problem of sanitation. Lay in a metal container with a tight-fitting lid, some plastic liners, and household disinfectants. You'll need them for disposal of waste and prevention of disease, to keep your family healthy through a shelter stay. If attack seems imminent, take precautions against fire. closed doors, windows, Venetian blinds. If you don't have Venetian blinds, cover the windows with household cleaning powder, aluminum foil, whitewash. For even in the fringe areas, miles away from any nuclear explosion, the heat wave could ignite trash and dry wood, set fire to your home. Have some basic firefighting tools on, especially a good fire extinguisher, and keep your garden hose connected. Unless your local authorities advise otherwise, fill the bathtub and other containers with water. For under enemy attack, the fire department may not be available. You'll have to help yourself. Above all, make sure you know what your local attack warning system is. There are a few exceptions because of special local conditions, but in most communities, the standard attack warning is this. A wavering, undulating sound on the outdoor sirens lasting 3 to 5 minutes. Or a series of short blasts on whistles and horns. And when you hear that sound, believe it, an actual enemy attack has been detected. Don't reach for the phone to find out what's happened. The lines need to be kept clear for official emergency use. And you need to find shelter promptly. If you're caught in the open, if there's a sudden flash and you feel warmth at the same time, don't look at the flash. Move. Take cover instantly. Behind a tree. Or a wall. In a ditch. Or a culvert. Curl up on the ground and cover your head with hands and arms. Stay there till heat and blast waves have passed. Then get to shelter before the fallout starts flowing. Then turn on the radio. The emergency broadcast station serving your area will be bringing you news, presidential messages, civil defense instructions. You would not be alone. In many shelters, you'd find friends and neighbors who've been specially trained in shelter management, radiological monitoring, medical self-help. All across the country, the Civil Defense Monitoring Network would be measuring and reporting fallout conditions. And from the state and community emergency control centers, your own local authorities would be directing life-saving and recovery operations, keeping in close touch with each shelter. Just follow their official instructions and stay in the shelter till they tell you it's safe to come out. All these things are easy to remember and fairly simple things to do. None of them cost much in time or effort or money. If nothing ever happens, if the world maintains its sanity and enemy attack never comes, that time and effort will still have been well spent. For the better, both we and the nation are prepared. The less chance, really, that anything will happen. And if they ever prove needed, they could save your life in time of emergency.
Medical self-help is an emergency measure to be used only in cases of sudden or extraordinary misfortune. If people require medical care in the course of normal, everyday living, they should always be treated by a doctor. However, when disaster strikes, you may not be able to obtain trained medical aid in time. There are many forms of disaster. They can happen to you and your family at any moment. This film is one of a series on medical self-help. Its purpose is to teach you what to do in an emergency situation when there is no doctor.
This powerful X-ray machine, a tool of medical science, is being used for healing purposes.
The radiant energy it emits is able to kill all living tissue within its beam, both sick and healthy cells of the human body. Its invisible rays so highly penetrative that protective shielding with lead glass windows must be used. X-rays are much like the gamma rays of radioactive fallout. We began our picture with X-rays because you are all to some degree familiar with their effects. But radioactive fallout is another matter. If you're like most people, it creates many questions in your mind, and you have doubtless read or heard some falsehoods and misconceptions. This film will tell you what you need to know about fallout, so that if our country is ever subjected to a nuclear attack, you can help yourself and your family to survive its dangers. For fallout is probably the most dangerous product of nuclear disaster in terms of the number of people who could be affected. It is also the one from which we are best able to protect ourselves. Let's examine what happens when a nuclear weapon is exploded near the Earth. First, there is blast, or the pressure wave created by the explosion, along with heat, the most intense ever created on Earth. Both will extend great distances from the point of the explosion, from 1 to 20 or 25 miles, depending on the size of the weapon. However, the further away you are from the site of the explosion, the less are the chances you will suffer the fatal effects of blast and heat. There is yet a third immediate result of a nuclear detonation: initial radiation. The final effect is residual radiation, the main concern of this film, or radiation that follows the explosion and one that may remain at high altitude for some time before falling back to Earth. What exactly is residual radiation? Our sun, like other stellar bodies of the universe, is a giant nuclear furnace, burning at temperatures of millions of degrees, while emitting various types of radiation. Among these are gamma rays, shorter in wavelength than their closest neighbor, X-rays. The Earth's atmosphere prevents these radiations, dangerous to the health of man and animal, from reaching our planet. However, when a nuclear weapon is exploded, man is creating on Earth, in the splitting of atomic nuclei, his own nuclear furnace to produce the gamma and beta radiations of outer space. Let's see now just how this radiation is created. At the time of the burst, vast amounts of dirt, stone, and other debris, vaporized by the heat of the explosion, are sucked up into the rising cloud. As the mushroom cloud forms, these particles are made radioactive, or as they cool and condense, they are contaminated by residue from the bomb. These particles, when they fall back to Earth, are what we call radioactive fallout. Can you or anyone else predict with accuracy the pattern by which fallout particles will return to Earth? The answer is no, for fallout will depend on the number, size, and location of nuclear weapons exploded and the direction of upper air currents. Let's, for example, explore the fallout produced by one of these nuclear weapons. It sends its column of radioactive material up to 80,000 feet, or about 16 miles or more above the Earth. Here, the radioactive particles, beginning to drift downward, are at the mercy of upper air currents that vary from day to day. Descending at various altitudes through many different layers of air that may be moving at varying speeds and directions. Thus, winds on the surface of the Earth give little help in determining the direction or the occurrence of fallout. Meteorologists, with their special instruments, however, can appraise altitudes as well as the total distance fallout will be carried. In a nuclear attack, keep tuned to your local radio station. It will keep you posted where fallout is taking place and its approximate amount. Though you may be able to see this dust once it reaches the Earth, you cannot see or detect the radiation it emits without the aid of radiological instruments. Nor can you taste, smell, or feel this radiation. Why is fallout so dangerous to human and animal life? Because each particle gives off radiation as if it were a tiny X-ray machine. This radiation consists mainly of gamma rays, which are extremely penetrating. Like X-rays, gamma rays are able to injure, even destroy the cells of our bodies if we are exposed to a sufficient dosage long enough, or if we eat or drink material contaminated by fallout particles. Exposure to gamma rays can make you sick, can even cause death. However, no matter how long one may be exposed to fallout, he does not become radioactive, nor can anyone catch radiation sickness from him like a contagious disease. In fact, this radiation cannot make anyone or anything radioactive. Now let us suppose that fallout has descended on this can. We'll let salt represent fallout dust. The particles don't go through the tin. The radiation does, but radiation is harmless to all except living material. It has no effect on the food inside. Now, if you wipe away the fallout particles, or better still, wash them away, the food inside cannot be contaminated and is perfectly safe to eat. The same is true of all foods and liquids that have been protected by packagings or containers, even the thinnest layer of cellophane. If you don't swallow the dust, there is no ill effect. If water for washing is in short supply, canned goods that may have been exposed to fallout can be handled safely with a piece of paper towel. Use one sheet of paper to lift the can and turn it upside down. There is no dust on the bottom. Now dispose of the paper. Wipe the sides of the can with a new piece of towel. And don't forget to put the contaminated paper in a covered receptacle. Now open the clean top. There will be no harmful particles in the food itself. A sealed loaf of bread that has been exposed to fallout can be salvaged in a similar manner. Turn the loaf upside down to expose the bottom, which will be clear of dust. Then dispose of the towel. Now insert a sharp knife through the wax paper at the center of the loaf and cut upwards, making a slot 4 or 5 inches lengthwise. Insert your fingers through the slot and rip the paper slowly open. The bread can be safely removed to a clean plate. Finally, dispose of the wax paper. Contaminated vegetables, such as potatoes, can be pared like this. Use a clean piece of newspaper and, working first in one corner, cut off one end. Move to a clean surface of the paper and peel in this manner. Move to another area of the paper and remove the other end. Dispose of all peelings and soiled paper carefully. After handling any contaminated food containers or vegetables, wash your hands. Fallout dust is dangerous, but it can be dealt with by following safe procedures. There is another widespread legend. The fear that fallout spells death to all life on Earth. The plain fact is that even if a great number of nuclear weapons were exploded, the resulting fallout would cover only a small area of the world's total land mass. The real concern then is this. If we are in that area, how do we protect ourselves? Like X-rays, radiation from fallout can go through almost every kind of building material. Over 99% would pass through glass, 66% through wood sheathing, 50% through a brick veneer wall. But only 1% of gamma radiation would penetrate 18 inches of concrete. And though it's not a building material, it's important to know that only 1% would pass through 25 inches of earth. Quite aside from the shielding effect of building materials, the intensity of radiation decreases with the square of the distance from the source. Thus, 10 feet away from a particle of fallout, the radiation rate is only 1% of that encountered at a distance of 1 foot. Other things being equal, the central parts of a building are safer. The radiation rate, or the intensity from fallout, decreases with the passage of time. In fact, for every 7-fold increase in time, the radiation will be reduced by a factor of 10. That means that at 7 hours after the explosion, the radiation level will be about 10% of its intensity at 1 hour. At 49 hours, it will be about 1%. Within 2 weeks, the radiation rate can be expected to decay to about 1/10 of 1%. Therefore, the most vital period to seek protection from fallout is the first few days after nuclear attack. Even more so, the first few hours. But remember, even with the passage of time, a low level of radiation can be dangerous. That is why you may need to remain within a sheltered area for as long as 2 weeks. These, then, are the 3 basic factors in protection against fallout: time, distance, and shielding. Time, meaning the longer you stay protected from fallout, the safer you will be. Distance, or the further away you get from fallout, the safer you will be. Shielding, meaning the more mass or weight you put between yourself and fallout, the safer you will be. You have often seen this sign on buildings. It means that indoors is a public fallout shelter, one of many and various kinds of buildings in your community that are similarly identified. Architects and engineers have carefully surveyed the shielding qualities of these areas to ensure they offer a minimum protection factor of 40 or more, meaning that in the event of fallout from a nuclear explosion, the mass and weight this shelter will place between you and the source of radiation will make you at least 40 times safer than if you were outdoors. Each of these shelters will hold at least 50 people and has been stocked by the government with austere supplies: food, water, sanitation equipment, medical kits, and radiological instruments. But what about millions who live in suburbs or rural areas, often far beyond quick walking distance of the nearest public shelter? With foresight, you can have a home shelter for the protection of your family, built from specifications and cost estimates for various types of shelters provided by your local civil defense office. The home shelter should be stocked with supplies of food and water sufficient for 2 weeks. Here you are afforded time, distance, and shielding if and when fallout so dangerous to human health should ever occur in your community. Just how much radiation can you receive without becoming sick? We measure exposure to gamma radiation from fallout in units called Roentgen. They're the same units used to measure X-rays, named for Wilhelm Conrad Roentgen, the discoverer of X-rays. People and animals may develop radiation sickness if they have been exposed to large amounts of radiation over a short period of time. Few people become sick who have been exposed to a total radiation dose of 100 Roentgens or less. However, exposure to more than 300 Roentgens over a period of a few days will cause sickness, may cause death. And if you receive an exposure of 600 Roentgens in that same period of time, death is almost certain. How can you tell just how much radiation you've been exposed to? These are the instruments commonly used to detect and measure radiation. They are part of the equipment supplied to the radiological monitoring team of every public shelter. With them, you can determine not only the total amounts of radiation received, but also the dose rate per unit of time, or the dose rate in Roentgens per hour. This is the dosimeter, conveniently shaped to be worn on one's person at all times. It is able to measure the total accumulated radiation exposure in Roentgen. The charger adjusts the dosimeter to a zero reading prior to its use, with each separate exposure to radiation building cumulatively on the dosimeter gauge so that a reading of the total dose is available at any given time. Next, the Geiger counter. This instrument measures radiation in fractions of Roentgens per hour within or outside the shelter. Finally, the survey meter, able to measure higher intensities of radiation that may exist outside the shelter. For home shelters, detection and measuring instruments are available from commercial sources. However, most householders will rely chiefly on their portable radios to receive readings as they are taken by civil defense monitoring teams. If there is a nuclear attack and you survive the initial effects of an explosion, you will have at least a half hour to get to a public or home fallout shelter. Therefore, to be safe from radiation sickness, get into the best available shelter as soon as possible. Once there, stay put, because each time you're exposed to fallout radiation over a period of a few days, the dosage continues to build until it reaches dangerous quantities. If you're among those compelled to travel through a fallout area on essential errands, there are certain rules to follow. Protect your body with boots or rubbers, gloves, headgear, and outer clothing that can be removed before you re-enter the shelter. On returning, brush off the rest of your clothing thoroughly, as well as any parts of your body that may have been exposed to fallout. If sufficient water is available, wash your face and hands carefully. Remember, these are the dosages of radiation as they affect human health. 100 Roentgens, little or no effect. 300 Roentgens, sickness or death. 600 Roentgens, death. Recovery from radiation sickness is nothing new. Patients who are treated by X-rays routinely experience this sickness and get over it. Of course, the dosages they receive are carefully measured. Just as in combating the virus of the common cold, your general state of health will often govern how quickly you can throw off the effects of mild or moderate radiation sickness. In an emergency situation where there is no doctor, always treat radiation sickness by treating its symptoms. In fact, these symptoms are often similar to those produced by extreme anxiety or emotional stress. So it's best not to try to determine their cause. I repeat, do not try to diagnose. Merely treat the symptoms, just as you would if they were the result of any other type of illness. These are the symptoms of mild as well as moderate radiation sickness, one or more of which may appear shortly after exposure to fallout. Fatigue, loss of appetite, nausea, vomiting, prostration. The treatment is rest. For nausea, you may give the patient any of the commercial preparations that settle an upset stomach, or 1/2 teaspoon of baking soda in a cup of water. Tea and other hot liquids may be helpful. When a high fever is present, apply cold wet packs. Aspirin also tends to reduce the fever. In severe radiation sickness, along with the early symptoms, other symptoms may appear a week or more after exposure. Recovery is possible, but it'll take longer. The symptoms are diarrhea, inflammation of mouth and throat, loss of hair. For treatment, control the diarrhea and give aspirin and warm water gargles. People are naturally alarmed at the thought of bodily changes that may follow severe radiation sickness, such as loss of hair or sterility. These conditions are usually temporary and will disappear with recovery. So I hope we've dispelled another commonly held myth. You can get over radiation sickness just as you get over many others. Nevertheless, don't minimize the danger of fallout. Remember, its effects are cumulative. The only real protection against it is to take shelter. Now, let's review some of the outstanding facts we have learned in this brief exploration of a vitally important subject. Fallout is composed of trillions of particles of dust that are made radioactive by residue from the nuclear weapon during the aftermath of the explosion. In a nuclear attack, depend on your local radio station to tell you where fallout is taking place. You may be able to see some of the fallout dust when it reaches the earth, but you cannot taste, smell, or feel the radiation itself. The gamma rays given off by fallout are able to injure or destroy the living cells of our body if we are exposed long enough. Food or water in containers that prevent contamination by fallout dust is perfectly safe. Radiation is harmful only to living tissues. Packaged foods that have been exposed to fallout should be opened carefully. By following proper procedures, you can eat such foods without danger to health. Radiation can pass through most building materials, but its intensity is diminished in proportion to the weight and mass of the material or the shielding. The intensity also decreases with distance from the fallout. The radiation rate will decrease or decay rapidly with time. It is most dangerous in the first few days after explosion. Thus, the three basic factors that protect you from fallout radiation are time, distance, and shielding. You should know the location of the nearest public shelter in your community. Inside it, you will be at least 40 times safer from fallout than you would be outdoors. And it has been stocked with supplies to sustain its occupants for up to 2 weeks. If you're not within walking distance of a public shelter, you can provide a satisfactory home shelter for your family. Radiation is invisible. but we have accurate instruments with which to measure it in Roentgen units. The dosimeter can be worn on the person and measures the accumulated radiation exposure, the total dose at any given time. The Geiger counter measures radiation in fractions of Roentgens per hour, inside or outside the shelter. The survey meter is used to measure the higher intensities of radiation that may be present outside the shelter. Assuming that you have the protection of a good shelter within a half hour after nuclear attack, you will probably have little or no radiation sickness. If there are victims who appear to have radiation sickness, do not diagnose. Treat the symptoms. Perhaps the most important thing you have learned is to see the danger in its true perspective. Make no mistake, nuclear attack would be a terrible catastrophe. Millions of our people would be killed by the initial blast and heat. Millions more would be threatened by death from radioactive fallout. But that is a threat that can be combated. Can, with knowledge, preparation, and courage, be faced and conquered.
And equally important, we must also realize that for a time as that prospect may seem, destructive as such an attack might be, we can survive. It would not mean the end of the world, the end of our nation. And you can greatly improve your own chances of survival if you remember these facts about protection in a nuclear age. Wherever we live, we're all inclined to think of our own hometown as target number one. But this is a very big country. With many cities, industry, military bases. And Defense Department studies show that even under the heaviest possible attack, less than 5% of our entire land area would be affected by blast and heat from nuclear weapons. Of course, that 5% contains a large percentage of our population. But even in these high-risk areas, if there's sufficient time to permit evacuation, many millions of lives should be saved. The other 95% of our land will escape unharmed, except possibly by radioactive fallout. Now, here's the things you need to know. First, the warning signal. There are two of them, and it's important that you know this. The attention or alert signal is used for peacetime emergencies, tornado and hurricane warning, industrial explosion, other immediate threats to your safety. The signal is a long, steady blast from the civil defense siren or other warning devices. It means turn on your radio or television set. Your local authorities have a peacetime emergency message for you. The intent warning signal is a 3 to 5 minute wavering sound on the sound. Or a series of short blasts on pistol. Or horn. This system contains warning an actual enemy attack against the United States is imminent. Don't pick up the phone to find out what's happening. The lines need to be kept clear for official emergency use. To conclude, if you're at work or in school, take cover in the basement or in the corridor. At home, go to your basement or fallout shelter, or find protection under the stairs. Keep a battery-powered radio with you. Then tune to your local emergency broadcast station for news and official instructions. behind a screen or a wall. In the shelter of a tree, curl up in a ball and cover your head with hands and arms. Stay there till both the heat and the blast waves have passed. If your home is in an area where the temperature has started small fires, use an extinguisher. Prevent them from growing into big ones. Shut off your main water supply. Have at least 30 minutes to do it before radioactive fallout starts coming down. When a nuclear weapon explodes on or near the ground, tons of dirt and debris are pulverized and carried outward to mushroom clouds. Vaporized by intense heat, then condensed into millions of tiny particles of fog, no bigger than grains of salt or sand. Spread by high-altitude winds, fallout can take up wide areas. And wherever it falls, it spells danger. The tiny particles emit invisible gamma rays, much like X-rays. And if your body absorbs too much of this radiation, it can cause sickness or death. It's not contagious. You can safely treat it as a radiation sickness without the one thing that can make you a victim is direct exposure to fallout. And you will do that if you prevent it. Mass, distance, and time. Mass means thick, heavy, dense material to shield and screen out most of the radiation. Like 16 inches of brick, 12 inches of concrete, or concrete block filled with sand. Even 4 feet of soft dirt. Your second defense is distance. The farther you are towards radiation, the fallout settles on the roof of ground, the safer you will be. In large buildings or housing structures, both the basement and the inner corridors are sealed, as this protects from radiation taken from both mass and distance. And finally, there's time. Luckily, radioactivity from fallout incidents very rapidly. In fact, 7 hours after the blast, the level of radioactivity will drop a full 90%. After 2 days, 99% of the radioactivity is gone. And after 2 weeks, only 1/10% is left. In short, time works. It protects us even though it doesn't. If a cat seems threatened, there are 2 kinds of protection. 1, public shelter. 2, home shelter. And 3, relocation. One, go to the nearest public shelter. After you see food, yes, shelter signs. There are more than enough public shelters to shield our whole population if they were perfectly distributed. Fortunately, greatest dangers would be blast and fire in private areas, which means the people most threatened would be those living or working in the commercial projects, near strategic military bases, and near some of our larger centers of industry. The simplest way to save them is to move them out. The small towns and rural areas where the only likely danger is falling. So the federal government, in cooperation with state and local governments, is now working on detailed plans for temporary relocation of these high-risk areas with crisis management. These are difficult and complex requiring much planning. After all, we relocate millions of workers from our cities to Russia. We have moved hundreds of thousands of safely in time of hurricane or flood. It could save as many as 100 million lives. It would be an orderly, controlled evacuation. Your own local authorities will give detailed instructions through radio, television, and the press, telling you what necessities to take along, what arrangements have been made for transportation, by bus, train, or private car, where you will find safety in a small town or rural district, and what routes to follow to get there. When you arrive, reception centers will be ready to welcome you to the and special arrangements will be made for a certain level of fallout protection in case the crisis should be followed by fire. In fact, we need fallout protection in place everywhere, so there's no telling where it may be needed. But even if you're unable to use the shelter, you can still improvise some protection. Set up a strong cable or workbench in the corner that's north below ground level and away from windows. Cover the top with as much heavy materials as it will safely hold. Swords, flag jumps, books. Wall it in with heavy bookcases. Test the drawer. Then fill the drawers with dirt or sand or either shield. If your house is built on a slab foundation, use the concrete floor for shelter. Unless the soil is too rocky or high water table prevents, dig a trench alongside the house. Tunnel under the foot of it and up. Digging out a shallow under the concrete slab, around big enough to contain your family. Shore up the slab with timber if need be, and slant some heavy doors covered with soil over the outside trench for added protection from fallout and rain. Or you can dig an outlet trench in your yard, about 4 feet deep and 3 feet wide. Make the longer side of the L big enough to accommodate your family. The shorter legs will serve as the entrance. Shore up the sides of the trench for safety. Cover it with outdoors or heavy timber. Then pile 2 feet of earth on top for protection. In rural areas, excellent fallout shelters can be found in natural caves. Tunnels. Mines with horizontal shafts. And stone or root cellars. Cover the cellar with a full of real earth. Then shield the entrance with brick or block to protect you from radiation. Of course, the maximum protection of all would be a basement fallout shelter, built before any crisis occurs. Your local civil defense director can supply the plan. With a little time, some money for materials, and do-it-yourself labor, you can supply the rest.
wherever you are, you'll need emergency supplies. If fallout in your area is light, you may be in shelter only a few days. But to be on the safe side, store enough pre-cooked, canned, or packaged food, plus special food for the babies, diet food for the sick and elderly, and enough water to last you, if necessary, for a week or more. Water is the most important. You'll need at least a quart, better yet a gallon, for each person, for each day. Store it in tightly sealed glass or plastic bottles. You can also use the bottled or canned beverages, fruit and vegetable juices, and milk from your refrigerator. Then there's your hot water tank. Water in the front tank, not the bowls of the toilets. And water trapped in the house piping system. Close off the main valve to keep that precious water from draining away into the outside beneath. Turn on the faucet located at the highest point in the building to let some air into the system. Then, drain water as needed from the lowest point. Don't forget sanitation supplies. A metal container with a tight lid for an emergency toilet and toilet tissue. A garbage can for wastes. Plastic liners and disinfectants. Medicines and first aid supplies. Blankets and feathers. Extra clothing and underwear. Soap, towels, personal hygiene items. Flashlight and candles. Fire extinguisher and bucket of sand. And a battery-powered radio with extra batteries so you can receive news and official instructions. If you're going to a public fallout shelter, bring as much water and ready-to-eat food as possible. Extra clothing, blankets, a flashlight, special medicine, and personal hygiene items. If you're being moved to safety from a high-risk area, pack all the other basic necessities your family takes when going on a trip. Plus blankets, bedding, special medicine. For your own protection, remember these basic things. First, the attack warning signal. A 3 to 5 minute wave-moving sound on the sirens. Or short blast on whistles or horns. Next, the effects of a nuclear explosion. Blinding flash. The heat wave. Then the following blast wave. And finally, radioactive fallout. Remember your 3 defenses against fallout. Mass. Thick, heavy, dense material to shield you from the radiation from fallout. Distance. The farther you are from the fallout that's settled on the roof and the ground, the safer you'll be. And time. Radioactivity does weaken rapidly. With shelter, you can wait it out. Keep a battery-powered radio with you, and use your local emergency broadcast station. It'll help you stay safe to come out. Don't forget spare batteries for your radio. Remember, too, you have 3 choices. 1. Go to a public fallout shelter. Know where the nearest one is. Your office, your home, your children's school. Be prepared to keep along food, water, the other necessities we mentioned. you decide to take shelter at home, know how to improvise and improve your protection there. And do lay in enough supplies. Relocation. If you live in a high-risk area, your local authorities may ask you to move to safety in a small town or rural area. Be sure you know their emergency plan, so you'll know exactly where to go and what to do. Whatever the choice, take time now to make your own family protection plan. Know what you need. Make your plan practical. Make sure each member of the family knows exactly what to do if crisis ever comes. Don't wait till you need it. That's too late. Do it now.
The Earth from space can seem a fair and pleasant place. And perhaps through strength and unceasing efforts to settle international disputes by peaceful means, we'll manage to keep it that way. The greatest danger is hopelessness. The fear that nuclear attack would mean the end of the world. So why not just give up, lie down, and die? That idea could bring senseless and useless death to many. But protection is possible. And your own chances of survival will be much greater if you remember these facts about protection in the nuclear age.
tools in the hands of skilled craftsmen have helped to build the world we know today. A world of towering steel, of giant airplanes, fast-moving transportation, a world of mechanical wonders, products of fine craftsmanship whose origin lies in the proper use of simple hand tools. But to more fully appreciate these tools and their part in our world today, let's turn back the pages of history. 60 or 70,000 years ago, long before the beginning of civilization, our primitive ancestors lived in caves, and we today might also be living in caves, except for a certain event that took place within the gloomy depths of this long-forgotten cavern. Here, a certain Stone Age craftsman by the name of Primitive Pete stumbled upon a very good idea. He suddenly realized that by fastening a stick to a rock, like this, he could extend the length of his arm, like this, and thereby greatly increase the force of his blow, like this. Thus was born the world's first practical hand tool. Oh, did we say practical? Well, anyway, it was a good idea. In fact, it eventually led to the development of all the numerous sledges and hammers we have today. But more than that, out of Pete's Stone Age hammer came other tools. Tools for every purpose. This ball-peen hammer, for example, is just a practical version of Primitive Pete's first crude invention. But like all tools, there's a right and wrong way to use it. There are still Primitive Petes among us today who would abuse this fine tool. And this would be the horrible result. Obviously, this hammer was never intended for crushing rock. The ball-peen hammer was designed for many purposes. The peen end can be used for riveting. It's also used for shaping soft metal. When using the face, you can avoid damage when hitting a hard object simply by striking with a full face. Never strike the object with the edge. Of course, there are many other types of hammers, all based on the original Stone Age model. There's the brass or copper, the rawhide base, plastic tip, and the claw hammer, which is the most commonly used. Or we should say most commonly misused. To use the claw hammer correctly, rest the head squarely on the nail. Give the nail a slight starting tap. Then drive it in with steady blows. A long nail can be pulled part way with the natural leverage of the claw. Then a block of wood placed under the head will increase the leverage, making a stubborn nail easier to pull, with less strain on the handle. A hammer with a loose head can be plenty dangerous. Here's how Primitive Pete would tighten the head on his hammer, but that only damages the handle at both ends. Have you a little beauty like this in your home? A steel wedge is the right answer. Driven into the wood, the wedge spreads the handle to the tapered sides of the eye and holds it tight in both directions. Gripping the handle too close to the head reduces the force of the blow, and sometimes makes it difficult to drive a nail in straight. Always grip the handle close to the end to increase the length of the lever arm and make each blow more accurate and effective. Never use a handle for a crowbar. That's going all the way back to primitive peat. Another familiar tool that takes an awful lot of abuse is the ordinary screwdriver. Our modern-day primitive peat often uses a screwdriver to pry open a stubborn window. Well, maybe he'll succeed in ruining the tool. This never would have happened if Pete had known more about the screwdriver. It's made up of three principal parts: handle, shank, and blade. Some screwdrivers have a full-length shank extending through the handle. But many household screwdrivers have a shorter shank, pinned to the handle in this fashion. This type will not stand a primitive peat treatment. The best rule is never hammer on any screwdriver. Many of us try to use one screwdriver for every size of screw head. Always choose a screwdriver with a blade equal in width to the length of the slot. Another thing, never attempt to turn a tight screw if there is too much play between the blade and the slot. A bad fit can cause serious trouble. It can ruin the screw slot or the blade. This looks like the work of primitive peat. So it is. Fortunately, if the blade is not too badly chipped, it can be reground into serviceable shape. First, grind the tip straight and square with the shank. Then grind each face a little at a time. But never allow the blade to become hot. Excessive heat will draw the temper and the blade will become soft. Here are the front and side views of a properly ground screwdriver. Here's a little trick. If the faces of the blade are tapered in slightly, a short distance back of the tip, the screwdriver will stay down in the screw slot, even when a severe twisting force is exerted. Here is a special type screwdriver designed for heavy duty. The extra-large square shank will stand a wrench if added leverage is needed. Don't be a primitive Pete and resort to the use of pliers. They're apt to chew off the shank. Pliers are made for other purposes. Here are some familiar types: combination, diagonal cutting, long round nose, and side cutting. These side cutting pliers are used chiefly for electrical work. To make an electrical connection, first cut the insulated wire to the required length. Then use the part back of the joint to flatten the insulation, like this. Then grip the insulation with the cutting edges without biting into the solid wire and strip off the insulation. Now right here is where long round nose pliers come in handy. To make a neat loop to fit a terminal, first use the tip of your pliers to make a right angle bend. Then grip the wire farther up and turn the end into a loop. These diagonal pliers have their cutting jaws at an angle. They're very useful for removing and installing solder pins. A drop of oil every now and then is good insurance against rust. Like all tools, pliers should be kept in good working order. These combination pliers, equipped with a slip joint, are very commonly used. They usually have a small shear between the teeth and the joint for cutting wire or nails. Think of these pliers as a set of extra, stronger fingers, valuable for all sorts of jobs. They should not be used to tighten or loosen nuts. The jaws might slip, chewing off the corners of the nut. A better tool for this job would be an open-end wrench. They usually come in sets, with openings ranging in size from 5/16 of an inch to 1 inch. Wrench measurements refer to the distance between the jaws. Use a wrench that always fits the nut exactly. Pushing on a wrench when the nut is tight is bad practice. Better not, Pete. We're warning you. Some people have to learn the hard way. On open-end wrenches, the head is set at an angle to the handle, usually 15 degrees. This permits efficient use in close quarters. For example, this nut has very little swing space around it. To start the nut, the wrench will fit one set of flaps in this position. And we can get the nut a partial turn before the handle jams against the block. But if we try to repeat the action, we find the nut is in a new position and the wrench won't fit. So we flop the wrench over and get a new fit on the nut. Again, we pull the handle as far as it'll go. We keep repeating the procedure until the job is finished. An ingenious development of the open-end wrench is this type. Its adjustable jaw makes it handy for many sizes of nuts and bolt heads. But the jaw should always be set for a snug fit on the sides of the nut before exerting any great force. To use the wrench correctly, the pulling force should be applied to the stationary jaw, like this. Great force applied to this weaker adjustable jaw might ruin the tool. This type of wrench is not intended for hard surface, so don't overstrain it. And remember to keep the moving parts well oiled. There are many uses for a medium-sized monkey wrench. This tool also is often abused. The jaws should always be adjusted to a tight fit. And remember to exert the pull on the right side, opposite the opening. If the wrench is used the wrong way, it might slip off the nut and do a lot of damage. See what we mean? Trying to force a stubborn nut by hammering on the handle of the wrench is a sure sign that you're a primitive Pete. If you really want to ruin a good tool, try this on your monkey wrench. You can ruin yourself, too. What Pete needed was a bigger wrench. And we should remember that there is a proper tool for every job. It will only take the trouble to use it. Pipe wrenches are used for turning pipe, pipe fittings, and other round objects. The teeth of the pipe wrench will not grip the fitting unless the tool is worked in the correct position. For best results, the bite should be taken at the center of the jaw. Remember, the teeth will always leave their mark on the work. However, if you must use a pipe wrench on plated fixtures, you can first wrap the pipe with a leather strap. This will protect the finish. A popular wrench with mechanics is the box wrench, designed for use in close quarters. The 12 knots this tool make it possible to get a good fit over the nut in almost any position. Notice the nut is gripped at all 6 corners. To ensure a working clearance, the head of this wrench is offset from the handle at a 15-degree angle. Some mechanics call this tool a knuckle saver. Here's a combination of a box and open-end wrench, sometimes called a half and half. The box end is ideal for breaking loose a tight nut. Then, if there's no clearance for a full spin, the open end may be used to turn the nut off more quickly than the box end. Every workshop should have a set of socket wrenches with at least one handle to fit the different sockets. However, a good mechanic needs a larger set, like this one, with a dozen sockets and several handles for different types of jobs. These special handles provide leverage in almost any position. For example, this hinged offset handle can be worked at various angles. This T-handle with a universal joint allows use in very confined areas where it would be difficult to work with ordinary handles. A further improvement is a ratchet handle. With this tool, the ratchet lever can be set so that the wrench pulls in either one direction or the other and ratchets in the opposite direction. When Primitive Pete attached a simple handle to a piece of rock, he became the inventor of the first hand tool known to man. And from this beginning, through centuries of trial and error, came the vast array of fine tools we have today. Most of us take our modern tools for granted, not realizing what a vital part they play in our daily lives.
In a nuclear attack on this country, one of the greatest threats would be radioactive fallout. While heat and blast effects of even the largest bombs would have a definite limit, any area could be threatened by fallout. The large number of weapons that probably would be dropped in full-scale attack would produce fallout, ranging from light to intense, over much of the nation. Weapons exploded close to the earth caused greatest fallout. Thousands of tons of earth particles were drawn upwards into the ascending melting cloud, where radioactive products, nuclear explosions, and temperatures. These particles are carried by high-altitude winds for many miles. Eventually, they settle to Earth, and this is called radioactive fallout. We are all subjected to radiation from outer space and from radioactive material at the Earth's crust. We're exposed to it when Dr. X-rays us and on many other occasions. Radiation in small or controlled amounts like that are not dangerous. But in large amounts, the amounts produced by nuclear explosions, radiation can make people seriously ill or even killed. Radiation produced by nuclear weapons presents a revolutionary threat to our people. In an enemy attack, it could become a direct threat to us all. Fortunately, there are means of protecting ourselves, means so effective that civil defense officials believe everyone can protect drive forward if they take true precautions to protect themselves. The biggest danger from all is the fact that the particles do not have to suffer to endanger. Their deadly rays can penetrate any place in life. The material through which they pass absorbs part of the radiation and reduces the effect. Your safety depends upon putting a sufficient mass between yourself and the falling. Concrete, brick, earth, or sand are the best. In a pinch, any heavy material will do. Civil defense officials recommend that everyone prepare a shelter. In most areas of the country, you would receive ample protection in a basement shelter constructed of 8-inch concrete walls. This provides the same shielding 12 inches of earth, 16 inches of wood, or 30 inches of wood. To be certain of adequate protection, the shielding should be that equivalent of 3 feet of earth. Civil defense officials recommend that for the best fallout, your family have to use 2 tents and 2 fallout shelters and enough supplies to enable you to stay in it for a maximum of 2 weeks. Within that 2-week period, it is estimated that community resources may have been restored within some time. Short-time later, assistance should be available from the state and federal government. Get started right away protecting your family from falls. Plans for approved shelters are available from your civil defense officials. Some of the shelters you can build yourself. The more elaborate models can be undertaken by contractors. Let us look at 5 shelters developed by the Office of Civil and Defense Organization. Any one of which will provide good fallout protection for your family. First, ancient concrete block shelter, typically designed as a do-it-yourself project. Cost will vary according to your area, but should range between $150 to $200 for the period. It will provide all the protection needed in most areas. You must ensure the shelter has proper doorways, air vents, and ceiling beams capable of holding 2 layers of concrete blocks. Plans for the shelter can be incorporated into new home construction. In all of these shelters, for example, you must ensure to use solid concrete blocks rather than the hollow blocks. The hollow kind will not give adequate shielding unless they are filled with cement, sand, or dirt. The second recommended shelter is the above-ground double-wall shelter. It is an outdoor, above-ground construction that also may be built with concrete blocks. It is ideal for regions where water, rocks, and asphalt build underground. Most people will want to hire a contractor to build it. Materials would cost about $700 plus contractor. Virtually absolute protection from fallout is furnished with a double wall, 20 inches of earth and 6-inch concrete steel covered with 20 inches of grass. Third, the 3-shaped metal shelter made from 3-shaped corrugated metal sections or precast concrete can be constructed either underground or above ground. This shelter is also suitable for regions where rock or water are close to the surface. When covered with 3 feet of earth and given a protected entrance, it also will provide almost absolute protection. The cost, like the double-walled shelter, is about $700 plus the fee of a contractor, who probably would be needed to build it. Number 4, an underground concrete shelter can be built by a contractor for about $1,000 to $1,500, depending upon the type of entrance used. Plans are designed so that it can have either a stairway entrance, such as is shown here, or with a hatchway. The shelter can be built with a roof at ground level and mounded over with earth, or it can be built below ground level or into an embankment. Last, the concrete basement shelter, similar to the underground concrete block, except that it is designed as an added room to the basement, either in an existing home or one underground. The shelter would add about $500 to the cost of the new home, and would be excellent to fall out. In construction of any one of these shelters, 4 essential features must be completed. The first is a proper entrance. It must have at least one right-angled chimney. Radiation travels in straight lines, only a fraction of it is scattered by air or material distance. So the sharp turns add to the field. The second necessity is ventilation. This is provided in a concrete block basement shelter by vents in the wall and the open entrance. The blower may be installed for added comfort. For the other shelters, vent pipe and the blower is essential for proper ventilation. Good radio reception is the next step. The shielding will cut it down. As soon as the shelter is completed, check the radio reception capability. It probably will be necessary to install an outside entrance to receive conduit from. Light is gas time. Civil Defense Shelter booklet will show him how to fix a simple electrical system. This will furnish adequate low-level light if you have a spare battery. You will also want flashlight or electric lantern for brighter light as needed. After your shelter is fixed, you can stock it with provisions, equipment, and ammunition for a 2-week trip. Since radiation outside makes it everyone inside, it is important that you have adequate supplies in your shelter. In choosing food, place the emphasis on those that require no refrigeration and little cooking. Foods in cans or jars will stay in good condition 6 or more months if kept dry at a temperature between freezing and 70 degrees Fahrenheit. Goods in paper boxes may be kept for 6 months if they are stored in tightly closed metal cans under the same dry, moderate temperature. Ensure they are in a spot where rodents and insects won't attack them. Plan meals where there will be no leftovers, thus eliminating the problem of rapid spoilage. Meat, poultry, fish, vegetables, fruit, many other items can be purchased in suitable quantities or cut down. It is a good practice to rotate canned foods at least once or twice a year. Change those in unprotected paper boxes at least every 3 months. Intimate food for infants, elderly persons, diabetics, and others who might require special attention. Ensure that you choose foods which fit the preferences of your family. Civil defense officials have stamped menus showing quantity of food set aside for each person. Use this as a guide. Water will also be important. You will need a minimum of 1/2 gallon per day. It should be stored in clean containers, preferably jugs, bottles, or jars, tight fitting cups. Water in a bottle will also be used if it is closed. Containers should be cleaned and refilled at least once every 3 months to keep the water out. Water purification tablets should be on hand to treat water which might contain harmful bacteria. For cooking and serving, you will want 1 or 2 pans. disposable tools, paper plates, cups, and napkins. Don't forget matches, can opener, and matches. You'll also want a small empty bin, which will use a minimum of hot space. The battery-powered radio is essential to provide communications with the outside world. For extra batteries, dry, cool, check the reception periodically, as early as in the receiver, on over dry. For cold weather, you will want lots of heavy clothing, warm bedding. In any weather, you will want some changes of clothing for all members of the family. A first aid kit will be very easy. Your civil defense officials have a list of the basic first aid items you must use. You should also have a 2-week supply of special medicines and prescriptions, contact tissues, things of insulin and hyperglycemia for diabetics. If you have a baby, remember to include powdered formula, and milk, bottles, nipples, disposable guides, skin, calcium, and soap. Provide sanitation supplies, pans, pipes to be lit, human waste, and garbage, and a receptacle with clean food. Don't forget such things as towels, sanitary napkins, and soap. And 5% baby food solution sent you for dinner. Remember how hard it is to keep the children entertained on rainy days? Maintaining high morale in your shelter will be even more difficult with cramped quarters and monotonous surroundings. Chauffeurs for midget parties, books, games, and other amusements. You will also want miscellaneous items, a calendar, clock, and pen, screwdriver, rubber gloves, and socks, also must be your hand. More information on the cars and ships, together with information on the approved fallout shelter, is contained in this book. Use it as your guide in planning and stopping your house. Now let's suppose for a moment that you can't get to your house in an emergency. What can you do to protect yourself? First, look for a base. One below ground with a cut radiation of 1/10 of the level option. Place a spot in a corner with the least exposed window, deepest below the ground. Instead of adequate order, you can improve a basic protection, locking the window with pictures, books, magazines, or other hidden materials. If you are in a house with no basement, best protection will be found on the ground floor in the central part of the house. The radiation there will be about half what it is outside. Large buildings such as apartment houses and office buildings afford excellent protection. With thick walls and heavy floors, they provide almost as much security as the special concrete block shelter recommended for renters. If you have reason to believe you can call out particles from your person or clothes, bathe thoroughly and leave the water outside. Outer garments always remain outside are all smelling more than a day or two. The washing of clothes, waterproof gloves, and fallout will be the primary threat which faces us in a national emergency. Keep in mind that it is a handicap. Right thing is now, food, alcohol, you will need a good shelter, 2 weeks supply of food and water, and other living necessities. You have them ready to learn as few safe as possible. You and your family stand the first-rate chance of surviving any nuclear attack. Talk to your local or state civil defense officials immediately. They will give you detailed instructions on what you need to do. Then do it. Then you can rest assured that no matter what the fallout threats the future, you and your family will be ready for it.
And what to do to protect yourself against it. Everybody needs to know. Yes, this does mean you. Watch and listen. One day, these facts may save your life. What is this fallout anyhow? Just bits of radioactive fall out of the mushroom cloud of the nuclear explosion and settle on the ground. These bits of matter can be dangerous. You're exposed to some radiation every day, from cosmic rays or other natural sources of radiation. These exposures are too small to hurt you. But when a wartime nuclear explosion occurs, a serious fallout follows. Thousands of tons of atomized earth, building materials, rocks, and gases may be thrown into the air. And the mushroom cloud containing them sometimes moves as high as 100,000 feet, nearly 20 miles up. Some of the radioactive particles spill out near the explosion site. Others may be carried for 10, 50, 100 miles or more. But how will you know if there is fallout? You can't hear, smell, taste, or see the radiation. But you yourself can detect the fallout particles that produce it. The easiest time to do this, without special instrument, is when the fallout is settling through the air. It starts any time from about 1/2 hour to several hours after the explosion, depending on how far away you are. And it continues to fall for an hour or longer. Usually you can see the fallout. So if there has been an explosion of a nuclear weapon within a 200 miles of you, you should suspect every unusual concentration of dust in the air of being fallout. After an explosion in daylight, watch any unusual accumulation of dust. At night, put a white or light-colored plate outside. Examine it every 15 minutes or so. If dust is accumulated on the plate, treat it as fallout. The particles in that fallout behave like miniature X-ray machines, sending out radiation in all directions. If there are many particles, and if you are exposed to them long enough, you will be hurt. Others will be watching for that fallout, of course. Experts will estimate the probable path and speed of approaching fallout and try to keep it focused. But it may come before you hear any details by radio or otherwise. You must take precautions, whether you hear their reports or not. If radio stations are operating, you will hear reports, especially on the Commonwealth frequencies 640 or 1240 on your AM dial.
as soon as it is safe for specially protected crews to get out into the open. These highly trained civil defense radiation detection teams will make a thorough check of radiation levels and characteristics. Those facts will be relayed to you by radio as fast as they come into civil defense headquarters in your area. Information from the radiation monitoring teams will be combined and analyzed by experts manning a central radiation control point. These experts, who know just how fast harmful radiation reduces in force, can predict when it will be safe for people to come out of shelters and resume normal tasks. We have warned that you may have to act before you get any detailed report. Just what can you do if fallout comes your way? Find the best shelter you can. The more solid substance you can put between yourself and the fallout, the better. But an ordinary frame house with windows closed will give considerable protection. In a house, it's best to get on the floor, away from doors and windows. Or if you can, find a location with additional walls in the center of the building. A basement is even better if the house has one. Large buildings, such as apartment or office buildings, give good protection. The thick, heavy masonry of their walls and floors makes it hard for radiation to get through. Basements, inside rooms, or corridors on the lower floors are safe. The basement of any house or building will become a good improvised shelter if you block the windows with sandbags and place other sandbags on the floor above the shelter area. If you don't have sandbags, thick, solid layers of books, magazines or newspapers, or even a series of file cabinets standing close to each other can cut the radiation danger. In some parts of the country, there are storm cellars or outside vegetable storage cellars. They may be used as shelters from fallout. If you plan to use such a cellar, or your basement, or any other shelter, stock it with food and supplies. To equip and supply your shelter area, you need some of the same things you might take on a vacation camping trip. First, sleeping equipment to fit your shelter area. Folding cots, or sleeping bags and blankets. Then, food and water. There should be at least a 2-week supply. You want plenty of fruit juices and lots of your family's favorite canned food. The drinking water supply should be rotated often to be sure it's fresh. Don't forget such basic needs as sugar, salt, pepper, and other seasoning that your family ordinarily uses. Now, some equipment. A radio is very important. It should be a battery portable with spare battery. A transistorized radio is best. The batteries last longer. Next, you need light in the form of flashlights and a battery-operated lantern. Then, a good first aid kit. Now, plates, cups, silverware. A can opener and a bottle opener are important. Add to these things enough closed containers to take care of garbage and human waste. Especially if there will be children in the shelter, include some books and magazines, paper and pencils, maybe 1 or 2 small, simple games. The best protection of all is the special shelter built according to specifications of your local civil defense organization. This has an air filter to allow ventilation, but keep dust out. It has at least 3 feet of earth over it. It would be a good idea to go right now to your local civil defense office to secure plans for the type of shelter you want. Then, to get busy on construction. Plans are simple, using standard materials. So maybe you can do the job yourself. But all this special shelter talk won't help very much if you are caught way out on the open road. If that happens,
Keep driving until you see a building, maybe a house or barn, church or school. Drive as close to the building as you can. Then get yourself and your family out of the car and take cover in the building. If you live on a farm and have sufficient warning, get your animals under cover and give them enough food and water to last several days. And if you can, cover any piles of hay or harvested crops that may be outside. If the explosion has been some miles away, you will have time to fill tubs and other containers with water before fallout arrives. All locations where outside dust does not penetrate will be safe storage points for water. Whatever kind of shelter you find, settle down and make the best of it. If there are others with you, help them by being as calm as you can, and don't be discouraged. You can go out for very brief periods if you are well covered and keep the dust off your skin. Wear heavy boots or shoes, and pants tucked in or tied around the bottom keep dust out. If any dust gets on you, brush it off promptly. When you have a chance, wash it off. That dust can burn your skin. But what happens if you do get exposed to a great deal of fallout? Food or water has been contaminated by the dust. Internal damage may occur. When dust has been left on skin, there will be skin burn. When you have been near dust too long, there may be radiation sickness. Exposure can even cause death. If you have had considerable exposure, you will vomit and grow weak. But after a few hours, this sensation will pass. And by the next day, you may have had the last. Even if you have been exposed to excessive fallout, you may eat and drink just as you normally would. But don't force yourself. Whether you have had these symptoms or not, if Civil Defense radio announcements have said that radiation has been high in your section, keep an eye on your condition for the next few days. Watch especially for these developments in the 2 weeks following exposure. Return of nausea, sore throat, bruise spots developing without any known reason, loss of hair. These conditions, or nosebleed, or diarrhea, should be reported to a doctor or to the nearest first aid station set up under civil defense plans. Unless civil defense teams have warned that your area is still dangerously radioactive, you can get out and work to help yourself and help others. Although fallout can be deadly, your chances of avoiding damage from it are much better if you follow the directions we have given you. During an alert, keep your portable radio tuned to the Commonwealth radio frequencies, 640 and 1240 on the AM dial, for the latest reports and advice. Right now, today, before there is an alert, take time to learn the Civil Defense 5 steps to safety. Learn warning signals and what they mean. Learn your community plan for emergency action. Learn protection from radioactive fallout. Learn first aid and home emergency preparedness steps. And learn how to use tunnel rad, 640 or 1240 on the AM dial for official directions.
2,500 years ago, Democritus said, sweetness, bitterness, warmth, cold, and color are only appearances. In truth, nothing exists but atoms and the void. Ever since the beginning of history, lonely men have searched for a pot of gold under a distant rainbow. Now the prospector has become, in a sense, a scientist. Now the object of the search is not only gold, silver, and copper, but also uranium, a radioactive metal which signifies its presence by the reading on a Geiger counter. Scientists foresee that in future years, uranium may supply power to heat our homes, drive our cities, and engineers dream. Future reality. They lose. Atomic power will require years to develop and apply. But atomic energy has still another aspect. The nuclear reactor, incubator of plutonium, precursor of the atomic power plant of the future, is also the source of radioactive materials known as radioisotopes, available now as peacetime weapons in the continuing struggle for health, material satisfaction, and scientific progress. The radioisotope is probably the most important new means of perception and investigation since the invention of the microscope. To use this new means of perception, the scientist has been forced to acquire many novel techniques, absorb a variety of concepts unfamiliar to him. Radioisotope becomes useful to the scientist only when these concepts have taken their places in an orderly structure of method and underlying theory. The first concept the scientist takes, those which have to do with the nature of matter and the dynamics of its smaller components. Now it is known that the atom, long considered the basic unit of matter, is itself a void, in which planetary particles called electrons revolve in great orbits around a central nucleus. The nucleus also has a structure. It is composed of protons and neutrons. Each proton has a weight of 1.00758 atomic mass units. The neutron is slightly heavier. In the usual notation, the mass is shown in round numbers, one for both proton and neutron. The proton carries 1 unit of positive charge, indicated in subscript. The neutron has no charge. The electron has 1 unit of negative charge. Its mass is insignificant compared to that of a proton or neutron. Again, charge is shown in subscript, mass in superscript. In describing an atom, the same notation applies. The atomic number of the atom, in subscript, is equal to the number of electrical charges carried by the protons in the nucleus. The mass number in the superscript is equal to the sum of protons and neutrons. Designation for helium is 2, 3, and 4. Normally, the positive charge of the 2 protons in the nucleus is balanced by the negative charges of an equal number of orbital electrons. Atoms can be classified according to the number of protons in the nucleus, or the atomic number, and according to the number of neutrons. In terms of proton number and neutron number, it is possible to define any atom. Normal hydrogen atoms, for instance, have 1 proton and no neutrons. Helium has 2 protons, usually has 2 neutrons. Lithium most often has 3 protons and 4 neutrons, and so forth. The other atoms are identified according to the same system. The number of protons, or the atomic number, most elements, there are found atoms of different neutron masses. These different forms of the same element are isotopes, atoms of the same element, alike chemically, differing only in the number of neutrons. The sum of protons and neutrons is the mass. An atom of helium, which has 2 protons and 2 neutrons, has a mass of 4. Lithium atom, with 3 protons and 3 neutrons, has 6 mass units, and so on. Different isotopes of the same element have different mass numbers, because they have a different number of neutrons. Again, to complete the description of each atom, the element is accompanied by its atomic number in substance. Most elements have 2 or more isotopes. However, a few have only 1. For instance, cobalt, element number 27, has only 1 natural isotope. All cobalt atoms found in nature have the same atomic weight, 59. Therefore, the same number of neutrons. However, most elements have more than 1 natural form. For instance, zinc, number 30 on the chart, has 5 natural isotopes. Zinc, as in most elements, the number of neutrons is greater than the number of protons. The number of neutrons can be found by subtracting the proton number from the mass number. Higher on the chart, a few additional elements have only 1 isotope, though most have several. At higher atomic numbers, the ratio of neutrons to protons becomes greater and greater. The natural isotopes of mercury, for instance, the lightest atoms have 116 neutrons, 36 more neutrons than protons. The heaviest have 124, 44 more neutrons than protons. To illustrate neutron-proton ratio, the isotopes can be plotted on a graph of atomic number against neutron number. In this graph, a straight diagonal line would intersect all points at which proton number equals neutron number. However, if the isotopes found in nature are plotted on such a graph, it is found that they depart from the diagonal. In other words, they have a preponderance of neutrons over protons. A preponderance which tends to increase at higher atomic numbers. With a few exceptions, these positions represent atoms with stable neutron-proton ratios, capable of existing indefinitely without any observable change. The empty spaces represent neutron-proton ratios which would not be stable. It is reasonable to assume that if an atom existed in an empty space on the chart, it would show a tendency to change itself to an atom having a more stable neutron-proton ratio. For instance, an atom occupying a position above the natural isotope would have a disproportionately high ratio of protons to neutrons, and would tend toward the position of one of the naturally stable isotopes below it. Similarly, an atom having a disproportionate excess of neutrons over protons would tend to take a position of one of the naturally stable isotopes above it. This illustrates one of the primary principles of nuclear physics, the tendency of all atoms to reach an equilibrium in terms of a stable neutron-proton ratio. Up to atomic number 83, the natural isotopes are stable, with a few exceptions. However, above atomic number 83, all the isotopes are unstable. They all have a disproportionate number of neutrons, either too many or too few. Without exception, these isotopes are radioactive and return to stability through a process known as radioactive decay. For example, uranium, the heaviest element found in nature in position, has 3 natural isotopes. Each uranium isotope tends to return to stability through a series of transformations ending in a stable form of lead. Polonium-238 changes to lead-206. Transformation from instability to stability is a complex process which takes place in a series of separate steps. The first step occurs when the uranium atom throws off a nuclear particle of 4 mass units composed of 2 protons and 2 neutrons. This single unit is known as an alpha particle. In this case, the uranium-238 atom becomes thorium-234, which has 2 less units of charge on the nucleus and 4 less units of mass. The nucleus of the thorium atom emits an electron, which possesses a negative unit of charge and negligible mass. This electron, thrown off by the nucleus of the thorium atom, is known as a beta particle, and is usually represented by the Greek letter beta. With this emission of a negatively charged beta particle, thorium-234 in turn changes to protoactinium-234, an atom with 91 charges instead of 90 on the nucleus. Protoactinium-234 throws off the beta particle, increasing atomic number by 1, thus changing to uranium-234. Uranium-234 next throws off an alpha particle to become thorium-230. In successive transformations, further alpha particles are given off, resulting in radium-226, radon-222, polonium-218, and finally lead-214, an unstable isotope. 2 beta particles are emitted successively, producing bismuth-214 and polonium-214. Polonium-214 gives off another alpha particle to produce lead-210, still unstable. Again, 1 beta particle is emitted in each of 2 changes. To form polonium-210. With the emission of a final alpha particle, polonium-210 goes to lead-206, a stable isotope. Thus, in radioactive decay, a complex series of nuclear transformations has taken place from an unstable neutron-proton ratio to a stable state. In every step of radioactive decay, the transformation is from parent to daughter, and parent to daughter. Atoms of the parent element decaying to produce atoms of a daughter element. The same terminology applies whether or not the transformation is to a higher or lower atomic number. There is no way of foretelling when any particular unstable nucleus will decay from one step to the next. However, in any sample of the radioactive isotope having millions of billions of atoms, some of the atoms are always in the process of decay. The number of atoms decaying in a unit time in a sample of radioactive isotope is called the activity of that sample. Activity, or rate of decay, is generally stated in terms of millicuries, or MC for short. A given sample of radioactive material is said to have an activity of 1 millicurie when 37 million atoms decay or disintegrate per second. Millicurie is the commonly accepted measure of radioactivity. Decay from a parent isotope to a daughter isotope can therefore be illustrated in terms of the number of unstable atoms and the time. On this graph, the number of unstable parent atoms that exist at any given instant can be represented by a point. Since the parent substance is decayed, fewer unstable parent atoms will be present at any later instant. In language of chemistry, the number of parent atoms has decreased by delta N during a time interval delta T. the slope of the line between the 2 points corresponds to the rate of decay. The rate of decay, delta n over delta t, is proportional to n, the number of parent atoms present, or equal to minus lambda n. Minus sign indicates that n decreases with time. Lambda is called the decay constant, and is characteristic of the particular parent radioisotope. If decay is plotted as a continuous series of short fractionals, an exponential formula is derived, which is the basic standard formula for radioactive decay. In this formula, n is the number of radioactive parent atoms present at a given time. N sub 0 is the number of radioactive parent atoms at the beginning of the first time. E is the base of the natural logarithm. Lambda, of course, is the decay constant of the parent substance. Since the number is proportional to the activity, the symbol n can be replaced by a throughout the formula. Accordingly, the same curve can equally well represent the change of activity rather than number versus time. From this equation for radioactive decay, activity at any moment can be determined in terms of the initial activity. In any decay process, there is a point in time at which activity is equal to 1/2 of that present initial. This time during which activity has decreased by half is known as the half-life. In successive half-lives, activity continues to decrease by successive halves, until finally only a small fraction of the original activity remains. Since the decay rate for a specific radioisotope is usually given in terms of half-life, it is often convenient to substitute half-life for the decay constant lambda. The equivalent of lambda is 0.693 divided by half-life. This formula is often used in finding activity at any time t when half-life is known. Plotted in terms of the logarithm of activity against time, exponential decay is shown as a straight line. Figures for half-life are generally available in high school literature. Each radioisotope has a specific half-life. Half-life may vary greatly, from a fraction of a second to thousands or billions of years. For instance, one isotope of cadmium has a half-life of 2.3 days. Carbon-14 decays to its brother nitrogen after a half-life of roughly 5,700 years. Or take the case of uranium. U-238 has a half-life of 4.5 billion years, giving a straight line on a graph calibrated in terms of days or weeks. In contrast to the long half-life of U-238, thorium-234, the daughter of U-238, has a half-life of 24.1 days. Thus, while all steps of decay are unpredictable in a single atom, the statistical rate of decay in a large number of atoms can be predicted and measured with great accuracy. Examining the various steps in the decay series beginning with U-238, it appears that there are at least 2 ways in which unstable atoms can change to a more stable form. By throwing off particles, losing 4 units of mass and 2 electrical charges, or by throwing off a beta particle and increasing atomic number by 1. In the process of decay of U-238 to stable lead, each of the 2 types of transformation occurs several times. In 8 steps of decay, 8 alpha particles are given off. One would assume that these 14 particles would account for the mass difference between uranium-238 and lead-206. Let's check this for some minutes. The exact weight of an alpha particle is known from accurate determination. 8 alpha particles thrown off weigh 32.022 units of mass. The mass of beta particles is also known with great accuracy. Adding the weight, it is found that 32.025 units of total mass have been given off as discrete particles during the decay process. But if the weight of lead-206 is subtracted from that of uranium-238, we find that the total mass lost in the decay is somewhat greater than that represented by the alpha and beta particles thrown off. In other words, 0.045 units of mass are unaccounted for, representing a minute fraction of a gram. According to Einstein's formula, energy and mass are equal. Subsequently, problem solving, it is found that this mass represents a really significant energy. The transition from uranium to lead, this energy has been released in addition to the alpha and beta particles. Most of this energy released during uranium decay has been applied in giving the ejected particles their high speed, in other words, as kinetic energy. Additional energy is also released as a form of electromagnetic energy known as gamma radiation. To summarize, the decay of uranium-238, resulting in stable lead, is accompanied by the release of alpha particles, beta particles, and gamma radiation. This is generally true. A change from instability to stability is accompanied by energy released as discrete particles or electromagnetic radiation, or both. It is the energy released by the decay of uranium in uranium-bearing ore which makes it possible to detect it with a Geiger counter, even though mixed in minute proportions with a variety of other substances. The decay series beginning with uranium-238 is only one of several. A similar decay scheme begins with U-235, another with thorium-230,